Going to hear is by Nobu Okoda. The title is a unified model for solving big problems of the standard model. Please go ahead.
Right, thank you very much. And first of all, I'd like to thank the organizer for the invitation to this very, very beautiful place. Today, I'd like to talk about I try and to solve some big problem of the standard model by to get some unified picture. And my talk is based on my recent work with Ravi Mohapatra in Maryland.
So, no, maybe you can be speaker.
Okay.
Speaker, yeah.
Okay, all right, this guy. All right, so the first introduction of motivations, and of course we have been working on the beyond the standard model because we have the many reasons to do that, of course, and we need to go beyond the standard model. So let me go through the introduction quickly. Okay, and first I need to apologize that actually my talk is not only SUSY theories, and actually my talk is on the non-SUSY theories, and I have some small reason for that. Something like the SUSY has been sick a little bit for a while after the LHC and the COVID-19 probably. So yeah, but I like SUSY very much, but while she is recovering, I'd like let me discuss about the non-SUSY theories. And actually in this conference, that's the SUSY conference, we have lots of actually the supporting message to SUSY. So let's wait for a while, right? Okay, so first I'd like to talk about the 5 big questions, and that the standard model cannot answer. And the first one is the neutrino mass. So why are the neutrino mass non-zero and so tiny? Of course, we know that the neutrino has mass and the flavor mixing, but the neutrino is just a massless particle in the standard model. So we need to solve this problem. And then second one is the dark matter problem. And we know the energy budget of the universe, 27% of the energy budget of the universe is coming from dark matters, and we don't have the suitable dark matter candidate in the standard model. We have to go beyond the standard model to solve this problem. The third one is a cosmic inflation scenario. Inflation scenario is actually the standard paradigm of modern cosmology, and to solve the problem, several problems of the Big Bang cosmology. And so simple scenario is, through low inflation, so we introduce the scalar field to drive the inflation. That's the so-called inflaton. And but we don't have the suitable inflaton candidate in the standard model. The next question is the origin of the baryon and the antibaryons, or matter and antimatter generally. And we know the baryon in the universe is much greater. The number of the baryons is much greater than antibaryon numbers in the universe. And also we have this quantity, the NB over S entropy ratio is actually 10 minus 10. We have to explain this one. Okay? And unfortunately, after the discovery of the Higgs mass is 125 GeV. Actually, we cannot discuss we cannot use the pure in the standard model case, and we cannot discuss the electric baryogenesis with this big mass. Actually, the 125 Higgs mass is too big to cause first order phase transitions. All right, the fifth one is the CP violation. Why the CP violation in the QCD sector is so small? Of course, we call it the strong CP problem. And as you know, if tilde term is the gauge invariant, we can add Weber, and this parameter theta must be really small to satisfy the experimental constraint. So why this is so small? That's the problem. All right. Okay, the next thing I'd like to discuss is just we have lots of ideas to solve each problem. Yeah, let me go through the base ideas, some of ideas related to my talk. All right, the first one is a neutrino mass problem, and we have the so-called Weinberg operators. It is a gauge invariant, but they are violating the Lepton numbers. So we can write up this operator, and that's the so-called Weinberg operators, right? So then they plug in the Higgs vacuum expectation values, we get the neutrino mass. Here, this dimension 5 operator, we have the denominator here. All right, so the seesaw mechanism, so this is like introducing the new particles. Away from the potential minimum in the other universe, and suppose this potential is really flat. In this case, the particles is slowly rolling down. Oh, okay, thank you. Okay, slowly rolling down to the potential minimum. Actually, here the potential energy dominates the potential energy density of the universe. We get the effective, we get the jitter space. We have the exponential expansion of the universe. Okay, after that end of inflation, then inflation oscillate around the potential minimum. Eventually, this decays to create the. Oh yeah, that's right. Okay, all right. So then that hits the universe, right? So this scenario is also we have the quantum fluctuation of the inflaton field here. That's magnified to the macroscopic level, and by the inflations. Okay, so actually the inflation scenario, we have the very precise measurement of the cosmic microwave background, and now we have the very, very strong constraint on the inflation scenario. This is the observation result. In a figure, this is the tensor to scale ratio. This is the spectral index. Actually combined, this is a recent result combining the Planck 2018 result with the bicep and the keck. And so we got now, this is the combined regions here. Then this one sigma contour, two sigma contour. We have the very strong constraint, the very constraint for the inflation scenario. Any inflation scenario must satisfy the power spectrum of the scalar, this quantity, and spectral index around the 0.965, and also tensor to scalar ratio. Now the combined these, the data is actually we get the upper bound like this. Okay, this is the constraint. All right, the inflation scenario, slow inflation scenario is a very simple scenario to derive the inflation. To derive the inflation, so we have the scalar field and the potential there. And it's everything for the inflation and prediction calculations is given by the potential derivatives, first derivative, second derivatives, right? The calculation just the standard way. And the slow parameters are expressed in this way, and power spectrum expressed in that way. They are all expressed in terms of potential and the potential derivatives. All right, in this way, to satisfy the experimental constraint and to get the power spectrum, the 2 times 10 to minus 9, and also we fix in the analysis, we fix the E-holding number, and say this quantity is something like the 50 to 60, the good number to solve the horizon problem. Then we can fix the parameters in the potential to get the prediction, inflationary prediction for the spectral index and tensor to scalar ratio. All right, so here I'd like to introduce the very simple slow load inflation scenario, which is called non-minimal lambda phi 4 inflation. Okay, the idea is quite simple. We have the inflaton field phi. This is the real scalar, but of course it's easy to extend this complex scalar field case, and we have the potential here. But the interesting point here, we can add the so-called non-minimal gravitational coupling proportional to the dimensionless parameter c and phi squared term. Oh, this is the Planck unit. And then during the inflation, the phi body is really big, and it is natural to think the lambda phi 4 potential dominates. All right? So using this one, we can calculate the inflationary predictions. Interestingly, after fixing all the parameters, the spectral index, and fixing spectral power spectrum value, and fixing the E holding number 60, let me consider 60 case. And everything, all the inflationary prediction is actually controlled by the non-minimal coupling Xi, dimensionless parameter here. Xi equals 0 is a minimal at the textbook lambda phi 4 chaotic inflation scenario. The predicted value here is, of course, far away from the actual allowed region here, right? However, the switch on the Xi values and make it bigger, and actually the prediction goes down that way, then it eventually gets inside the contours, and to get consistent with the experimental result. There are another interesting point of this scenario, the really simple scenarios. We take the Xi very large. Actually, we have the asymptotic value for the tensor to scalar ratio, and that value is something like the 0.003. We cannot get the value smaller than this. However, the interesting thing is that in the future, and the future experiment like the CMB stage 4 or the light bird will cover this region. So that's an exciting thing. Okay, so non-minimal lambda phi 4 inflation, very simple inflation scenario. That we need to do, for what we need to do is just add the non-minimal coupling, and the lambda phi 4 potential dominates during the inflation. Then we get the perfect result, actually consistent with the experiment, right? Okay, and the fourth problem, and baryon asymmetry, baryogenesis, in my talk, I'd like to focus on the so-called Affleck-Dine mechanism. They are the very interesting idea by the Affleck-Dine many years ago, and we introduced the complex scalar field, which carry the baryon number or lepton number, all right? So then we add the potential, and for the scalar, complex scalar field, we add the first part is here the symmetric part, phi dagger phi part, and then in addition to that, we add we have the asymmetric term. That's the explicit violation of the baryon, the lepton number term. Okay. With this one, and we consider the suitable initial conditions in our universe, then we consider the evolution of these particles. All right. So this evolution of particles that actually this phi 1 phi has the baryon number or lepton number, and the baryon number lepton number, then the baryon density, this case say it has the baryon numbers, and the baryon number density is expressed in terms of this way, right? The phi q is the baryon charge, or the baryon charge of this field phi. Then you can see that this is a combination of phi 1, phi 2. You can see that the phi 1, phi 2 evolution is asymmetric. Clearly, we get the NB non-zero. So this is the idea. Okay. This is just illustration purpose, and I'm showing that there are some solutions and numerical results of the equation solution of equation motion, and I was putting the suitable value, the suitable potential with the asymmetric term, and I have the evolution of phi 1, phi 2, the imaginary part, the real part, and that's circling around the potential minimum, starting from some point. So during this evolution, we get this co-moving frame baryon asymmetry of the universe that the baryon asymmetry universe is created. Okay, so once we get the non-zero baryon asymmetry, it's there, created, and stored in the vacuum by the Affleck-Dine field, and the Affleck-Dine field decays to the standard model particles through the operator with the phi and the standard model operator. We may have the BSM operator there. Then the phi decay that creates this particle, and then then the baryon and the lepton number transmit this to the standard model sector. That's a scenario. Okay. So now, and I talk about the inflation scenario. That's a scalar there, and Affleck-Dine field is also a scalar. And you may think that we can combine this scenario, just unify this scenario. Actually, recently, we have many works on this and ideas. Actually, this idea works. Okay, and identified as Affleck-Dine field has an infraterm. So that's kind of unification. Right? Okay, the basic idea is just like this. I already explained the lambda phi 4, the non-minimal lambda phi 4 inflation. The idea just for like this. I say, and there are some scalar field there, and the very early universe, the lambda 5 potential at the dominant, and we add the non-minimal coupling, gravitational coupling here, then we get the perfect the inflation, very simple perfect inflation scenario consistent with the experiment. All right? So then that's the idea. So if phi body is very large, we get the inflationary predictions. Then after that, and the phi becomes smaller, this part becomes irrelevant, right? So that becomes very small, and the Planck suppressed part. And so we don't care about this one. After that, we can consider Affleck-Dine baryogenesis. That's the unification picture, unification, the idea of the unification of Affleck-Dine field with the inflaton field. Okay, so here in my talk, and I took the recent idea and proposed by the Stubbs and McDonald, and they consider this scenario, and just introducing the very simple potential, the mass term, quartic term, and then explicit explicit baryon or lepton number violating term, baryon or lepton number violating term, and that's the parameterized epsilon, some small quantity epsilon times m squared. Okay. So then we consider the equation of motion for the real and imaginary part. It is just something like this. You can see that these formulas and the M1, M2, in the presence of this term, we have the mass differences for the real part and imaginary part. And so the evolution, so that is actually the origin of the asymmetric evolution of phi 1, phi 2. Then we can create the various symmetry of the universe. Okay, the story is the following. Step 1. We have the lambda 5 term dominates over the potential, and we add the non-minimal coupling. Then we get the good inflation scenarios. Right? So here we point the inflaton is a complex scalar. We assume that the initial value of the inflaton and the horizon equidistant scale, we have the non-zero theta values. And suppose the theta is order 1. Okay. So after that comes to the end of inflation, then the oscillation happens. The first, and we have the oscillation, the still lambda 5 term dominates. This is the symmetric term. So that in this evolution, during this evolution, theta value is still the constant. Okay? Then after that, the amplitude of phi becomes smaller and smaller. Eventually, and the m squared term the dominates. Then we have the damped oscillation, damped harmonic oscillation here. However, in the phi 1, phi 2, and in the presence of this one, M1 and the phi 1, phi 2 mass is different. So that we have the symmetric evolution of the phi 1, phi 2. Then we get the baryon asymmetry of the universe. Okay, that's the idea. And then the baryon asymmetry is stored in the vacuum in this field. And then this field, Affleck-Dine field, actually this is the inflaton field, decays to transmit the baryon asymmetry of the universe to the standard model sector. At the same time, this is the reheating process. Okay, that's the unification picture. Actually, there's some calculations that we can find that the formula in V over S is really, really simple formula like this. Okay. So you can put some numbers there and to get the 10 to minus 10. All right. Okay. Fifth one is just action model. I think everybody here are familiar with that. Let me skip it. Okay, so now they come to unified model proposal. Actually, model is really simple. I need only 5 minutes. Okay. All right, so the particle contents, the relevant part is just like this. Consider the lepton number, and the lepton doublet in the standard model, and lepton singlet. In addition to the standard model particle, we add the 3 generation, the simple case is 3 generation of the vector-like doublets, and then singlet, and 3 generation singlet chiral fermions. Okay? So these are vector-like fermions, and these are chiral fermions. And then we have the one scalar here, which carries the lepton number. This is actually AD field and inflaton field, the unification. All right. So then a Lagrangian model is like this, the inflation term, Affleck-Dine mechanism part, and also Yukawa coupling, and also the mass term. This is fermion mass term. And the first two part is the non-minimal coupling for the inflation here. And then this is Stubbs, McDonald, and the paper, McDonald paper. They actually we follow their way, and the potential for the phi field is very simple: the quadratic term and the quartic term, and the explicit breaking term here, the lepton number breaking term here. Okay. So then Yukawa coupling, we can write up the Yukawa coupling gauge invariant way in a particle with the particle content, and then also we can add the mass term, gauge invariant mass term for the extra fermions. That's the Lagrangian. Okay. So first, by using this Lagrangian, actually we can draw the dimension draw the one loop diagram to generate the neutrino mass. This is so-called the radiative seesaw model. So you can see that connecting the whole stuff, and we get the effective the dimension 5 operator, the Weinberg operator this way. But the important thing is like here and the phi field, that's the AD field, the infraton field, plays a crucial role to get the one loop diagram. You see that this term with the mass insertions in this explicit lepton number violating term. Then we get the neutrino Majorana mass term. All right. Okay, so this is so-called the radiative seesaw mechanism, and that's calculation, the one-loop calculation, we get the expression for the neutrino mass matrix over this form. Okay? Well, actual calculation, we choose just a diagonal Yukawa coupling and so on to simplify it. All right. This is the benchmark scenarios, and we have the variety of the numbers and consistent with the experiment. And this is just one example. And choosing the epsilon value 10 minus 5, the infraton mass is 10 to 6. Thank you very much. And the heating temperature is just one order magnitude smaller to avoid the washing out process, actually. And then choosing the mass for the vector-like fermions, the doublet fermions. And two of them are very heavy, but the only one is the kind of 1 TeV range. And then choosing the suitable Yukawa coupling, then we can reproduce the neutrino oscillation data. Right. Then for the dark matter part, the WIMP dark matters, maybe some of you they noticed that in this model we have the singlet fermion and the doublet vector-like fermions. Okay? That structure is the so-called singlet doublet fermion dark matter scenario. Actually, that is already here. And so the dark matter is a linear combination of the doublet charge neutral component in the doublet and the singlet, okay, the fermions. And here we take the doublet must be the 1 TeV. And that is actually this structure of this dark matter is very, very similar to the well-known Higgsino-like dark matter in MSSM. And so then taking the mass of the dark matter to be the 1 TeV, we get the right value for the electric density, observed electric density. All right, so then I already talked about the unification time mechanism and the inflation, right? What we did is the complex scalar here, I add the non-minimal coupling there, and then adding this potential with the explicit lepton number violating term. And then inflation, the universe, the phi value is very large, we have the successful inflation scenario. After that, we have the generation of the lepton number. Here, this is the lepton asymmetry. So that converts to the baryon asymmetry by the Farnelon process. And the formula is very simple. By using the formula is very simple. Just this is the formula. And plug in the benchmark values, you can get the 10 minus 10. Okay? So now, this is summary. So let me summarize what I did. What's the actual proposal? The first thing, we have proposed a unified framework for solving so far the 4 major puzzles of the standard model. Okay? What I did first, I introduced the AD field or inflaton field, which carries the lepton number 1. Then the inflation happened. Of course, when I introduced the non-minimal coupling. Okay, so then this explicit breaking term, lepton number violating term is introduced. And this is the crucial for the afflict dying mechanism to generate the baryon asymmetry of the universe. This gets first, the lepton asymmetry of the universe. Okay, then after that, in this guide, AD field and the infraton decays, right, to transmit the lepton number stored in the vacuum to the standard model sector. Here, this case, the standard model lepton doublet, and it's a part, and then the D1. This is actually the massive doublet, the vector-like doublet, right? This is the process, and also this phi field is the infraton. This is also the reheating process, right? Then after the electric symmetry breaking, and we have the mass mixing between the doublet component and the singlet component by the Higgs band. Okay, so this is the fundamental Feynman diagram for each process to generate the inflations and also the baryon number, lepton number symmetry, baryon number symmetry generations, and the dark matter candidate is also included. Using all the diagram, actually you can get the one loop diagram for the neutrino mass. They are all related. This is thank you very much, the unified picture. Okay, I'm almost done. And now, so the last comment. Actually, we are preparing a new paper. And so my talk, the strong CP problem solution is missing. Actually, we can implement the action model easily. And the basic idea is like this. I consider the Affleck-Dine inflaton field unification. And this is the crucial term, right? We have the explicit breaking term. We can replace this one by we can consider this term generated by some complex scalar web. But this complex scalar, actually, we consider the lepton numbers. Actually, the lepton number. But actually, this lepton number is identified with the Peter-Quinn U1. Actually, we can do that. So in this way, we can create this term, explicit breaking term, by the Peter-Quinn complex, the action model, the complex scalar field web. So this is the way. Then we combine our scenario I explained with the invisible action model. So then the action models, and then we can solve the 5 problem in this way. Okay. All right. So that's all. Thank you very much for your attention.
Any question for Nobu?
Maybe it's not on. Yeah. Do you remember the number of no.
Can you go back to your slide 44?
Oh, 44. Okay. Let's see.
Maybe we can put that away for now because it seems like
All right.
this always makes noise. We'll try a little bit, see how it goes. Yeah? Okay. So this is the one you hold, but I will first. So we are happy to have Ignatios Antoniadis telling us about challenges of an accelerating universe in string theory.
I thank the organizers first for the invitation, and I'm glad that I'm in Ioannina again in the Supersymmetry conference in presence. So the motivation comes from the universe evolution that at least in two instances we face cosmological constant. This one phase is today, if the results on dark energy imply a cosmological constant, and a second instance is in the past during inflation, which in the simplest case is in a flat region of the scalar potential, which again is described by the de Sitter vacuum. So the search for the de Sitter vacuum in supergravity, and in particular in string theory, is more involved because in string theory the vacuum energy and deflations are related to the moduli stabilization problem. So one has to have a mechanism of of stabilizing first all the moduli. And the difficulty is to find the Sitter vacuum led to a conjecture by Kumlum, Guri, Palten, and Hugh that restricts the first and the second derivative of the potential. Putting together these two constraints forbid the Sitter minima, but allow maxima. However, they also restrict a lot, challenge, I would say, the slow roll conditions of the single field inflation because they restrict, they constraint the two slow roll parameters. And there is an ongoing debate on the validity of these assumptions, and in particular on previous proposals like the KKLT, which are going on. Here, what I'm going to describe is an explicit construction which uses quantum corrections and which will lead to the Sitter. So I will first describe I will go very briefly through the history. I will use the mechanism of the framework of KKLT. So we'll start by compactifying type 2 theory on a Calabi-Yau manifold in which you obtain an equal to supersymmetry. The geometric moduli belong to complex structure which are in vector multiplets and Keller class which are part of hypermultiplets, and in addition we have a string dilaton, which is whose expectation value fixes the string coupling. Then one turns on three-form fluxes in a particular way that that break half of the supersymmetry to n equal 1. Consistency of the theory implied to introduce at the same time orientifolds and the d-branes. And then at the end, one obtains a superpotential and therefore a scalar potential that allows to fix in a supersymmetric way the complex structure moduli and the dilaton. I will not challenge this part of the mechanism, so I will assume this to happen. And then I will go on to the Keller moduli, which have a vanishing potential at the classical level due to the non-structure of the kinetic terms of the Keller potential, which combine with a constant superpotential depending on the fluxes that is left over from this minimization, gives a vanishing potential. Now, there are two mechanisms that were proposed to fix the Kähler potential. The ingredient is a non-perturbative superpotential that can be either understood in effective field theory as a Gaussian condensation from the gauge groups on deep branes, that was an old proposal, or in the context of string theory, deep brane instantons. Turn it off. One takes a lambda phi to the 4 theory and computes quantum corrections, the effective potential. Then this is a perturbative series function of lambda. Lambda depends on the field, so because it runs the radiative corrections, times phi to the 4. And this potential has a minimum either at lambda equals 0, which is weak coupling, zero coupling, or lambda of order 1, if phi, of course, is different than 0. Now, in Coleman-Weiber, you use one has two couplings, the lambda phi to the 4, and one assumes also that phi has gauge interactions. Let's say take scalar QED, so it has a gauge coupling, and therefore the potential gets this form. The first is a lambda phi to the 4, and the second comes from the gauge interaction. So the observation is that if both you can consider both couplings to be perturbative, less than 1, but lambda of order e to the 4 in a way that the minimum then is trustable, depends on this exponential form minus lambda very square, where both couplings are weak. So the proposal is to make a realization of this variation, of course, of this proposal in string theory, and replace the Giacchino quantization part by logarithmic corrections in the f part of scalar potential, while using the d terms to uplift it as in the large volume scenario. So the first step is how to find where to find logarithmic corrections in string theory. In general, logarithmic corrections could arise by when one has propagation of massless particles in less than 2 dimensions. So in 2 dimensions, massless propagator is logarithmic, gives you logarithmic dependence on the space of the space of propagation. While at 1 dimension you get linear corrections. We have done some work in the past with Kostas-Backas. This actually can be realized in string theory, and the ingredients is the following. Suppose that you have some D brane here, where you have localized couplings on the brane, such like the Gates couplings, the Gates kinetic terms. And then from this, you can, from this brane, you can emit closed strings that hit some distant orientifold plane or a distant brane, so that you create local tadpoles. Now, if the propagation of the closed string in this in the bulk is effectively 2-dimensional, then one gets logarithmic corrections. If it's 1-dimensional, then one gets linear corrections. Otherwise, it's finite. So this, the propagation is 1 over p square. Even the space is compact, then the 1 over p square becomes sum over the excitations. And then one finds these logarithmic corrections. Now, of course, the theory needs local tadpoles, which have this form. I mean, there is a contribution from orientifold planes and D branes. The global tadpole is 0, as it is required for consistency, but it can be local tadpoles. So for this one needs localized couplings on the brane, for instance. We are talking about corrections to the scalar potential. The corrections to the scalar potential come partly from the superpotential, which the superpotential is fixed, cannot receive corrections. So they can only come from the Kähler potential. Now, in type 2 strings, the corrections to the Kähler potential are directly related to the corrections to the Planck mass. In other words, to the gravitational couplings, as we studied in the past. And indeed, when one considers type 2 strings on Calabi-Yau compactification, then in the large volume limit, you can obtain localized couplings, or gravitational couplings, which can be easily understood, starting from the 10-dimensional term, which contains 4 Riemann tensors in a wedge product, in which 3 of them can be saturated on the Calabi-Yau, on the compactified space, and give rise, when you integrate over the internal space, gives rise the Euler number of the Calabi-Yau space. So it's proportional to the difference between the number of hypers and vectors. This is supersymmetric compactification does not need thermal fluxes yet. So this term actually is localized in particular points where in the large volume limit the Euler number is chosen to be inserted, and it gives a 4-dimensional Einstein term, which precisely have some constant coefficient. The first one is 3 level, it's proportional to zeta 3, while the second one is 1 loop, and that's all. In the larger volume limit, these are the only possible terms that you can get. The unloop the three-level correction vanishes for orbitals. One can do it where one can do explicit computations, but then there is the unloop correction which remains. In that work, we studied the localization with the properties of this localization space, localized gravity kinetic terms, in which we found that it is proportional to the four-dimensional Planck length, which can be parametrically different from the 10-dimensional Planck constant by introducing a large Euler number. And this is in agreement with general arguments of localized gravity by Dvali, Capodacci, and Porati. So this correction here is going to be to transmit to give a correction, a localized correction to the Keller potential. And once you have this localized correction to the Keller potential, then one can, or if you want still at this level, you have localized kinetic terms for gravity. From these localized kinetic terms from gravity, you can now go to the next order and emit closed strings. And if a theory has local tadpoles, for instance, in the presence of D7 branes and O7 planes, then these closed strings propagate in effectively 2 dimensions, and therefore they give rise to corrections which depend logarithmically on the size of the bulk, which is transverse to the D7 branes. And they have this form, is proportional to, they are proportional to the tension on the branes, and they depend logarithmically on the size of the bulk with and here there is a localization with in the argument of the law. So the Keller potential gets this form. The first term is the volume, the 6-dimensional volume, which is a 3-level Keller potential. Then there is a one-loop constant term, psi, or 3-level in Calabi-Yau in general. And then there is this, the logarithmic corrections that comes, and it depends on the transverse volume for every source that it is away from the localized place. So I start where I choose to have to put all the Euler numbers localized, let's say, at the origin, and then these depend on the distance from the origin of the various branes. So the coefficient psi has this form, which is proportional to the Euler number times this function which is I described before, and the coefficient of the log is also proportional to psi, and it is 1 order higher. Now, the next step is to use a toy model with 3 stacks of these 7 branes, in which in every D-brane one can have a D-term potential coming from magnetic fluxes, let's say, on the branes, in which from which one can just fix the ratio of the transverse volumes of the D-branes and left over with the total volume. So once you do that, you find just a D-term potential which has this form. And this is what I write here. So at the end of the day, the result is that there is the scalar potential has 2 pieces. One comes from the gravity, let's say the F terms from in which the logarithmic corrections play a role, and then the other term comes from the D terms. So these are the analog of these 2 pieces in the Coleman-Weinberg potential that they described in field theory, and one of them contains logs. So this potential can be analyzed. It has in principle a de Sitter minimum. Essentially, there is one parameter, effective parameter, which is the relative strength between the D terms and the F term coefficient. So all these parameters depend essentially on the fluxes that you turn on the theory. And in this region, there is the Sitter minimum, which fixes the volume at this value. So just graphically, it means that's the ratio of the D over F term coefficient. If you start from starting now from negative values, the potential is run away. At some point, the potential will start develop a minimum and a maximum. Here it will turn on to, so I zoom this region. At infinity, it goes to 0. And then at some point, it passes at 0, and then it becomes negative. So that is the region where there are the Sitter vacuum. And we would like to have to see if this can be trusted in perturbation theory. So in order to have large volume and weak coupling, the tension of the brane should be positive. So it means that one should have a surplus of D branes compared to orientable planes. And then parametrically, the volume becomes large at the limit of weak coupling, where the string coupling is fixed already by the three-form fluxes that I described before. And W0 is the superpotential, constant superpotential, which is left over. And in addition, in order to be in that region, one final requirement is that one needs a negative Euler number, which means a surplus of vector multiplets in the bulk, which is here. So the next question, interesting question, is whether this potential can give inflation, can give a model of inflation. This can be studied easily, or can go to the canonical normalized field, which has this form, logarithmic form in terms of the volume. I'm also for simplicity, I redefine this parameter, which fixes the region of the Sitter minimum in this region to be positive. And then one can find the minima of the potential and express them in terms of the Lambert functions, and give explicit expressions for the Slorol parameters. So the result is that indeed one can find successful inflation models. It's possible around in which the inflation happens very near the minimum with initial conditions or the horizon exit, if you want, from the inflection point, near the inflection point. So the potential, again, in terms of this parameter, has this form. For positive x means you start from at the Sitter. Then at this value of this parameter, it becomes, you have a second minimum at 0, and then it starts going up, and then the minimum disappears. So I can write down, as I said before, the Slorol parameters, fixes the number of V-folds with putting some initial conditions, requiring that the number of V-folds is between 50 and 60, and requiring that the spectral index has the observed value. The epsilon parameter is much smaller than eta. And then at the end, one fixes the amplitude, the overall normalization of the potential. And all these conditions can be satisfied when the horizon exit is around the inflection point. So essentially, the only parameter, the spectral index fixes the only real parameter of the potential. And as I said, the phi star, the horizon exit is near the inflection point. And then it is also interesting to see that the excursion of the field is small. So that is between minimum and maximum, if you want. And therefore, the effective field theory is trustable because it's small field deflation, and you obtain a prediction for the ratio of the tensor to scalar perturbation, which is small, 10 to the minus 4. And this is the scale of inflation. Yeah, thank you. One can also study the question how stable is this minimum, which is not, it's local minimum, so it's metastable. And therefore one can find transitions from, let's say, from here to there. And it turns out that these transitions are dominated for the values of the parameter that give consistent inflation by the Hawking-Moss transition, which is a classical transition over the barrier, which gives the dominant contributions compared to the Coleman-De Lucia transition. And the reason is that the potential is very flat. However, the transition, when you compute it, you find that it takes a long time, much longer than the life of the universe. The subsequent question is that since all the parameters essentially are fixed and the minimum is quite high, it's near the inflation scale, 10 to the 12 GV. In order to be able to find, to combine this mechanism with the present situation in which one has the standard model with a cosmological constant which is almost zero, one can supplement or extend this mechanism to introduce in a hybrid way, in other words, to introduce an additional field which becomes tachyonic around the minimum of the potential, and then there is a new direction that makes the inflation stop and the field to go to and the potential to go to minimum. In other words, this is the old potential, and then there is a new direction that opens up, and it goes it lowers the minimum. This waterfall field can be realized in particular models which we have studied using charge fields from open string states on the d-branes that and could give an explicit example in which this can be done. And also this example will allow us to realize that one has sufficient discrete parameters, magnetic fluxes in particular, to put numbers to this mechanism. So we'll skip this and go to the conclusions. So I try to describe a new mechanism of module stabilization, which is based on perturbative corrections that replace the Giacchino condensation. These corrections are consistent with weak coupling in a large volume. And the main ingredient are logarithmic corrections on the size of the bulk that are due to transverse to the volume of the 7 branes due to local tadpoles that are induced by the localized gravity kinetic terms. It is interesting that these localized gravity kinetic terms arise only in 4 dimensions. In other words, if you go to 6 dimensions, then you don't find localized gravity kinetic terms, but you find R² terms. So, of course, this part is supersymmetric. With supersymmetry, this is the only way to, that's the first dimensionality in which you can have localized gravity kinetic terms. And then, of course, this will induce logarithmic corrections. And this apparently can lead to de Sitter vacuum in string theory using these quantum corrections. And it is interesting also that one can realize inflation and even hybrid inflation to lower the vacuum energy. Thank you very much.
Okay, does this work? No questions. Okay.
This looks.
Any questions?
Yes, nice talk, Ignatius. Coming back to what you said at the beginning and what we heard from Professor Waffa yesterday, how this is an explicit ultraviolet complete construction of a de Sitter space. Am I right?
Yes.
So, do you have any feeling what's the reason why the conjecture fails? I mean, what is the particular ingredient that it fails?
It's quantum corrections.
Is the quantum correction? The stringy or whatever, even in the supergravity.
But let me mention, yesterday Kumrum talked about, not this conjecture, talked about the,
I'm coming to that
it's
now.
a different one.
Yeah.
You're
But
asking him, not me, right?
yeah. At the moment, I'm asking him. So
I have other answers. But
okay. Then I can ask you then. Fine. So, in the other conjecture, what happens to the tower of states that appears here? I mean,
There is no large field here.
there's no large field.
No, there is no large field. There is small field inflation.
actually,
Okay.
this is related to the question. If you go to page 14,
Yes.
your slide. Yeah. So the orange curve will
Yeah.
give you an ADS, which in principle can have as small a lambda as possible, right?
Yes.
Okay,
Right.
that would be contradiction with what I was talking about. So indeed, if what he's claiming is true, which I have issues with, then you would have a contradiction with also my talk yesterday. That means that the scale separation would have failed here. They would say that there's a scale separation because as lambda goes to 0, he doesn't have a tower of like states.
Of course, that limit, one has to study that.
Yeah, so I have issues with these as well, but that's different.
Thank you. Thank you, Bob.
I have to see though what implies going to that limit for this parameter, for the,
But there's nothing special, it seems, right?
well, there are some fluxes which become either very large or very small. I have to check.
So you mentioned that you would start like the phi star, the horizon exit of the CMB modes will be close to an inflection point.
Yes.
I'm wondering whether is there any risk that you would maybe form primary little black holes close to the CMB emission or maybe even after? Because if you would form primary little black holes on the inflection point right before crossing phi star, potentially you could have
But
modes which re-enter the
usually
horizon.
you need something, let's say, a regularity of the potential, I think, in order to obtain primordial black holes. Here, I mean, the potential is very smooth and very shallow. So this it's very flat, the potential.
So you mean
So I don't think there is, you can make from this potential.
Any other questions?
What ensures that you get the necessary number of inputs?
Yes, it's.
How do you ensure that?
I saw you the question. No?
Yes, so
Yeah, I mean, the epsilons you determine is epsilon star. No?
solutional constraint. How does your model ensure that?
It doesn't, so it's initial condition.
Such it.
Yeah.
So in principle, you could have something that just creates a model patch as big as ours.
It can be much bigger. Yeah, if you start from the maximum, it can be.
Or it could
Yeah.
be much bigger. Okay, so no control.
Any other questions? So I have just a general question. So if you claim to have a UV complete model, can you write down explicitly which what are all the corrections in your model and why these are the only relevant correction? Everything along the lines? Because I didn't see it.
Yeah, the computations that we made was on orbifolds. Because, you know, in Calabi-Yau, to make a loop computation, it's not easy. So we took an orbifold in the...
No, it's okay to be orbifold. I don't have a problem with orbifold. So is there a concrete model where you can say you take this particular orbifold, you do this, you can show that these are the only corrections and there's nothing relevant?
Yeah, but there is a part of it that it is put by if you want, put by hand, in the sense not completely string theory, which are the three-form fluxes that stabilize the complex structure model in the dilaton.
String theory description.
I mean, you know very well. I mean, you have introduced also. I mean, you have worked on this effective superpotential that is induced by the three-form fluxes.
There are no problem with fluxes in string theory. If you have it,
but for this you need, if one needs an explicit computation, it has to go to maybe to.
So maybe we should discuss it to what extent is the UV complete theory. Any other questions? Okay, if not, let's thank Ignatius again.
Homepage. Clean stall.
Okay, so our next speaker is Dieter Lust, who's going to tell us about the Gravitino and the swampland.
All right, so thank you very much. Thanks to the organizers for inviting me. I was here 5 years ago, and I'm very happy to be back at Ioannina this year, and maybe then I will come back in 5 years from now. So the title of my talk is the Gravitino and the swampland, and since this is a SUSY conference, I found it appropriate to talk about the Gravitino. But as you will see at the end of my talk, the conclusions for, at least for low energy supersymmetry, will not be very bright. Okay, let me see how this works. In fact, this is a joint work with Niccolò Scribiori and Marco Scalisi, both working at the Max Planck Institute in Munich. Okay, so let me first show a plot about a kind of exclusion plot for low energy supersymmetry from various experiments. The details are not so important, but as you very well know, apparently low energy supersymmetry is not favored by experiments, and we know very roughly that the masses of the possible superpartners of the standard model particles must be at least as order TeV. So this plot is a little bit older, and John is not quite happy with the plot, but I think it's at least a correct statement that low energy supersymmetry was not yet found in experiment. Okay. So my question is there any fundamental reason against low energy supersymmetry? As you know, in the context of supergravity, the graviton is accompanied by a spin 3/2 particle, the gravitino. That is fundamental reason, fundamental origin supersymmetry. And therefore, as we also know, the scale of SUSY breaking is set basically by the gravitino mass. So you have this basic relation that the square of the supersymmetry breaking scale is the product of m3/2 times m Planck, and then we can also conclude that m3/2 must be at least bigger than order of milli-evolt, 10 to minus 3 evolt. So this is a crude bound, but it should hold, I think, in any model. So we can also reformulate then the question, is there any fundamental reason against the light gravitino? Or in other words, can we get information about the scale of SUSY breaking, which means this mass about the mass of the gravitino from basic properties of quantum gravity? And that's basically one question which is addressed by the so-called swampland program. As you know, the swampland program was initiated by our chair Kumrun, together also with Oguri, and is basically asking the question, which infrared consistent quantum field theories cannot be embedded into a UV complete quantum gravity, such as string theory in particular. So this is depicted in this by now famous picture by Rampalti. So the outline of my talk is I will first recall a few swampland conjectures, then I will come to the so-called ADS distance conjecture, which is a conjecture about the cosmological constant. I think this was already discussed yesterday by Kumrun. Then I will, in a way, refine this conjecture, and I will come to the gravitino-mass conjecture, and finally, I will also discuss some phenomenological consequences. So let me mention a few of the swampland conjectures. And the first is a no global symmetry conjecture. I think it is the best established and perhaps also best understood of all these conjectures. And it's saying that a theory with a finite number of states, it's also important finite number of states coupled to gravity cannot have exact global symmetries, for example. And this is also, I think, important for model building, for phenomenology. Global baryon number cannot be exactly preserved in quantum gravity. So what one can do, one can introduce, one can gauge the global symmetry introducing an abelian coupling constant, GU1, and then basically this conjecture is also saying that the global limit where you turn off this coupling constant or where you make it small is apparently obstructed. Okay. In a little bit different light, one can also formulate it saying that the effective field theory breaks down above some swampland scale lambda swampland, and if this scale lambda swampland is lower than any characteristic energy scale of the EFT, then the entire EFT belongs to the swampland. And very typically, the scenario is such, as you know, that often there's an infinite tower of states which is above this particular swampland scale. Let me see if I can turn on the middle one. Yeah, so you have a tower of states which starts at this particular energy scale, lambda swampland. And this brings me to the next conjecture, the so-called swampland distance conjecture, which is saying that at large distance directions in the parameter space of string vacua, there must be an infinite tower of states related to a typical mass scale little m. And if you formulate this a little bit more precisely, you see that this mass scale little m is exponentially related to this distance in the parameter space. So if the distance becomes large, this energy scale, if you identify with the scale of lambda swamp, becomes small, and this means a breakdown of the effective field theory for large distances. In general, and this is how it was formulated originally, delta determines on the geodesic distance in the so-called phi parameter space of backgrounds in gravity. So there is a scalar field, and if you normalize it canonically, you see that the distance basically is given is of order 1 or is of order of the field value times some particular parameter lambda. Of course, you might know how this distance conjecture is realized in a UV complete theory, so for example in string theory, and actually there are two possibilities. It can be due to Kaluza-Klein towers, or it can be also due to string states. This is emergent distance conjecture. But in many instances for compactifications, the SDC is due to the higher dimensional nature of the theory. So a new dimension is opening up. That's the famous Kaluza-Klein scale. In this scenario, in this case, the tower mass is the typical energy scale of the tower mass. It is just the inverse radius, and then the distance is given by the log of the radius. And you see immediately that the cutoff is also given by the inverse radius. And in fact, related to the Kaluza-Klein state, there's also a U1 gauge coupling, and you can read it off. It's also given by 1 over r, and you see that also the global distance conjecture is implicitly realized here. So if you take the radius to be large, also a kind of a global symmetry is popping up. So a little bit more generally, quantum gravity or string vacua are normally characterized by parameters like coupling constants and masses, and now a little bit more generally spoken, we like to know what is happening in certain infinite distance limits, where, for example, we go to small coupling limits, or also where we go to limits where certain masses or other energy scales in the theory becomes small, and in particular if these limits are obstructed in quantum gravity in the sense that they are related to lowering the cutoff and that they are accompanied by a tower of light states. Okay, so this brings me to the next conjecture. This is a conjecture about small limits of the cosmological constant in quantum gravity. I believe it was introduced yesterday in Kumrun's talk, so this is something we formulated about 3 years ago together with Kumrun and Aaron Palti. A priori, we were considering ADS vacua in quantum gravity with varying negative cosmological constant, and then the statement is indeed in the limit of a small cosmological constant, there again exists an infinite tower of states with masses that are related to the absolute value of lambda cc with some power alpha, and this power alpha should be bigger than 1/2. So you see clearly, if you go to the limit of small cosmological constant, there should be an infinite tower of light states, and then the cutoff of the theory becomes very, very small. It basically means that ADS backgrounds in a certain dimension, little d, cannot exist alone as consistent backgrounds, and this has also interesting CFT implications or descriptions, which was pointed out or discussed in several papers. Okay. In fact, there is a strong version of this conjecture, namely that the bound is saturated for alpha equal 1/2, and again we have this picture here. So here's the onset, here's lambda cc, and above we have a infinite tower of states. And as you know, this conjecture is satisfied for many known backgrounds in string M theory, for example, in the simplest case like ADS5 times S5, via the tower of KK modes. Okay. Now, let me just make a remark about the case. A priori, at the beginning, this conjecture, I think there's good evidence or very strong evidence that it holds for negative cosmological constant, but you can go on further and also assume that this conjecture is also true for positive cosmological constant, for metastable or even stable de Sitter vacua. And then in a standard cosmological scenario, indeed, this conjecture leads to a light tower of states, which is really very, 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 very light, because we know the value of the cosmological constant in natural units. It's about 10 to minus 120. So there should be indeed a tower of states of such a low mass scale. So the question is, what could be this tower of states? And if it exists, can it escape observations? So now I like to mention, I think, a very nice recent work by Montero, Kummen, and Valenzuela. I think we also mentioned this in our paper, at least briefly, about what is happening for positive cosmological constant. But in this paper, they propose indeed a so-called mesoscopic extra dimension with very light KK states, which is now exactly linked to the size of the cosmological constant. So about the length scale of this additional fifth dimension is about 1 micrometer. The associated KK masses are around millievolt, and there's an associated species scale. Now the true quantum gravity cutoff, I will come to it later, should be of the order of 10 to 10 GeV, and there are also interesting implications for sterile neutrinos. So I think this is what Kumrun discussed yesterday, and I find it an attractive scenario. Let me mention that recently with Ignatius and Louis Ankodocki, I believe that we also made an interesting observation, because now if you consider the decay rates of so-called primordial black holes, you will see that the lifetime of relevant primordial black holes gets enlarged. And if you assume that there are black holes in this mass region, which precisely fits to the length of the extra dimension, so they have a Schwarzschild radius which is of the order of the size of the extra dimension, you can show that these black holes now could serve as viable primordial dark matter candidates. So in this way, you do not only explain the cosmological constant, but you also relate it to the dark matter problem, and this could be also a very elegant scenario. But now I want to, basically, as I said already at the beginning, I want to refine the conjecture. If you perhaps do not like the idea so much that the tower of states is related to the cosmological constant, I propose now a slight variation, and this is what we call the gravitino mass conjecture, which was also at the same time basically introduced by the Spanish group around Luis Ibanez with Castellano, Font, and Herreyes. So instead of the tower mass emerging in the limit of small cosmological constant, we were investigating the alternative that in the limit of a small gravitino mass there exists an infinite tower of states with mass scale m. So basically you have a similar relation, only that the mass scale m, the tower masses, is now related to m3½ again with some parameter little n, and for n being positive you see that in the limit of small gravitino masses again this little m also becomes small. In fact, that is easy to see for supersymmetric ADS spaces. Basically, the two conjectures are completely equivalent to each other because there's a relation that m3½ square is minus lambda cc over 3, and therefore it follows that the ADC, the conjecture of the cosmological constant, is equivalent to the GMC, to the gravitino mass conjecture. Basically, they are one and the same. And also note that the case of m3½ equal to 0 is kind of special. And maybe this also addresses some particular issues in Ignatius' talk. Often the limit where you cross over from negative to positive cosmological constant, or here if you take m3½ small, is problematic because in this crossover regime you will potentially also get some problems due to light states. Okay. But on the other hand, in case of broken supersymmetry, one has that m3½ square is always bigger than minus lambda cc over 3, and then the ADC and the GMC lead to different conclusions. In particular, now the GMC allows for, say, string theories or quantum gravities, where indeed you can go to the limit lambda cc to 0, but keeping m3½ finite, and do not get a light tower of states in this particular situation. So indeed, for positive cosmological constant, the ADC and the GMC would lead to different conclusions. Okay? So why the GMC can be true, I will be maybe brief here. The first case is that the gravitino mass is related to extra dimensions, and then the GMC follows from the distance conjecture, which I have already mentioned. Or the second case, which is true in n equals 2 compactifications, or in compactification, which have the origin from n equals 2 supergravity, you can also show that the gravitino mass is directly related to U1 gauge coupling, and then you can also see that the GMC is following from the magnetic weak gravity conjecture, or even from the no global symmetry conjecture, which I have also mentioned at the beginning. So let me very briefly mention the case of extra dimensions, and I also like to say that there was already several years ago a paper by Antoniadis, Bachas, Levin, and Tomaras, which pointed out the connection of the gravitino mass and the KK scale, at least in certain instances. So maybe I do not go through all the details now. In n equal 1, there's a scalar potential, there's a superpotential, and there are kinetic terms of scalars, and we now want to consider the situation where supersymmetry is spontaneously broken. So we have also certain F terms. And then you know that the gravitino mass square is given by the square of the superpotential times the exponential of the scalar potential, which is also abbreviated often by e to the g. So this sets the scale of the gravitino mass. The scalar potential, on the other hand, or the cosmological constant has two contributions in this context. One gravitational, which is negative, and one positive contribution, Vf, which is positive, and this is just given by the F terms, which I have written here. So now we can consider a string compactification, a generic string compactification with a KK mass scale, which is 1 over V to the power 2/3 in Planck units. You can express this in terms of the scalar potential or the vacuum expectation of the superpotential. So the scalar potential has a parameter alpha here, which we assume times the log of the volume. the superpotential or the vacuum exponential value of the superpotential. We also assume that it scales with some particular parameter, with some particular exponent of the superpotential. And then we get that M3 half is 1 over V times alpha minus beta over 2. And hence we can read off this parameter n, which I introduced in the GMC at the beginning. N is 4 over 3 minus alpha minus beta. And now one has to see what, so these parameters alpha and beta are, if you wish, the microscopic parameters of a given string compactification. One has to compute or see whether the conjecture holds. So I do this really very briefly. You see, for example, that for supersymmetric ADS vacuum, n is 1/3, maybe plus some logarithmic correction. For non-supersymmetric Minkowski vacuum like Church-Schwartz, n is 4 over 3. If you include an uplift, you can argue that n is 1 over 3. In all cases, n is positive, and you see that the Gravitino conjecture is holding. Let me very briefly also mentioning that the Gravitino conjecture can be due to a U1 gauge coupling constant. This is in particular the case in n equals 2 supersymmetry. Then there is an extended supergravity multiplet which contains the graviton, the Gravitino, plus another U1 gauge boson coming from the graviphoton. And then you can see, if you analyze the prepotential, you see that M3 half is indeed given by the relevant gauge coupling constant, and therefore the limit of small gravitino mass is obstructed. Okay, so in the last 5 minutes, I like to discuss some phenomenological applications, and for that we need the cutoff scale of quantum gravity, which in this case is the so-called species scale, which I have mentioned before already. So it's m Planck over square root of n, where n is the number of species. And now by some computation you can relate indeed the species scale to M3 half. So you get this relation is given by a certain power of M3 half over m Planck with a power n over 3. And you see that M3 half is smaller than the quantum gravity cutoff only for n smaller or equal than 3. So for bigger values of this parameter n, in fact there is not even effective field theory for supersymmetry breaking. Okay, so this is the basically the starting point for any phenomenological consideration. And now I want to very briefly relate this to inflation. If there's an effective field theory inflation, one needs that the Hubble parameter must be smaller than the quantum gravity cutoff. And if you combine these two relations, you see that there's a lower limit for M3 half, in fact. Lower M3 half must be bigger than h over with the power 3 over n. So again, it depends on the n. For example, for n equals 3, M3 half must be bigger than the Hubble scale, which was also argued by different reasons some time ago by Kalosh and Linde. But you can say roughly that M3 half must be of order or even bigger than the Hubble scale, at least if the Gravitino conjecture holds. So h can be expressed in many models by the scalar to tensor ratio R in this way. So we get another relation where M3 half is bounded by the value of R. Currently we know that the experimental constraints for R is that it has to be smaller than 0.6, but maybe next TMBA experiments will reach values of R of order 10 to minus 3. So if R would be measured, we really would get in this way a lower bound on the gravitino mass, so possibly one can reach gravitino mass values of the order 10 to minus 2. So in this short plot I show you for particular choices for n, 2/3, 1, 2, and 3, how the bound of the gravitino masses depends on R. For example, for the strong GMC, which is perhaps the most favorite case, you see that the gravitino mass varies from a few evolts up to 1000 GeV. So indeed one gets interesting constraints on the gravitino mass during these arguments. So I'm basically done. Here's a brief outlook. there are various swampland conjectures motivated from strings and black holes. In fact, as I indicated at least briefly, many of them are relating and are hinting at a deeper origin. I discussed two specific swampland conjectures, the ADC, where the cosmological constant lambda cc is setting the cutoff of the theory. Of course, don't be misled, the cutoff is not it's not directly given by lambda cc, it's given by the species scale, so it is of course much higher, otherwise we would be in real trouble. And in the GMC, M3 is setting the cutoff of the theory, and this is something which is of course possible, that there is still a parametric link between M3 and lambda. So there are strong constraints from inflation on M3 which say basically the SUSY breaking scale is of order higher than the scale of inflation. And here I have again plotted the various scales which we know in nature. So in this, assuming that this conjecture is true, the gravitino mass scale is somewhere in between the scale of inflation and the cutoff scale lambda quantum gravity, where gravity becomes small. So again, showing this picture of the landscape, I'm afraid I have to conclude that low energy supersymmetry apparently belongs to the swampland, and okay, that is at least my conclusion here, and with that I'd like to thank you. Okay.
Nice talk, Dieter. In the same paper that you cited by Kalos and Lin, they proposed an alternative in which they had a second non-perturbative term, a kind of a racetrack, in which case the gravitino mass could have been arbitrarily small and decoupled from the mass of the volume modulus, and would this contradict the conjecture?
Well, if so, I think it would indeed somehow contradict the conjecture, and I think this is also along the lines of what Ignatius was just discussing before. There possibly could be microscopic models, UV complete models, not sure whether they are really completely consistent, where there are additional corrections like non-perturbative or radiative quantum corrections, where some of those relations indeed get corrections. And then, Ignatius was telling us that the de Sitter conjecture gets basically invalidated by quantum corrections. So I do not exclude the use, but on the basis of what I told you, basically taking those three-level relations between M3 and, for example, the volume of the compactification, then you are led to these conclusions which I have showed you.
In their case, of course, it was a ad hoc supergravity model, the kind of racetrack, but then it was clear that there was a decoupling between the gravitino mass.
As far as I remember, it was a model where you have two terms in a superpotential, as you say, racetrack.
And of course, one has to
see whether this can really realize the UV complete theory.
Yes, sure. Thank you.
Oh, actually, there and first there and
the constraints you derived for M3 from inflation should be valid for M3 at the time of inflation. But I guess M3 doesn't have to be the same at that time and today. If you use today's dark energy data, what kind of constraints do you get?
Well, I think indeed certain couplings will be renormalized, going from the UV scale or from the scale of inflation to the nowadays scale. So assume that we deal now with scales of order TeV and inflation takes place at 10 to 10 GeV. There could be a change indeed in M3 I don't know how big it is, so I have not really looked at the, so to say, of the renormalization group equation for M3 I assume it shouldn't be too dramatic, because we are not, admittedly in our work, we do not care about factors of 2 or 3. We are doing order of magnitude estimations at the moment here.
Thank you, Dieter. Talk. I think we already had this discussion last year in string Fino. all the evidence that we have from the LHC is that the Higgs is a fundamental particle and not a composite. Can you say anything about maybe attempts to build composite string model in string theory or otherwise?
I think it's really a different question, which I cannot answer here. Of course, there might be composite Higgs models in string theory, in particular also in the context of Rendel-Sundram scenarios where you have strong warping, and then you can argue that there is a technicolor scheme which underlies, so to say, the Higgs particle. But I think this is not really what I address here.
The evidence is that the Higgs is composite or fundamental?
I mean, here I assume basically the standard model with an elementary Higgs. But the standard model, so to say, if you look at this from this point of view, so to say, I mean, there's maybe the standard model is realized by some brane setup. So maybe a standard model quiver theory where the standard model fields are located, and these fluxes which are responsible for supersymmetry breaking or whatever are located at a different, so to say, corner of the internal Calabi-Yau space. But this is not really the issue of the talk.
I disagree with you. I think that it is the issue of the talk.
Okay, we can again discuss further, but indeed I never mentioned the Higgs particle. You might object against not having mentioned it, but it's not what enters our discussion.
Supersymmetric.
It's part of our world, and it's part of our SUSY or non-SUSY low energy effective field theory.
At some point, I missed. You mentioned you tried to obtain a lower bound for the gravitino mass.
Yes.
About 100 GeV. What was the assumptions and what were the inputs? For instance, I mean, we know that if there is, for instance, gauge mediation, gravitino mass would be...
Are you referring to these kind of relations? So it basically, it came, if you assume that we measure R of order 10 to minus 3, the scalar to linear ratio, putting it in here, you get a lower bound for the gravitino mass, which is indeed of order 100 GeV.
This excludes gauge mediation models?
Possibly, yes. Yes, I think it's against gauge mediation, because as far as I know, gauge mediation against, unlike other SUSY mediation, gauge mediation in particular favors very small gravitino mass. That's true.
Okay. If there are no more questions, let's thank Peter again. I guess we head for a coffee.
Okay.
Thank you.
Yes. So it's my pleasure to chair the second morning session and to invite Kostas Bahas for the first talk, who is going to talk about multigravity from string theory. Kostas, please.
So let me thank also the organizers for the invitation to speak in this meeting. I think, like many of you, I was here 7 years ago in the Planck 2015 meeting, and it's nice to be back again. My title has slightly changed. It was massive gravity, it became multi-gravity, but I will say a word why. And it's basically work done a couple of years ago with my then student, Ioannis Lavdas, and updated a little in a paper that will come out soon. So I think it's one of the deep questions. I mean, you heard a lot about landscape and swampland from the previous speakers, from Kumrun, Dieter, and others. There's one question that is still not very much addressed, which has to do with infrared modifications of gravity. When you look at the literature on infrared gravity, essentially it's dominated by scalar tensor theories, which are, of course, the simplest infrared modification. However, the question is whether one can have more serious or more drastic modifications. And when one actually compares the situation between spin 1 and spin 2, there is a big asymmetry. Namely, for spin 1, we have learned, first of all, we know that there is a Browtangler-Higgs mechanism. You can make it massive, there is no problem. We have also learned in string theory that you can localize spin 1 on a billion spin 1 interactions. For spin 2, both are still question marks when you come from top-down string theory. Namely, we don't know if gravity can be localized, and we don't know if it can be made massive. Now, the question actually came to front stage at the turn of the millennium, in particular following the Randall-Sundrum and Karch model. I will say a little more about this. And also the Dvali-Gabadadze-Porati bottom-up. These were bottom-up brain-world models based on thin brain assumptions, which were at the time ad hoc and still in some sense are. So there was a lot of activity 20 years ago, and then a decade after these initial papers, a very nice program was completed of basically writing down at least an effective field theory. Up to then, there was no real effective field theory, and this was really a very long history. I don't know if Claudia talked about it yesterday. I missed her talk. But it started with Fritz-Pauli, and eventually the so-called DRGT theory, Deram, Gabadadze, and Tolley, I think closed at least one chapter. Namely, they showed that there is a good ghost-free effective field theory that can describe massive spin 2 particles. And the question is this part of the landscape or of the swampland? Can this be realized in string theory? Now, if you are a phenomenologist, you can basically start by saying that simply massive gravity is essentially all but ruled out. There are all sorts of constraints, but let me simply summarize by saying that astro and cosmo data essentially tell you that the graviton mass cannot be too many orders of magnitude below the Hubble scale, 10 to the minus 32 electron volts. Now, this means that the breakdown scale of the effective theory, I will come back to this in a moment, is about 100 kilometers. So laboratory tests, you cannot compare even to this theory. And even perhaps not worse, but also bothersome, is the fact that nonlinearities, the so-called Weinstein nonlinearities, enter also very early on at galactic scales. So in some sense, one can say that laboratory tests are impossible and solar system tests require acrobatics, a lot of theoretical acrobatics. So there is very little incentive to replace Einstein's theory by massive gravity. It seems to me, maybe my viewpoint is not shared by everyone. But on the other hand, multi-gravity or bigravity is much less constrained. So here's what I mean by gravity. It's the picture on the right. So you have the usual massless graviton, and then you have a second spin 2, which is very light. You may want to call it dark graviton just to have a word for it. Of course, gravity is dark anyway, so it doesn't mean much. The whole point is that this extra massive spin 2 can have both mass uncouplings that are much less constrained by phenomenological considerations, and therefore you can basically, one can focus on this kind of theories. Now, I want to clearly distinguish this from the picture on the right, which is what we usually get in string theory and quantum gravity, large towers that condense, in which case there is a priori no effective field theory for massive spin 2s. The question on the right, the question is whether the picture on the right can be realized, where there is really a mass gap between 2 or a few spin 2s, and then a mass gap before you see extra towers. Now, actually, massive gravity and multi-gravity are not very different theoretically. One can talk about them together. So I will focus now on bigravity just to make things precise. Now, the embedding, when you try to think about the embedding bigravity in string theory, you stumble immediately on two problems that were already quite a lot discussed here. The first one is that we want to be in de Sitter. Now, in de Sitter, there is a unitarity bound called the Higuchi bound, which forces the mass to be bigger than 1 over the radius, Hubble radius. So secondly, you want to have scale separation. I mean, you want to have an effective 4-dimensional theory, be it massless or massive. And if there is no scale separation, if the Kaluza-Klein scale is always there at the Hubble radius, you never have 4-dimensional gravity. So in a sense, both these assumptions go against these two key swampland conjectures, that there are no stable de Sitter vacua. This is a conjecture now 4 years old. It was actually augmented and made more precise in later work by Kumrun and collaborators, and the no-scale separation that Dieter nicely reviewed in the previous talk. So basically, if you want to take away one thing, I would say it's the following thing. The fate of scale separation also decides whether multi-gravity is part of the landscape or not. And if scale separation can be achieved, so will effective field theories of massive, at least ADS supergravity. And in the rest of this talk, I will try to convince you about this using holography. I would also speculate that the fact that stable de Sitter solutions may not exist is not necessarily a stumbling block. Maybe it's even, it goes in the right direction, because if one only has unstable de Sitter, this removes the Higuchi bound, and therefore removes potentially the tension between these two conditions, namely that the mass has to be bigger than Hubble radius up here for de Sitter and less than the Hubble radius down here for scale separation. But if de Sitter is unstable, the uplift does not need to satisfy this bound. But this speculation, let me now move on and say a few words about how the embedding goes and why the mechanism I will describe will go through, I think, intact the day we have really scale-separated ADS vacua. So first, a couple of transparencies for those of you that haven't seen much about this subject before. What are these bigravity effective field theories? Well, there's a nice way to think about them, which was introduced in this paper of Arkani Hamed, Georgian Schwartz, which is the following. Suppose you have two universes, that each has a different metric, different coordinates, they are separate, okay? So they each has a massless graviton. Then suppose you are given a mapping that sends the coordinates from the left to the right. So phi m of x, it's an embedding of this manifold to this manifold. In some sense, you can think of this as the would-be Stuckelberg or Goldstone boson fields. And indeed, if you are given this mapping, which are 4 scalar fields from the point of view of the theory on the right, or a vector field from the point of view of the theory on the left, if you are given this, then it's very easy to write down interactions. All you have to do is pull back one metric to the other manifold like this, and then you have 2 metrics transforming like tensors over here, and you can form easily invariants. So that's basically the construction of diffo invariant local actions. It's very simple to write down like this. The real problem is that there are 4 Goldstone bosons or 4 Stuckelbergs. You only need 3 to make a massive spin 2, 3 missing polarizations. The 4th has to go away. And this is a problem that required a lot of work and which was finally solved by Claudia et al. Actually, the terms they write down have even a very elegant form as essentially mixed volume elements in the first order formalism, so generalized cosmological terms. Now, so this gives you now an effective field theory of bigravity. You can easily get massive gravity by basically decoupling one of the 2 metrics, sending the Planck mass of, say, the left universe to infinity. This fixes Gmn to be a fiducial metric, and then you are left only with a massive graviton. So the 2 are essentially the same kind of construction. Now, of course, like Einstein theory, this is an effective theory. The problem is, as I said, that it breaks down much, much earlier than Einstein gravity, much before Planck scale. And actually, in flat space, it breaks down at this intermediate scale called lambda 3. In anti-de Sitter, it breaks down at the smaller of these 2 scales. And the smaller one depends on the value of m times the radius, the Hubble radius of anti-de Sitter. Now, notice you may want to compare this with the case of massive spin 1, where an effective field theory where you have a nonlinear Higgs sector breaks down typically at m over g. You want weak coupling to have some range of validity. And of course, here we know that the Higgs particle solves the strong coupling problem or the breakdown problem. In gravity, this is tentative, but at least calculations around Minkowski space-time seem to indicate that no particles of spin lower than 2 will save the day. So if there is a UV completion, it has to include particles of spin 2 or higher, which is, of course, again, very constraining and points to something like string theory. That's all I want to say about bigravity. Now, let me move on to the mechanism. So there's a very nice way to try to understand this using holography, and here is how it works. First of all, this problem has a very interesting translation in terms of a dual conformal field theory. The 2 universes are 2 decoupled conformal field theories. Each theory has a conserved energy momentum tensor, and each theory has a central charge, which is basically the 2-point function of the energy momentum tensors. And there is a holographic dictionary that relates the mass of the dual graviton. You know, the energy momentum tensor is dual to a graviton. The mass of the graviton in Hubble units is given by the scaling dimension of the dual operator. And C is basically the radius of ADS in Planck units to the square. Now, when the energy momentum tensor is conserved, you are missing states, missing polarizations, then it has canonical scaling dimension, and it's dual to a massless graviton. So what you want to do is couple the 2 universes with a small interaction, and the whole problem is what is small, actually, as I will say in a moment. Now, you put a small coupling, then you have still a conserved total energy momentum tensor, and this is dual to a massless graviton. But then you have a second spin 2 operator, which I construct in a unique way so that it be a spin 2 primary field. It's some relative energy momentum tensor. This is not anymore conserved. So it acquires an anomalous scaling dimension, 3 plus epsilon, and this corresponds to obtaining a mass. Epsilon is roughly ml squared. Maybe there is a 3 missing here, actually. Now, you can also easily understand the Stuckelberg, because if this is not conserved, it means there is a non-vanishing operator on the right side. This is a vector, and these are the missing polarizations of the dual gravity theory. And Poratti already realized very early on, in terms of conformal, that's also a misspell, representations, that what is really happening is that there is a short representation of the conformal group. It joins with a long vector representation to make a long spin 2 representation, namely a massive graviton. Okay, if you try to think about supersymmetry, you can easily see, using just representation theory, that the whole story can go through as long as you have at most 4 supersymmetries in 4 dimensions or 2 in 5. This is just representation theory. And actually, an interesting curiosity is that in the maximal case, the Stuckelberg vector contains 4 spin 3½ fields. The long massive graviton multiplet has exactly the content of n equal 8 supergravity, and it's a question which we have been trying to address with Severin Rist, whether one can deform gauged n equal 8 supergravity to find such a theory, but we only are halfway there for the moment. So now the key question, though, is what is this interaction that will join the 2 universes? And Ilias Kiritsis, Saharoni et al., and also Vasilis Niarchos tried many years ago the first obvious thing you want to try, namely, well, take an operator from theory 1, an operator from theory 2, make sure that the product is marginal in the sense of conformal field theory, so you have an arbitrarily small coupling lambda, and then you hope that this will be a weak coupling. And indeed, if you do conformal perturbation theory, you can compute the mass of the graviton very explicitly. It's proportional to lambda squared to 1 over the central charge, the radius of ADS4, and then some numerical factors. The problem with this is a very nice story. The problem is that the effect, when you translate it in gravity, is basically one loop. It's a quantum gravity effect. And another way to say it is that the longitudinal modes of the graviton are basically very loosely bound states of anti-de Sitter. They are double trace operators. And it is very unlikely that an effective field theory can exist here, because you are essentially working with gravitons that have wave function scales of the order of anti-de Sitter. So although this points in the right direction, it has these drawbacks, and this is what we sort of think we corrected by proposing a slightly different, a somewhat different mechanism. Namely, rather than taking 2 operators, 1 from each side, just find the common global symmetry and gauge it. So you take a common global symmetry, you introduce, this is language used by so-called quiver gauge theories. You introduce a UN gauge group, you basically gauge this thing, and then you communicate between the 2 theories by having a gauge group, intermediate gauge mediation, if you want. But this is not in gravity, this is in conformal field theory. Okay. Now, you may say, well, but how can this ever work? Because remember, 4-dimensional gravity is dual to 3-dimensional CFT. In 3 dimensions, gauge couplings cannot be tuned. They always drive to infinite coupling. So whatever you do, this coupling looks very strong. Well, it turns out that the secret is the following. You need to have very few mediators, so to have a very small rank compared to the ranks of the gauge groups of these components. And as I will say in a moment, you also can play with a hidden parameter on the CFT, which is the string coupling, which has no clear interpretation in the holographic dual language. So this is basically the idea. Now then there is some technical work that I will by and large skip. I mean, we have shown in these papers that this thing works very precisely as expected by using exact type 2B string theory solutions. The only problem is that we needed a lot of supersymmetry to fully control the geometry, and with this much supersymmetry, scale separation is impossible. There is a very simple old argument by Polchinski and Silverstein that with anything more than n equal 1, scale separation doesn't work simply because there is R symmetry, which is related to a large isometry in the internal manifold. So in a sense, this is the stumbling block. If one had n equal 1 constructions with scale separation, the rest would go through. Now let me still tell you how things look on the gravity side. So there are these exact solutions. Actually, I won't tell you a lot about them. It's really one of these very beautiful set of solutions whose local form was developed by a group in UCLA. And then we completed, and also Haroni et al., the full global consistency and the duality with exact CFT. So we have full dictionaries and everything is controlled and so on. And furthermore, these are among the very rare solutions of supergravity where you really have localized branes as opposed to smeared branes. So I will skip this. Just what I want to tell you is that everything is analytic. We know the solutions explicitly. They are of the following form. The compact manifold is basically has two spheres. This is because of the large supersymmetry or the R symmetry. And these are warped over a Riemann surface, sigma. And then there are 5 branes of both kinds, and 3 branes, and the dilaton, and so on. And everything is written in terms of some harmonic functions. The rough picture is that here is a Riemann surface. This Riemann surface, which is the base manifold with these fibers, ADS4 and 2 spheres, has singularities on the boundary, which are the 5 branes. For those that know about it, these are very much similar to Polchinski-Strasser throats, and actually one of the directions to try to make this into a real n equal 1, perhaps scale-separated theory, is to convert this to real Polchinski-Strasser throats, but I won't talk about this here. It's anyway not its work underway. But essentially the picture in drawings is the following. You just pinch this Riemann surface, and this is the same as pinching the universes. You know, it's really having the same effect as what you see here. 2 universes become coupled through a very thin throat. This is a wormhole in 6 dimensions, but it's a worm brane in 10 dimensions because ADS4 is a fiber that exists everywhere. So it's a very nice and very controllable mechanism if we could reduce supersymmetry. Now, the other thing that's very nice about this problem is that if you are interested in the spin 2 KK spectrum, unlike all the rest of the KK spectrum, which is a very hard problem typically in compactifications, this only depends on geometry. It doesn't depend on fluxes, on scalars, or anything else. There is a universal operator. You can see the proof, the full proof in this paper with John Estes and an earlier version in a paper of Xaki et al. So the whole spectrum is given by this so-called Bakri-Emery operator, which has been analyzed also very nicely recently in work by De Luca et al. So all that enters into the spectrum is the metric of the compact manifold and the warping factor of the ADS4 fiber. So it's a problem that you can solve relatively easily as compared to the rest of the KK spectrum, which is much harder. Okay, now, so you can compute the spectrum, and we have done this. And let me simply, now since I started by talking with Karch-Randall syndrome, let me just touch bases with these bottom-up models, which in some sense are, in my book at least, the more reasonable models for an embedding, a controllable embedding in string theory. Well, eventually, you see what happens is that in this previous picture I showed here, the whole story happens in this narrow throat. And these very large caps of the throat are basically replaced in the Karch-Randall model by two thin end-of-the-world brains. In the language of Randall syndrome, these are both Planck brains. There is no infrared brain here, two Planck brains. In the middle, you have ADS5 deformed to be Janus. And this is also used in holography nowadays with the word wedge holography, because you have a three-dimensional CFT that reconstructs a big part of five-dimensional gravity. Although it's never really five-dimensional, it's cut off near the boundary by end-of-the-world brains. Okay, we computed the spectrum, and here is the mass of the lowest graviton that we found. So in a sense, it's very much like the double trace deformation that I showed earlier, except lambda, the marginal coupling, is replaced by this particular combination of the rank of the mediating group, and delta phi is the variation of the dilaton across the throat. This is basically what a Janus throat is doing. Dilaton varies. And when you look at this formula, you see explicitly the two factors suppressing the mixing, making this mass very small, as if the universes were decoupled. One is what I already announced, namely the rarity of mediating degrees of freedom compared to the degrees of freedom on the end-of-the-world brains. So this has to be very small, few mediators. The other rather unusual suppression comes from delta phi. When delta phi is large, you get a big suppression due to the Janus parameter, and this is a hidden parameter in the conformal field theory. Well, hidden, but not so much. Basically, where is this parameter in conformal field theory? Remember, the dilaton is the string coupling. Now, here, since we know explicitly the dual theories, they are the so-called Gayotto-Witten theories, we know that this has to do basically with the ratio of NS5 to D5 brains. It's this ratio that stabilizes the string coupling in these universe compactifications. Okay. So if you join a universe with small string coupling to one with intermediate or large string coupling, the throat mixes very little the two universes. And actually, a posteriori, this should have been so, because if you take the massive gravity limit of one central charge to infinity, then eventually what happens is that one CFT becomes effectively four-dimensional n equal 4 super Young-Mills. And when this is a free theory, of course, it cannot couple at all to the remaining brain, if you want. Now, all this, I believe, will persist with less supersymmetry. The question again is, can we construct less supersymmetric examples? The last question, and then I'm concluding, is that if this UV embedding of multigravity works, how does one see the breakdown of the effective field theory, which from the work of Claudia and collaborators we know should be there? And actually, it's reconforting that you do see it very explicitly. Actually, both limits suppressing the mixing, namely n squared over c to 0 and delta phi to infinity, in both cases, the throat grows a fifth dimension. In this case, it is simply becoming full ADS5. In this case, the throat tends to ADS4 times an interval whose size is determined by the dilaton variation. And the KK modes on this interval condense if you try to take the mass of the spin 2 to 0. So I'll say a comment about this in my last transparency, but if you need to carry away a lesson from this, I would say here it is the recipe for a UV completion of multigravity. One, find scale-separated ADS4 flux vacua dual to three-dimensional large N CFTs with less than 2 supersymmetries because of the Polchinski-Silverstein argument. Second, gauge a common global symmetry of the two CFTs with a rank much smaller than N and a large Janus variation if you can allow it. So we believe 2 clearly is a mechanism that works. The real question is whether 1 can work. If 1 is in the landscape, I think this is in landscape. If it's in swampland, this is in swampland. And before concluding, I should also mention 2 related papers. I mean, there is more. I haven't, of course, been exhausted, but the first one is Dieter with collaborators. They did something else. I mean, they just noticed that Kaluza-Klein and OpenString modes are the only spin 2 multiplets that don't have higher spins when they acquire a mass. So they said, well, okay, so open strings are maybe easy to compute. Let's calculate the couplings of the open string to the massless graviton and see how it looks compared to the DRGT theory. Now, this is a nice calculation, but I think Dieter would agree, there is no effective field theory here, and therefore, there is a whole Regge spectrum, there is never a gap. There is no particular reason to expect to find DRGT as an effective theory. In a different set of works, but these are bottom-up models by Ignatius and collaborators, they also found that you can get a gapped spectrum if you have some bottom-up model with a linear dilaton. So these are interesting models in their own right, although I believe that the gapped spectrum is there from the very start whenever you have 2 Planck Karch-Randall brains, because you start with 2 massless gravitons and a mass gap, and the 2 massless gravitons can only mix into a massless one and a massive one. Still, this is motivated by little string theory. Maybe it can be useful in some efforts to solve the scale separation problem. So thank you very much.
So thank you, Kostas, for the nice talk. So are there any questions, please?
Sorry, I didn't hear. In what two?
It's on, but it doesn't feel on. Okay, now it's on. So it seems like a good example might involve a 2D holography with ADS3. So in fact, just if you ask it in the conformal field theory in 2 dimensions, can you have just the spin 2 operators to be, just the usual energy momentum tensor plus 1 with low dimension and nothing else for a while? Can you do that, or can you find an obstruction that cannot be done? Either way, it would be interesting to
of course, it's a very good question. Somehow, I mean, it should be done, and maybe conformal bootstrap can actually even help settle the question there. Still, it's not clear to me that the step from 3 to 4 is innocuous. So
no, it's not innocuous.
But it would be nice to do. I agree.
Yes, I would suspect that you won't be able to achieve it, but I think that would be instructive to see if it's possible or not.
I fully agree.
Any
other questions?
Yeah, I wonder whether you thought at all about the phenomenology of such a model. So, I mean, obviously, there are very strong upper limits on the possible mass of a graviton. Is that something which you can easily obtain, or does it impose important constraints on your model?
You mean theoretically, or? So, as I said, I think one should distinguish here between massive gravity and bike gravity. Massive gravity, and maybe Claudia can comment much better than me, I think is on the verge of being ruled out. I mean, it's almost ruled out. the bounds seem to be in the ballpark of 10 to the minus 29 electron volts. I mean, they are definitely much above 10 to the minus 25 electron volts, and this makes the theory so hard theoretically that, yeah, but by gravity is much less constrained, so there are papers that I mentioned. For instance, you know, people have looked at the possibility of dark matter being the other spin 2, and this seems to fly. The point is that the second spin 2 is much freer to do things. It can have a much bigger mass, and it can also have weaker couplings, actually. It doesn't have universal couplings like the massless graviton. So I don't know how far it has been constrained. Maybe Claudia can comment on this, but I believe, you know, it's definitely not very constrained as far as by gravity goes. Do you agree with this?
They constrain by gravity much more than they would constrain massive gravity. Just
you mean from phenomenology?
Yes, from phenomenology. But in reality, I mean, you do want, if you want an IR modification of gravity, you do want the mass to be very small anyways, to be of order of the Hubble parameter today. And so that seems to...
Yeah.
Yeah, I mean, I'm talking about both cases. In the massive gravity case, theoretically, there's not much more problem having it to be of the order of the Hubble parameter today rather than anything else. Actually, it's quite the opposite. You would expect it to be the more natural. For bi-gravity, some of the constraints that you have, for instance, on the speed of gravitational waves, do constrain bi-gravity much more than they would constrain massive gravity, for instance.
From gravity waves, you mean?
That's right.
But why can't I turn off the coupling of the massive? I mean, the massive graviton, I can tune its coupling also, so I can make sure that a lot of what we see comes from the usual massless graviton.
Yeah, but then you need to tune it. So then you have constraints
right.
as well. Yeah.
But this is something I believe you can do theoretically much more easily, but we can discuss this over the break. Yeah.
Okay. Are there any other questions? Okay. Thank you very much, Kostas. And now we go to our next speaker, Takeo Moroi, who is going to talk about the muon G-2 anomaly and supersymmetry.
Okay, thank you very much. Thank you very much for the introduction. And I'd like to thank the organizers for inviting me to this nice conference. So, okay, my talk is more phenomenological, and I'd like to assume low-energy supersymmetry and discuss the implication of muon G-2 anomaly to the phenomenology of supersymmetric model. So probably you have already seen this figure many times before, but still, I'd like to show you this figure to start my talk. So this figure indicates the discrepancy between the standard model value and the experimental value of the muon G-2. So now the discrepancy is about 4.2 sigma. So this discrepancy is quite significant. So this may indicate the existence of some new physics beyond the standard model behind this kind of discrepancy. And in particular, I'd like to assume that this is coming from the supersymmetric contribution and consider its phenomenological implication. So yeah, that's what I'm going to speak today. So yeah, I will discuss some implications of the muon G-2 anomaly to the phenomenology of the supersymmetric model. So this is the outline. So first, I'd like to give you some brief overview about the SUSY contribution to the muon G-2. Then I'd like to pick up two different subjects on which I'm recently working on. So the first subject is about the muon G-2 anomaly and the vacuum stability in the minimal supersymmetric standard model. I'd like to explain the relation. Then the second subject is about the reconstruction of the SUSY contribution to the muon G-2 using some collider experiment, in particular international linear collider. So yeah, then I will summarize my talk. So this is the plan. Okay, so let me first give you some brief introduction about mu G minus 2 in the supersymmetric model. So, okay, so the SUSY contribution to the mu G minus 2, denoted as mu SUSY, is coming from, dominantly coming from this kind of one-loop diagrams. So, one diagram contains scalar muon, superparton of the muon and the neutralino. And another diagram contains chargino and scalar neutrino. So, in fact, there may be some two-loop contribution, changing the result by 10% or so, but still, we can just look into the detail about these kinds of one-loop diagram to understand the behavior of the SUSY contribution. And one important feature about the SUSY contribution to the mu G minus 2 is that the contribution is enhanced when the parameter called tangent beta is pretty large. So supersymmetric model is a two Higgs doublet model, and one of the Higgs, called down-type Higgs, gives mass to the leptons. So if the vacuum expectation value of this HD is small, then corresponding to large tangent beta limit, then the Yukawa coupling constant of the muon is enhanced to have the observed value of the muon mass, for example. Then something like this. So this is the muon Yukawa coupling constant in the MSSM related to the standard model value. So if the tangent beta is large, then this coupling is enhanced. Then using this kind of enhanced coupling, the SUSY contribution can be enhanced in the large tangent beta limit. And such a kind of enhancement can be well understood by looking into the one-loop diagrams by using a so-called mass insertion approximation. So in the mass insertion approximation, we treat the Higgs vacuum expectation values as perturbation. Then we can find these kinds of 5 different diagrams which are enhanced in the large tangent beta limit. And actually, they can be classified into 2 different types. So the first one, this one, is so-called Bino-Simuon diagram. This contains just Bino and Simuon, scalar muon. So in this diagram, the tangent beta enhancement is coming from here, the left-right mixing of the Simuon. So actually this mixing is enhanced by the mu parameter, the Higgsino mass parameter, as well as the tangent beta. So originally this is coming from the Yukawa interaction of the muon in the MSSM. And the other 4 different diagrams actually contain the Higgsino propagator inside the loop, as well as gaugino and scalar leptons. So behavior of these diagrams are pretty different from that of this diagram in the heavy Higgsino mass limit. But for a moment, let me assume that all the SUSY particles are almost degenerate with the mass scale which I call M SUSY. Then by adding the contributions of all these diagrams together, the SUSY contribution is estimated something like this. So it's enhanced, proportional to the tangent beta and suppressed by the SUSY scale squared. So for example, requiring 2 sigma consistency between the observed value and the theoretical prediction of the muon G minus 2, requiring the SUSY contribution of this size, then the SUSY scale is required to be smaller than about 700 GeV or so, using this estimation. So based on this kind of estimation, we can see that SUSY contribution may be large enough to explain the anomaly with the SUSY mass scale slightly heavier than the weak scale. So that's encouraging. So we can use SUSY contribution to solve the muon G minus anomaly. So based on this kind of argument, I'm interested in this kind of scenario, and I'd like to look into more about detail about this kind of possibility. Okay, so now let me go into the main subject. So the first one is the relation between the muon G minus anomaly and the vacuum stability, in particular the stability of the electric vacuum. So the starting point of this analysis is actually the absolute upper bound of the SUSY mass scale. So because SUSY contribution is coming from these kinds of one-loop diagrams, we naively think that if we push up the SUSY scale too high, then we cannot explain the muon G minus anomaly because SUSY contribution is suppressed. But actually that kind of argument is pretty too naive because there is some diagram which may not decouple even if we push up the SUSY scale, which is this one, Bino-Simuon diagram. So this diagram doesn't contain Higgsino propagator, but this vertex or the mixing is actually proportional to the Higgsino mass parameter. So actually, even if we push up the Higgsino mass, this contribution is enhanced. So we may think that the SUSY contribution may be large enough even if we push up the SUSY scale by pushing up this mu parameter, Higgs-Shino mass parameter. But actually, that kind of enhancement of the SUSY contribution is quite dangerous because actually in such a kind of limit, electric vacuum may be destabilized. The reasons in the following. So actually, this left-right mixing originally this kind of trilinear scalar interaction, Higgs, muon, muon. And after the electric symmetry breaking, this will become the left-right mixing of the muon. So if we push up the mu parameter here, actually we are enhancing this kind of term in the potential. And because this term is not bounded below, so if we enhance the coefficient of this term in the potential, the electric vacuum may be destabilized. And yeah, that kind of behavior can be understood in more detail by looking into the behavior of the scalar potential in the MSSM. So yeah, this is a part of the scalar potential in the MSSM, which contains the scalar Higgs potential, the mass term of the muons, the left and right-handed ones. Then we have the trilinear coupling coming from, which is proportional to the mu parameter. So I call the coefficient in front of this trilinear coupling T, and this will become the left-right mixing of the muon after the electric symmetry breaking, because this Higgs will get the wave there. So then, because this is the origin of the enhancement of the muon G minus 2 in the SUSY model, for example, we can tune this T parameter to have the correct value of the SUSY contribution so that it can be large enough to solve the muon G minus 2 anomaly. So the required value of the T is plotted on this plot. So here I plotted the value of T on muon mass versus Wiener mass plane. So the required value of T varies from 0.5 TeV to 5 TeV on this, for this range of the muon mass. So we can see that if the muon mass becomes heavier than, say, TeV or so, then this trilinear coupling actually becomes larger than the muon mass itself to solve the muon G minus 2 anomaly, which is dangerous because trilinear coupling may dominate over the quadratic term. So for example, in order to give you the feeling about the behavior of this potential in the large muon mass limit, I picked up, I plotted the behavior of the scalar potential for this parameter point using the value of T, about 1.1 TeV or so. Then this is the contour plot of the Higgs, the scalar potential on Higgs amplitude versus mu amplitude plane. So somewhere around here is the electric vacuum. So it's a local minimum of the potential. But actually, if we increase the amplitude of the Higgs and muon simultaneously, then we can find a region at which the potential energy becomes smaller than that of the electric vacuum. So at this point, actually, the electric vacuum is metastable. So this is local minimum, but there is some field space where potential energy is lower, somewhere around here. So in such a kind of case, this parameter point is excluded if the lifetime of the electric vacuum becomes shorter than the present cosmic time scale. So that is why the vacuum stability is important in the study of the muon G minus 2 in the MSSM. So in order to study the detail about the stability of the electric vacuum, we performed the calculation of the lifetime or the decay rate of the electric vacuum using the prescription developed by Carr and Coleman. So that's a famous one. So the calculation is done with the bounce configuration. Bounce is a field configuration connecting the false vacuum and true vacuum. Then based on the argument by Carr and Coleman, the decay rate, or actually decay rate per unit volume, is given in this form, A times exponential minus B. And this B is the action of the bounce. So actually, the calculation of the bounce or the bounce action is not so difficult once the potential is given. And the progress we made in our analysis is that we have performed the full one-loop calculation of this prefactor A to have a precise and reliable result for the decay rate. So actually, this is like the WKB approximation of the calculation of the tunneling rate in quantum mechanics. So this B is a leading part, and this A is subleading part, higher order in H bar expansion. So basically, this prefactor A is coming from the quantum fluctuation around the bounce configuration, and its calculation is pretty complicated. So we developed a formalism to calculate this kind of prefactor to take account of the quantum fluctuation and calculate the decay rate, including the effects of these fields. So first we included the effects of the quantum fluctuation of Higgs and leptons or muons, which are bounce field. And we also included the effect of the top quark as well as gauge bosons, which has relatively strong coupling to the bounce fields. And I also assumed, so we also assumed that other fields, including SUSY particles, are heavy enough so that their effects are decoupled, so we didn't consider the effects of those kind of fields. And actually, the calculation technique is pretty complicated, so I skipped the detail and let me show you the result. So this is the example of the result of our analysis. So what we did is that first we calculated the trilinear coupling T to have the input value of the SUSY contribution to A mu, so that the muon G minus anomaly is solved. Then by using the coupling constant T as well as other MSSM parameters, we calculate the bounds as well as the prefactor using the prescription we developed. Then once the decay rate is obtained, we require that the bubble nucleation rate within the Hubble horizon scale should be smaller than the inverse of the present cosmic time to have the bound. So then we get some contour. So on this plane, I mean the muon mass versus Wiener mass plane, this red line is the line corresponding to mu is equal to its maximal possible value here. And we also found that the decay rate becomes larger as we increase the muon mass in this way. So this shaded region is excluded. So yeah, we get some bound. And in particular, we are interested in the mass of the muon because it's charged particle, so it should be a very good candidate, target of a future collider experiment. So we want to know the bound on the muon mass. So we varied the Wiener mass to get the maximal possible value. So in this case, the upper bound is somewhere around here, 1.2 TeV or so. So we repeated this kind of analysis with changing the SUSY contribution to A mu and the mass relation between the left and right-handed muon. Then we get this result. So here, the horizontal axis is the ratio of the right-handed and left-handed muon mass, and this is the maximal possible value. So, for example, in this, so this green and blue line, they are the upper maximal possible value of the muon mass with changing the Wiener mass for this kind of mass ratio. So this is the 1 sigma bound, meaning that if you require the 1 sigma consistency between the theoretical and experimental value of the muon G minus 2, the lightest muon mass should be lighter than this for this mass ratio. And if you require that the SUSY contribution should be exactly equal to the discrepancy, then we get this pink curve. So anyway, we can see that the upper bound of the muon mass is maximized when the left and right-hand muon mass are almost equal. So we, from this peak value, we obtain the upper bound of muon mass for with changing this ratio, which the result is summarized here. So for example, if we require the 1 sigma or 2 sigma consistency between the theory and the experimental value, then the muon mass is required to be less than 1.4, roughly 1.4 or 1.7 TeV. That's the first message from my talk today. Okay. So okay, let me move to the second subject, which is the reconstruction of the SUSY contribution using collider experiment. So yeah, okay. So in the first part, somehow I'm considering SUSY model with relatively high muon mass, but that's not necessary. And SUSY particles may be light enough to be observed by future experiment. And if that happens, and if the properties of the SUSY particles are measured by future experiment, then we have a hope to reconstruct the SUSY contribution by using the mass and mixing parameters determined by collider experiment. And I think that kind of possibility is pretty interesting because if we can do that, then we can confirm that the muon G minus anomaly discrepancy is really coming from the SUSY contribution. So in the following, let me consider how and how well we can do such a kind of reconstruction using international linear collider. So in particular, yeah, I'd like to concentrate on the role of ILC, international linear collider, because it will provide a very clean environment to study the properties of the SUSY particles. So what we did is to adapt this sample point, parameter point of the MSSM, and perform some Monte Carlo analysis to estimate the accuracy of the measurement to reconstruct the SUSY contribution to A mu. So actually, this point is pretty optimistic because all the leptons are within the reach of IRC 500. And this maybe I should tell you that this point was recently excluded by the Atlas experiment. So now we are pushing up slightly these lepton masses to have a new estimate of the accuracy for the parameter point which is still alive. But in fact, we just have to push up the lepton masses a few GB or so to go to the point which is alive. So probably the basic strategy doesn't change so much. So let me use this point for my talk today to show you how well we can reconstruct a SUSY contribution using IRC analysis. So basically, in this point, all the the leptons and the lightest neutralino is within the reach of the IRC 500. And I assume that other superparticles, in particular chargino and the Higgsino, they are out of the reach. So in such a kind of case, actually, the SUSY contribution is dominated by this one loop diagram, again, the Simeon diagram. So what we have to do is to measure parameters on which this diagram depends. So the first thing we have to do is to measure mass parameters of Simeons and B0. And such a kind of mass parameters are obtained by the endpoint analysis. And the second parameter we need is the B0 lepton coupling here and here. And such a coupling can be understood probably by the study of the pair production process of selectron, in particular the cross-section, as studied by these people. So I will not go into detail about the measurements of these kind of parameters, and I just borrow the result of the former analysis coming from former analysis. And what I'd like to focus today is the third one. This one, the left-right mixing of the Simuon, which is the origin of the tan beta enhancement of the SUSY contribution to the G-2. Because the direct measurement of this left-right mixing parameter seems to be very difficult. So basically, this is the off-diagonal element of the mass matrix of the Simuon. And actually, for the parameter point, we assume the off-diagonal element is much, much smaller than the diagonal element. So the collider observables, actually, are pretty insensitive to this parameter. So even if we use the pair production process of Simuon, probably we cannot have a good estimate or a good measurement of this parameter. So the possibility we considered, actually, is to use the star pair production process to estimate the left-right mixing of the Simuon. Because in the parameter point of our analysis, in the heavy Higgsino mass limit, the left-right mixing of all the leptons are given in this form, the lepton mass, muon, mu parameter, and tangent beta. So once we know the left-right mixing of the star, then it can be rescaled to obtain information about the Simuon left-right mixing. So we try to use this kind of relation to get the information about the Simuon left-right mixing coming out of this parameter. And because the left-right mixing is proportional to the lepton mass, the star left-right mixing is bigger, so it's easier to measure at the collider experiment. And indeed, it can be obtained once we observe the star pair production process, for example, because this left-right mixing is related to the mass eigenvalues and the mixing parameter like this. So once we measure the mass eigenvalues of two stars as well as the mixing parameter, then we can know the left-right mixing, using those kinds of measurements. So yes, the story is pretty complicated, but what I'd like to do is to understand how we can determine this parameter, star left-right mixing, to get the information about the Simuon left-right mixing, which is necessary to reconstruct the SUSY contribution. So in the following, what I do in the following is to study the star pair production process to get the information about this one, left-right mixing of the star. So we performed some Monte Carlo analysis to estimate the accuracy of this, to get the accuracy for the measurements of the mass and mixing parameters. So we are interested in the star pair production process. So among the data sample obtained by Monte Carlo analysis, we first picked up the event which contains two hadronic tau candidates with opposite charges. So two taus coming from these two pair-produced taus. And in order to avoid the SUSY background coming from the pair production of scalar electron and scalar muon, we require that the tau to decay hadronically. So we require the event to have no isolated leptons to avoid such a kind of background. Then we applying additional cuts, we found that the background level can be reduced and it can be made subdominant, so that we have a hope to study the pair production process at the International Linear Collider. So anyway, okay. Then we are interested in, or we try to determine the mass and mixing parameters. And information about these kinds of parameters can be obtained by using the cross-section and the endpoint information. So first of all, the star pair production cross-section is dependent on the star mass and the mixing parameter. So this is the production cross-section of the heavier stars. So of course, the cross-section should depend on the star mass like this. And importantly, at the ILC, the polarized initial state beam is available. So because if we use the polarized beam, then the cross-section becomes very sensitive to the mixing parameter too, like this. So for opposite polarization combination, the cross-section depends on the mixing parameter like this or this. And in addition, we can also use the endpoint information. So we can measure the energy of the tau jet coming from the tau decay. And actually, that kind of energy of the tau is bounded from above like this. So the upper end point is sensitive to the mass of the star, parent star like this. So if we can identify the position of the end point, then we can also get the information about the star mass, assuming that the lightest neutrino mass is well known by other measurement. So this is the example of the event distribution, I mean the distribution of the energy of the leading tau jet for this polarization combination. So this is the blow up, okay, these are the blow up of the star 1 and the star 2 endpoint region, energy region. So there are lots of histograms, but basically this red one is the contribution coming, histogram coming from the star 1 pair production. And this dotted red one, this one is the star 2 pair production coming from the star 2 pair production. And actually this is the star 1, star 2, and others background. So we can see that the signal cross-section or signal contribution is above the background or comparable to the background, so that we have a hope to study the star pair production process. And we can see from this kind of distribution that here and here, there is a kink in the distribution which corresponds to the endpoints. So using some fitting function, we identify the position of these endpoints. And the result is summarized in this table. So the central value is pretty close to the true value, and the error bar is pretty small, and the endpoint can be determined with the accuracy of the percent level. And in addition, the total number of events should depend on the cross-section. So we chose this region as we choose this energy region to get the information about the cross-section. And for opposite helicity polarization combination of the initial state beam, we can get a similar result. So basically, what I said so far is that we can have the information about the endpoint as well as the information about the cross-section. So once we get those kinds of informations, we can combine the information of those to perform the likelihood analysis with defining the chi-square variable using the cross-section and endpoint. So and after minimizing the likelihood function, I mean chi-square, and estimating the error, the accuracy of the determination of parameter is summarized in this table. So this is basically the result of the accuracy of the determination of the model parameters, mass and mixing parameter. And then by using these kinds of parameter, we can determine the left-right mixing of star, which can be converted to the left-right mixing of the muon like this. Then by combining also using the expected accuracy of the Semion mass and neutrino mass parameter obtained by former analysis, finally we get some estimation about the reconstruction of the SUSY contribution to G-2, which is this value. So central value, okay, so for some measurement, we use the central value as the input. So central value here is not so important, but the important one is this error bar. So we expect that so this error bar seems to be pretty small. So this is 10 to minus 0.4 units of 10 to minus 10. So this is actually much smaller than current experimental uncertainty. So, and also I should tell you that this error only contains the uncertainty coming from the ILC observable. So this doesn't contain, for example, the systematic error in the theoretical calculation of the SUSY contribution. But anyway, this result seems to be quite encouraging because ILC is really helpful to reconstruct the SUSY contribution pretty accurately. So this is the second message from my talk today. Okay, so I think I can summarize my talk now. So what I discussed today is the implication of the SUSY contribution, SUSY interpretation, muon G-2 anomaly to the SUSY phenomenology. And if SUSY is the solution to the muon G-2 anomaly, we can expect very rich phenomenology. And I picked up two different subjects. And first, I discussed about the stability of the electric vacuum in the light of the muon G-2 anomaly in the MSSM. And if the SUSY contribution is really behind the anomaly, then Semion mass is required to be smaller than this value, 1.4 to 1.7 TeV, assuming 1 to 2 sigma consistency between theory and experimental values. Then second, if SUSY particle can be found in future collider, then we can have a hope to reconstruct the SUSY contribution, which seems to be very interesting. And for such a kind of purpose, ILC will be very helpful. Okay, so thank you very much for your attention.
Okay, thank you very much. Are there any questions, please?
So for the question of vacuum stability, I think that what you did is just to concentrate on the Semion sector, right? So I was wondering, that plot, in that plot, I don't know if in this or the other plot you show that tangent beta 10. I was wondering what is the value of mu that is associated with...
it depends on tangent beta, but it's above 10 TeV or so to have the correct value of muon G-3.
So it should be much larger.
Much heavier.
Much heavier.
Than this one.
And the second question I have is related to something you said. The scenario you had was recently discovered by Atlas.
Oh, you mean?
So that means that the LHC has also the capability before the LHC is constructed.
Yeah. For the discovery, LHC may help, but LHC may help, but in order to reconstruct the muon G-2 SUSY contribution, we need very precise measurement of the mass and mixing parameter. Then for which probably ILC is better, much better.
Much better.
I
agree. But the problem that ILC, I don't know how.
Actually, we didn't do any analysis for LHC, but ILC will get this kind of very, very precise measurements of mass and mixing parameters, which seems to be really impressive.
I agree. And the second question is, will your analysis change too much?
I don't think so, because we just have to push up the mass 5 GeV or so. So it shouldn't change that much.
Let me finish my question. If instead of having the ILC, you have a circular collider, then if instead of having the ILC, you have a circular collider, so can you do anything? Then,
probably, result doesn't change so much, but for circular collider, I'm not sure we can use the polarized beam. Polarized beam seems to be pretty important for this kind of measurements, so ILC may be better in that sense.
Thank you. Okay, please.
This analysis that you performed here is based on tree-level calculations?
You mean this one?
Cross-sections, yes, the second part.
Tree-level, but actually we included the initial state radiation and those kind of things.
Okay, I'm more worried about all the contributions for the production processes, for example, that really come in from the SUSY loops, and when also then the parameters may mix and have. Okay. I would guess that this induces some other uncertainty that is not accounted for.
Oh, you mean cross-section? Yeah, maybe one loop correction is not included, so yeah, we have to worry about that kind of uncertainty.
And do I understand it right that you do not have to determine 10 beta because you only determine the product of 10 beta and
That's right,
U?
yes.
Okay, okay. So you don't know individually. Okay. And of course, you also assume that only one diagram contributes.
Yeah, that's right. Yeah, so that kind of theoretical uncertainties are not included in this analysis. Okay. Yeah, thank you very much.
Okay, thanks.
Okay. Is
Yeah.
there another question, please? Yeah. There. Yes, okay.
Yeah, sorry, just a follow-up to what I think was being said. So because your bounds and your analysis of vacuum stability is based on getting Gmu minus 2 from that particular diagram, but you could get it for lower values of mu from the other some of the other diagrams that you showed, and in that case, vacuum stability will not be a problem.
Yeah, our purpose is to get the maximal possible values. Then probably we have to push up the mu parameter. So yeah, if you want to use other diagrams containing Higgs-Zenos, the mu cannot be that large. Then probably the mass scale of whole superparticles gets reduced.
Yeah, so that's what I'm saying. That is in that particular case that your vacuum stability issues are relevant, but you could bypass them by using other diagrams.
Yeah.
Okay, there's another question here, please.
So this is just a follow-up to what Carlos was asking, where I guess he didn't insist on asking the question, which is the following. Since we're not going to have an ILC or any Higgs factory for at least 15 years, we will have LHC for the next 15 years. What do you expect to be in 15 years from now, the LHC limits on SMUON masses, which would then inform about whether this physics can be done at eventually an ILC or whatever plays that role? Under the assumption that LHC does not discover the SMUON in the next 15 years, because of course if it discovers it, then
yeah, actually, I should tell you that we picked up this point because the degeneracy between the SMUON and neutrino is pretty close. So in this kind of region, actually, LHC cannot do good job so much. So actually, this is a very, very special point. So I'm not sure if this kind of point is really excluded by the in the next 15 years. Maybe, but nobody knows. Probably they will because experimenters are very powerful.
So you would claim that no matter what happens with LHC, there will always be a window.
Yeah, that's we can expect that, I think.
Okay, since we are running late, thank you very much.
Thank you very much.
Second one, yeah, thank you. Perfect.
This one, huh?
Yeah.
And I invite
Which is the
our
pointer?
next speaker, should be Sarkar. And we talk about challenges to the cosmological standard model. Please.
Thank you. Well, I was last in this auditorium 7 years ago. It was Planck 2015. And we had a special day to celebrate the career of our colleague Kyriakos Tamvakis, who then retired. And on that occasion, I spoke about our work at the time, that the supernova data were not, in fact, indicating cosmic acceleration as robustly as people seem to think. So I'm very happy that 7 years later, the organizers have invited me back, George, Yanis, Sakis, etc., to talk about some further developments that have happened since then. The bottom line being that the present standard model of cosmology of the late universe, dominated by lambda in de Sitter space, is really not fit for purpose. And I hope to convincing you of that with some very simple observational arguments, nothing very technically complicated. And my philosophy is that of Dennis Sharma, who introduced me to cosmology, who was of the opinion that before we ask the big why questions, we should really first address the how questions. In other words, describe the universe as it actually is, rather than impose a model on it that was constructed actually 100 years ago. So the issue in cosmology, as different from all other physical sciences, is that we are on some particular world line and we can only see back along our past light cone. We can't move somewhere else in the universe and ask what would you see from there. So George Ellis, a relativist, pointed out quite some years ago that this meant a certain limitations to how far we can go in reconstructing our understanding of the universe. And we have to rely on a philosophical principle in cosmology, which is called the cosmological principle, namely that our position is not special, so we can extrapolate from what we observe to what other observers might observe. And what this means is that we have a limitation in the construction of the model. And in fact, Ellis and Stroger gave a manifesto, a prescription for how to start with observations and build up a cosmological model. Unfortunately, that has not been followed. Rather, we follow the cosmological principle, and that says that the fundamental symmetries of isotropy and homogeneity of the universe operate on the large scales after you average over small scale structure. So this is actually a Hubble volume simulation of a lambda CDM universe, and you see this cosmic web of galaxies, clusters, superclusters, and so on. But the idea is that statistically it is isotropic and homogeneous. And you know how we proceed to infer that we are right now in a de Sitter phase. You can approximate this by perturbed Friedmann-Lemaitre-Robertson-Walker metric. You can then construct from that the Ricci tensor, the Ricci scalar, and relate it to the energy momentum tensor in Einstein's equation. And that gives you the 10 equations then collapse into one, the Friedmann-Lemaitre equation. And that then allows you to write the entire model very simply as a sum rule, the sum of the fractional contributions of matter, curvature, and the cosmological constant, because these are the only three terms that you allow in the equation. If you were to write a fourth term here, that would be one more term here, and that would no longer give you this simple sum rule. However, because this lambda, in addition to the contribution from the left-hand side, which just comes from the coordinate invariance, general coordinate invariance, you also have the contribution from the quantum fields, the super-normalizable term in the Lagrangian. And those add up together to give you the net lambda, capital lambda, that enters into this Friedmann-Lemaitre equation. And it is that which you then infer from this sum rule. You do not measure lambda directly. What you measure, for example, since lambda has an equation of state where the pressure is the negative of the energy density, you would expect acceleration, and the supernova Hubble diagram is, then gives you a measure of omega matter minus omega lambda, which famously came out in this combination to be negative. You also measure the position of the first peak in the microwave background. That gives you the sound of the size of the sound horizon at the last scattering surface. And that tells you that the curvature is very close to zero. And you also measure baryonic acoustic oscillations, you measure the rich abundance of rich clusters and all that. That tells you omega matter is 0.3. So on this familiar diagram, you have a diagonal constraint from the CMB, you have a orthogonal diagonal constraint from the supernovae, and you have this omega matter picking out this point, and this has therefore become our standard model. The point being that lambda has to get a value of order h0 square. That is the natural scale, because that's the only dimensionful parameter in the model. and h naught is the present day rate of expansion of the universe. It is not a constant, it is not a fundamental as far as I know, and yet it is that which necessarily dictates the size of lambda. Now this is what we actually infer from the data, from the luminosity distance, angular diameter distance, whatever we measure. But we choose to interpret it as energy density by writing it out in Planck units, multiplying it by Planck mass square, and then we get something which is the geometric mean of the Hubble parameter, which is 10 to the minus 42 GeV, as we heard earlier, and the Planck scale, which is 10 to the 18, so you get something of order the present day temperature of the CMB, not by accident. And so we have come to this standard model, which is now depicted as so, accelerating driven by lambda, and we are told that lambda makes up 70% of the universe. And I remind you again, I emphasize that we are interpreting this as the energy of the vacuum. There is no actual measurement that has determined that it has negative pressure, that it is indeed due to the vacuum. And the reason why this is so popular is because it's a simple model. It has just a few parameters, if you consider lambda to be just another fitting parameter, as the astronomers do. And they are not so bothered that it completely lacks a physical foundation. And so all the effort, cosmologic advances have been made in building better instruments on the ground, in the sky, but all they're doing is trying to measure the parameters with higher precision, not asking whether those initial assumptions that you made to construct the model are in fact correct. And this is in contrast with the situation in particle physics, where we have actually examined whether the arbitrary construction of the standard model is correct by testing its relative corrections at left, for example. We know that the gauge group is what it is, even if it is arbitrary. The particle content is what it is, even if it is arbitrary. Now, people often say at this point, hasn't Planck shown that we live in a lambda CDM universe? Well, here is the Planck data, here is the power spectrum, here is the table of parameters. Now I ask you, where is the entry for lambda? You have something for omega baryons, for cold dark matter, the optical depth to last scattering, the amplitude of the perturbation spectrum, its spectral index, etc., etc. There's nothing for lambda because you don't actually measure lambda from the microwave background. You infer it using that sum rule. You measure these two other quantities. So until we actually see something called the late integrated Sachs-Wolf effect, which is a correlation between structure and the microwave background induced by the effect of lambda within a redshift of 1, and that will require measuring about 6 times more redshifts than we have at present. Now, I just want to take a minute to point out the cultural difference with particle physics, since most of you are from that community. The standard model works pretty well, but we look at all the parameters here continuously, and we just heard a talk about G minus 2. The anomaly is 4.2 sigma. You might dispute, you might do a better lattice calculation to work out what it actually should be, and so on. But the point is that it is paid attention. It is not dismissed or swept under the carpet, and I find this to be a curious cultural gap. So it has got to the point where all the string theorists here have accepted that we live in a de Sitter vacuum and are trying to understand what implications that has for fundamental physics. But we should really ask if that is indeed true. Pardon? Okay. So I invite you to look at the actual data because perhaps this is something you're less familiar with. Now, we know what the FLRW metric looks like. This is what the actual universe looks like today. This is a map of the universe out to about 800 megaparsecs made from the Sloan Digital Sky Survey. You see the cosmic wave of galaxies. This is the inner 200 megaparsecs blown up here, a mapping program undertaken by Brent Tully and collaborators. We are at the center here. We are moving towards Shapley supercluster. I'll show you in a second. These thin lines are velocities. We belong to this Virgo cluster here. It does not look very much to me like a FRW universe. So the question is, are we justified in approximating it as exactly homogeneous? and to assume that we are a typical observer. I mean, might it not make a difference if you are in a low-density region or a high-density region? We all know that general relativity, you respond to the local matter density. Does it matter which direction you look at? Would it not make a difference if I looked along this direction rather than along matter? These questions are not asked, or certainly not answered in astronomy papers, because the assumption is that the universe is isotropic and homogeneous. So we hear about the Hubble tension. H sub 0, it's a quantity that characterizes the FLRW universe, okay? This model, not the real universe. In the real universe, the Hubble parameter changes by 10% across the sky. You have to make a lot of corrections to reduce that uncertainty, but all those corrections are model dependent. Now let's go back to basics. So Dennis Sharma, who I mentioned earlier, in 1967, he pointed out that the microwave background could not be isotropic because we are not in the frame of reference in which the expansion is Hubble expansion. That is to say, all galaxies go away at a rate proportional to the distance, because there are peculiar velocities. So we are in a dance with Andromeda galaxy. Andromeda is actually coming towards us, and therefore the peculiar velocities, which are of order a few hundred kilometers per second, should induce a dipole with a temperature varying as so. This was calculated by Peebles and Wilkinson, just a special relativistic effect, which we set as an exercise for our students. And this means that we are moving at about a thousandth of the speed of light with respect to the frame in which the CMB is truly isotropic. So what we do is we boost to that frame, but in fact the motion is a bit more complicated because we are actually going around our galaxy in the opposite direction to this hotspot. So the two velocities add up, and our net motion is more like 620 kilometers per second, and that is in a certain direction. Why are we moving? If it's a homogeneous universe, we shouldn't be going anywhere. That's because there is some large clump of matter, presumably, that is pulling us, because we know the universe is inhomogeneous on small scales. But the expectation is that we become smooth when averaged over scales larger than something like 100, 200 megaparsecs. You can quantify that statement in terms of the power spectrum of fluctuations and the variance in a top hat box of that size. Basically, all cosmological data is corrected by transforming to this putative idealized frame in which the distribution of matter and the radiation are isotropic. Okay? We don't actually live in that frame, but we believe that it exists. Does it actually exist? So just a reminder that a wise person once wrote that the reason why we do all this cosmological principle stuff is not because we really think it's correct, but when you have no data, you've got to start with something. And that was certainly the case 100 years ago when Friedman wrote down his equation, because there was no data then. We didn't even know we lived in a galaxy. But he did say that if the data will not fit into the framework, we'll have to reevaluate the situation, and this does not appear to have been done. Even though a test to do this was proposed in '84 by George Ellis and John Baldwin, radio astronomer from Cambridge. In fact, at the Orthodox Academy of Crete in Kolimbari, where many of us have been, they say the standard interpretation of the dipole in the CMB is due to our peculiar velocity in a homogeneous isotropic universe, then number counts of radio sources must show a similar anisotropy, because radio sources had then been discovered and they were known to be at cosmological distances. And if the standards of rest determined by the microwave background and the number counts were to be in disagreement, then they gave three options. Either the microwave background is not cosmological, today we would not accept that, or the radio sources are not at cosmological distances, today we know they're redshifts. And the third possibility is that you have to abandon the Friedman-Lemaitre-Robertson-Walker model. Now, if you look at a good textbook, this one is by Jim Peebles, he shows this picture of about 35,000 radio sources mapped from Green Bank, West Virginia. And he says this shows that the universe is isotropic. In fact, that statement is not true. By the way, you might wonder what that line is. That's actually the Milky Way. That's a local clustering thing. And these are regions that you can't see from a ground-based telescope. The point is that this distribution cannot be isotropic if the CMB is anisotropic, because these are at cosmological distances. But you can't see that anisotropy with just 35,000 sources. You need a lot more. And this was outlined by Ellis and Baldwin. They appealed to the effect called aberration, which was discovered by Bradley 250 years before special relativity, but is in fact special relativity, the formula that says that anything that you look at actually looks like it is displaced in the direction of our motion for a moving observer. And then you have to also take into account that in the moving frame, if these sources, for example, have a power law spectrum, you are sampling a different part of the spectrum in your boosted frame. And the number density of these objects as a function of their flux is also usually a power law. So you have to take into account these two exponents of the power law spectrum and the power law flux distribution. And from that, you infer that you should see a dipole in the distribution, which is also proportional to V over C cos theta, as before, but there is a term here that includes this x and alpha, and this can be like, factor of 4 times bigger. So you see a bigger dipole anisotropy in the distribution of distant objects. What do you need to do this test? Well, you need a lot of objects at cosmological distance, so at redshift of 1 or more. You need a lot of them to beat down shot noise. And you need to exclude the possibility that accidentally one of these objects is close to us in some direction, in which case it will obviously give you a so-called clustering dipole. We first did this test with a catalog which was made of radio sources at Socorro, New Mexico, the VLA, very large array, and combined that with the catalog from Australia, from Molonglo. That was not quite 1 million sources. We didn't really know the redshifts of these objects, so we could only claim that the clustering redshift is negligible. We couldn't actually prove it. We had more galaxies from a satellite called WISE, which had surveyed the sky for many years. But here the redshift is quite shallow. It's about 0.14, not deep enough that the clustering redshift is entirely negligible. But I'll show you our most recent work with quasars, 1.4 million of them from the same survey, which are definitely at high redshift because we know their redshifts. And here we can say that the clustering redshift is definitely, clustering dipole is negligible. This work is done with Nathan Seacrest, who is an astronomer at the Naval Observatory in Washington, Mohammad Ramiz, who is at the Tata Institute in Bombay, Sebastian von Hausegger is at Oxford, Roya Mohai and Jacques Collin are at the Institute for Astrophysics in Paris. This is just to quickly show you that if you do that radio test with the radio sources, each of those points is a radio source, and we have to do a fair bit of manipulation to match the two catalogs. They're made at different frequencies. We removed nearby objects like the galactic plane, which you saw in the Peebles picture. And we also remove nearby sources, which are seen by a satellite called 2MRS, which is infrared satellite. And we see the characteristic cos theta pattern. We see the hot spot and the cold spot for the dipole. There is only one problem. Although the direction is the same as that of the CMB, the amplitude, you can tell here, is a lot higher. The velocity that we infer is much higher than what we got from the CMB. It does not agree. Now, this was actually discovered by someone called Ashok Singhal 10 years ago. But the problem is that the number of sources is not enough, and the redshifts are not known. And then if you do Monte Carlo simulations to ask how often would we get this pattern just by pure chance, the answer is 2.8 sigma. It sounds impressive if I quote it as a percentage, but actually it's not very impressive. You would not get out of bed for 2.8 sigma in some laboratory experiment, right? But now we have some new news, which is here is the cat-wise quasar catalog. These are quasars which are seen in the mid-infrared at micrometer wavelengths. So what you're really looking at is the dust ring which is surrounding the central black hole, not the jets of plasma shooting out which make the radio sources. And we see them in several bands, and each of these points here is a quasar, but now there are 1.4 million of them. And the real advance is that a subset of these were mapped by the Sloan Digital Sky Survey, which measured their redshifts with high precision. So we know that the redshift distribution is peaked at just above 1, and 99% of them are at distances further than where they could possibly give a clustering component. So that's a big, it gives us confidence in our result. Again, when you smooth it, we see the dipole, the hot spot and the cold spot. Here are the distributions of the flux the indices for the flux dependence on frequency and the number distribution. There are 1.4 million objects in these. So what we can do is you can sample from them and generate mock skies, Monte Carlo simulations, of what the sky should look like if the standard model of cosmology is correct, and ask if we do see something consistent. First, I wanted to show you that we do various checks and balances, just like you do for data at Atlas or CMS or wherever. You have to make sure that you are actually looking at quasars and not at spiral galaxies or stars, which are far more numerous. We have to make a cut on the magnitude to make sure that our sky is complete. We are not selecting with regard to flux. By the way, this confusing nomenclature is because astronomers put a minus sign in front of their magnitude. In other words, the larger the number, the fainter the object. We have to mask the sky to make sure that the source identification efficiency is constant and all that, right? So these are all details I can happy to discuss with you later. The bottom line is this. We see a dipole. This is the triangle. It is consistent with the CMB direction, which is the star. But if we look at the distribution of our Monte Carlo simulations, we did 10 million simulations. This is the distribution around the expected theoretical value according to Baldwin and Ellis. This is the value we find. You can see it's well out in the tail. In fact, the formal discrepancy is 4.9 sigma, because only 5 of those 10 million simulations got up to here by accident and were within that cone. So this is almost at the level where you would actually start paying attention. Incidentally, all our data and code is public. We believe in doing open science. Please have a look and check for yourself that this is the result. More recently, in a paper that we just put out a couple of weeks ago on the archive, we have gone back to the NVSS catalog, done a huge amount of work on cleaning it up, masking it. This is the, for those who know radio astronomy, this is the 408 megahertz Haslam map, which is used to make sure that we are not confusing these sources with things which are nearby. And here is again the WISE map of quasars. We have been able to increase the number to 1.6 million. And we find that the dipoles in this and this are consistent with each other, and their vector mean is a value which is about 2.5 times what you expect from the CMB, in other words, from the standard model of cosmology. And now we actually adopt an even more generous definition of our p-value. We don't care about what direction the dipole is pointing in. We don't require it to be consistent with the CMB. And this is the offset angle, and this is the dipole amplitude. The central point here is the expectation from the standard model, and these are the ones which reflect what we see in these two catalogs. And because these catalogs are consistent with each other, we can combine the p-values. And by the way, they have no sources in common. They are two independent experiments, like Atlas and CMS, if you like. And so when you combine them, we find that we can now reject the standard model at 5.2 sigma, which is just psychological 5 sigma. I mean, there's nothing special about 5 sigma, but to most of us, that's the kind of watershed. I want to take a few more minutes to tell you that this actually is interesting, particularly because for a long time, people have been trying to trace at what point the universe actually becomes homogeneous and we converge to this CMB frame, which according to the standard model is supposed to follow this purple curve with the associated variance that you see as these bands. The actual data don't seem to follow that curve. There seems to be a constant bulk flow extending out to hundreds of megaparsecs. But the errors are very large. You know, this is interesting but not, compelling, so people have not paid it attention. Incidentally, if you look at that simulation that I showed you in the first slide and ask how often would you find a neighborhood of the universe in a lambda CDM model which looks like that, this could be a fluctuation, but that fluctuation would have to be pretty rare. Less than 1% of Milky Way-like observers like us have a neighborhood like that in the simulation. In other words, we are definitely not Copernican observers. I mean, a lot of people raise this Copernican thing. The point is that according to lambda CDM itself, we are not Copernican observers. And that has implications. For example, if you are in a bulk flow, such as is indicated here by this yellow patch, then according to work that has been done by Christos Sagas and collaborators at Thessaloniki, such an observer is what's called a tilted observer, and this was already studied some years ago again by George Ellis and collaborators. They would actually infer different quantities from their observations than a Copernican observer. So for example, if this flow is converging or diverging, then according to the sign of that, the deceleration parameter that such an observer would deduce from the data would be the usual quantity minus this quantity which comes from the Raychaudhuri equation, which tells you what the congruence of null geodesics is. And what this means that a co-moving observer might measure a negative deceleration parameter when the actual deceleration parameter is positive, or vice versa, because we are not typical observers. This is the main point I want to make. Now, I discussed with Christos what the amplitude of this thing would be, and that's hard to determine. We don't know that much about the bulk flow. But a clear prediction is that we should therefore see accelerated expansion only along our direction of motion. Is that the case? Well, yes. When we look at the supernova data, we looked at the large catalog of supernovae called the joint light curve analysis, and we do a cosmographic expansion. In other words, we don't adopt a model, we just do a Taylor expansion, thank you, in terms of the Hubble parameter and the deceleration parameter, and then there is something called the jerk parameter and so on. And we allow the monopole and a dipole to both be present in this deceleration parameter. So this is like a fudge. We are not really analyzing in a consistent anisotropic universe. We are just letting the inferred Q naught to have a monopole and a dipole just to keep the number of parameters small, because there are only of order 1,000 supernovae. There's not that much data. You don't want to inflate your number of parameters. But see what we find. When we let loose a maximum likelihood estimator, it says that the acceleration that we see from supernovae is mainly a dipole. This scale is much compressed compared to this one. So it's actually the dipole is 50 times bigger than the monopole. In fact, the monopole is consistent with 0 at 1.4 sigma, whereas the standard lambda CDM model is up here with no dipole and a large monopole. We exclude it at 3.9 sigma. And as you see here, if I plot the acceleration on the sky, the acceleration is in the direction of the CMB dipole. In the opposite direction, if people had looked, they would have seen deceleration. And you might ask, where did they look? Well, actually, most of the supernovae that the Supernova Cosmology Project and the HiZ Supernova Search team looked at were in this direction. Why? Because that's where the telescopes see from the ground. So this suggests to us that cosmic acceleration is an artifact of our being located in a deep bulk flow and not being sort of idealized Copernican observers who see the universe as isotropic, etc. And it is not due to lambda, because lambda cannot give you an isotropic acceleration. So let me come to my summary. I remind you that the standard model of cosmology that you use today actually goes back 100 years to Friedman's 1922 paper. And the assumptions that it was based on then, for lack of any data, have not been tested even after you get the data. Of course, the data came very recently. The radio catalog came only in this century. It was 2001. And the quasar data we only got last year. So we should really now use data to test this model and not simply assume those things. And what we have done is to do the Baldwin-Ellis test, and we find that the real universe fails it. And this is a very serious challenge to this underlying metric assumption. And of course, as a side product almost, it means that all this standard procedure of boosting to the cosmic rest frame and making all these corrections for peculiar velocities, that is not justified. So the inference of lambda, the inference of the standard cosmological model, all the precision cosmology that we hear about is not justified in terms of this failure at over 5 sigma of the standard assumption. In fact, we see that the measurements in the heliocentric rest frame, where you make observations, do see a strong dipole in the recession velocities, in the Hubble parameter that is, and also in the acceleration. So cosmic acceleration may not mean that we live in de Sitter space. It might just be an artifact of our local neighborhood. Local, I mean extending several hundred megaparsecs. So what do we do now? We are going to get a lot of data from future missions. Looking forward to that. In fact, I'm part of the Rubin telescope, so-called legacy survey of space and time that's going to start taking data next year. We'll have millions, literally millions of galaxies, quasars, up to a redshift of about 0.8. And there is also the dark energy spectroscopic instrument on the Mile telescope in Kitt Peak. That's already got, I'm told, 5 million spectroscopic redshifts. So there's a lot of data coming. We must construct a cosmological model from data rather than from philosophical principles, and following the manifesto that was spelled out by these authors many years ago, which they called the cosmological fitting problem. Thank you.
Thank you very much, Sudhir, for the very interesting talk. Are there any questions, please?
Actually, it seems to me you confirmed the standard cosmological model.
And how so?
Because the two purely kinematic dipoles you measured actually agree. Now the CMB is not just a kinematic dipole, right? It's the sum of a kinematic dipole plus an intrinsic CMB anisotropy dipole. And you can only measure the sum.
Correct.
And the intrinsic dipole is pretty poorly predicted because of the very large cosmic variance, right?
The kinematic dipole is not measurable, but because it is expected to be of order 10 to the minus 5, like all the other higher multipoles,
right, but
it would be 100 times smaller than the kinematic one. That is the general belief.
100 times?
Well, because the dipole amplitude is 10 to the minus 3, not 10 to the minus 5, the one that we see and ascribe to kinematic. But you are right in principle that the intrinsic CMB dipole could be of order 10 to the minus, whatever we see it to be, and ascribe to kinematic. However, in fact, we are looking at it right now. In principle, such a thing could be done by a horizon scale perturbation. It would actually have to be an isocurvature perturbation rather than adiabatic one, because adiabatic perturbation, matter and radiation fall at the same rate. But then the question arises, Manuel, why should that be aligned with the other dipole if that is due to our motion? So you can try and do that. In fact, you're looking into what it would take to do that, but it actually, I'm sorry to say, is not a clean-cut solution. It raises as many questions as it attempts to answer.
That's probably true.
Yeah.
Any more questions, please? There.
Hi, Sudhir. Thanks for the nice talk. So as you know very well, WISE, as you mentioned, is in the infrared. And that has a totally different set of systematic errors that can come in than the radio observations.
Which we consider an advantage, yes.
Yeah, but then I worry about your combination for the total discrepancy with the CMB dipole, because it's not just a simple addition, right? You have to...
No, we do a simple addition because the two p-values are completely independent here. So you can just use the Z scheme to combine two p-values of independent experiments. You're quite right that the systematics are quite different. One is made from the sky over many years, the other is made from the ground. And the fact that they give dipoles consistent with each other is actually quite interesting. In fact, that increases our confidence in the result. But the combination of p-values is the standard one, Fisher's method. This is quite legitimate when you have independent catalogs. So what we did was to make sure that there isn't a single object in common between them, because the radio sources are extended lobes due to the plasma beams that are being shot out from the black hole, whereas the infrared sources are, as I mentioned, the accretion disks around the central engines, which are actually being heated by the radiation. The dust gets heated up and emits infrared. So the selection procedure is completely different. The selection effects are completely different. But they're totally independent. That's from a statistical point of view, that's all that
The
matters.
statistical point of view, yeah. But the systematics from zodiacal noise in particular for infrared observations can be pretty nasty, right? So
Well, we have the world expert on infrared quasars on our team. That's how we are able to do this.
Okay.
I mean, if you held me up outside and asked me about infrared quasars, I might not be able to answer all your questions. Yeah.
Sounds good, thanks.
Okay, please.
But I know who to ask.
So I have a very naive question. So then what convinces us of the standard cosmological picture is not only simplicity, but its consistency. Yes. So then, as you mentioned, the omega, the total omega is omega lambda, omega matter in the standard picture, omega k, and omega radiation.
Yes.
That is small and you omit it. So
Yes.
then, and it adds up to 1. How do you propose to modify this based on the fact that we know from the CMB the measurements of the omega matter, omega k, that should be close to 0. So what is lacking?
Well, when you say they add up to 1, is because you wrote that equation down and you made them add up to 1. Nature did not tell you that. Nature did not tell you what are the terms in that equation here. Those are the ones we allowed them to be there. If I add a fourth term, for example, I call it something, then that would be an additional omega appearing in the sum rule, and that could be 0.7.
If you do what? Sorry?
I'm saying, you are asking if I have got only omega m and omega k, what makes up the rest? That's what you're asking.
Right.
I'm saying it could be a term that I did not add to the Friedmann-Lemaitre equation. The Friedmann-Lemaitre equation is based on exact isotropy and homogeneity. If we depart from these assumptions, then you can add additional terms to them. This was done by Thomas Buchert, for example, in a modified Friedmann equations. He has an additional term, call it omega.
Well, that was my question. What kind of terms you have to add for this to?
Well, you have to construct a model of a inhomogeneous and anisotropic universe. They would have additional terms. The simplification that you see here is directly due to the assumed isotropy and homogeneity. Now, those options, unfortunately, pardon? What is still valid? I just showed you the evidence that it is not. Yes, because the quasars are at tens of thousands of megaparsecs.
Okay, if there's no other answer question, let's take the speaker again.
Thanks.
And invite our next speaker, who is Ilias Kiritsis. And would talk us, yes, there is, what is the, did you take it to be the pointer? And will talk us about the light from the dark sector.
My thanks to the organizers for giving me and I guess all of us the opportunity to be in this beautiful place. It's a pleasure to be back to Ioannina. What I would like to tell you briefly today is several things that one can get from a specific kind of dark sector, and this is work that appeared on various forms in several papers. How do I move the... several papers. So let me start by reminding you that both fundamental particle physics and cosmology face major problems and puzzles, and these are associated, first of all, to observation, dark matter, dark energy, matter-antimatter symmetry, as well as the completion of the neutrino sector. And then we have theoretical problems like the cosmological constant problem and the black hole information paradox. Both of them, in fact, can be viewed as a clash between semi-classical gravity and quantum field theory. Most researchers agree that most probably the weak link for these problems is gravity and how we marry gravity to quantum mechanics. Now, we have perturbative string theory, and I think it's fair to say that this is the only context that so far can provide at the same time both a quantized theory of gravity and a semi-classical space-time. However, it's not really a UV complete theory, or at least perturbative string theory is not a UV complete theory. It has a cutoff, and this cutoff is the Planck scale. And one of the most important breakthroughs in the last few decades is the concept of the holographic correspondence, which intimately linked two frameworks that were thought to be quite different. One was string theory, and the other was quantum field theory. In the 80s and the 90s, we used to think that string theory basically was encompassing quantum field theory as a low energy limit. Today, we believe that both string theory and quantum field theory are two different aspects of a single framework whose universal description is harder than both quantum field theory or string theory alone, and its global description is not known. Holography did, however, provide a non-perturbative formulation of string theory around at least asymptotically ADS backgrounds, although other backgrounds, in fact, it's still debated whether such a thing exists. And one of the lessons we learned from the holographic correspondence is that gravity and gravitons can be composites of quantum field theory fields, which are generalized gluons. And this is, of course, an idea that is much older than holography. Physicists pursued it in the past, basically motivated with the analogy between pions and QCD. And in that case, we know that the low energy theory of pions and baryons is a bit like gravity. It is non-normalizable, it is infrared free, and it was unclear until the advent of QCD on how to treat the quantum theory. However, QCD gave a clear picture. Pions are composites of quarks and gluons, strongly interacting in the infrared, but the UV properties of that theory are controlled by the quarks and gluons. And similarly, it was attempted, at least in the 60s and 70s, along similar ideas, to make graviton composites of quantum field theory fields. However, not much progress was achieved because you need strong coupling, at least in the infrared, and then the Weinberg-Witten theorem came, which severely constrained the outcome of such approaches. Then came Tufts' observation in 1974 that maybe a weakly coupled string theory could be describing large N QCD. That did not appear really as a big surprise because it was already suspected that QCD flux tubes must have some string-like dynamics. The new element here was that these dynamics, in fact, would become weakly coupled when N was large. However, nobody dared at the time to fantasize that the string theory associated with QCD would describe, among other things, the quantum gravity of the spin 2++ Grubel. And when Mandaceno proposed the ADS-CFT, he provided us essentially with two items. The first is a string theory candidate, which was dual to a large N four-dimensional gauge theory, and also a big surprise, that this string theory lived in 10 and not in 4 dimensions. And moreover, it made it clear that the string theory fields were basically the gauge invariant single trace composites of the gauge theory fields. And he provided the first non-trivial hole, in fact, in the Witten-Weinberg theorem that prohibited a massless emergent or composite, if you wish, graviton. Since then, of course, we have theories with discrete spectra like those of real large N Young-Mills, and they have been constructed. They violate, in fact, the Weinberg-Witten theorem in a very interesting way, in the sense that the emergent gravitons are massless, or the emergent graviton is massless in the higher dimensions, which is not forbidden, in fact, by the Witten-Weinberg theorem, but when reduced to 4 dimensions, it becomes massive via the gravitational Higgs effect. And it's interesting to use what we learned from the holographic correspondence in order to study the emergence of gravitons and other particles, which could be typically axions or graviphotons, as avatars of a hidden sector that's coupled at high energy to the standard model. And this might give us a complementary view of older approaches of obtaining gravity from string theory. So hidden sectors, of course, have been used in various contexts added to the standard model. They can be hidden because they have either small marginal couplings to the standard model, or they are connected by very massive messengers. And what I would like to advocate is that gravity and many other weak interactions could be the result of the standard model coupled to such a hidden sector which is holographic. So the relevant framework, which is similar to something that Kostas has discussed a bit before, is with one difference, that is, you have a hidden large N gauge theory, that's a holographic theory. Instead of having another holographic theory, I have the standard model or some mild high energy extension of the standard model. And then these things are coupled with massive messages. And the messages are biofundamentals under both the hidden theory gauge group and the standard model gauge group. You can assume they're massive with some mass m, which could be, which is assumed to be much larger than all the scales of the standard model and of the hidden theory. And the complete theory is assumed to be a standard 4-dimensional quantum field theory, which is defined on a flat Minkowski background metric. Now, there is another picture for this theory once you integrate out the messages and you go to lower energies. In that case, you can discuss a direct coupling between the hidden holographic theory and the standard model. And in this case, you have contact interactions between the two theories that couple them together. So now these couplings, in fact, look irrelevant from an IR point of view. And in this way, various gauge invariant operators of the hidden theory, in fact, can couple directly to the standard model. And one of these couplings, in fact, would be a coupling between the stress tensor of the hidden theory to the stress tensor of the standard model with appropriate powers of the mass scale m to make this dimensionless. And essentially, already from this type of coupling, in fact, if this has some vacuum expectation value, which I called h mu here, basically this would look like an induced gravitational coupling where some metric here, h mu, would couple to the standard model stress tensor. Now, this is the framework, in fact, that would seem to induce gravity, in fact, to the standard model. And in the generic case, this, you can think of it as a composite graviton. It's basically reflecting the hidden stress tensor, the hidden stress tensor. But in a generic case, of course, if these are generic theories, this is not something you would call gravity. Neither H would be something that looks like what we consider to be the gravity. However, when this hidden theory is holographic, then this graviton will be a massless graviton in a higher dimension, as we know, and it will also move in a non-trivial background, as we learned from the ADS-CFT correspondence. So the emergent gravitational interaction in this case has the standard features of gravity. It's weakly coupled, it has diffeomorphism invariance, and it's accompanied by a few other, few or more, depending on the situation, other additional fields, which could be the analog of graviphotons and light scalars and maybe fermions. And when this gravitational interaction is reduced back to fourth dimension, then the graviton would acquire massive features due to the non-trivial gravitational background in the higher dimensions. So a holographically dual picture of this setup is given by some bulk gravitational theory that should be describing the hidden theory. This, in general, will live in more than 4 dimensions. How many depends on what theory this is. And it will be essentially the theory that's dual to the holographic hidden QFT. And this will be coupled to a 4-dimensional standard model that would look like a brain embedded in the bulk geometry. A picture, in fact, that has been considered many years before. It looks like a simplified Randall-Sundrum picture, but there are important technical differences, in fact, from what Randall-Sundrum had done. So the main difference, in fact, from Randall-Sundrum realizations of this idea is there is no UV cutoff in the bulk description, and there are no Z2 boundary conditions on what people call the Randall-Sundrum brain. So in this context, one can show in general that, first of all, the emergent gravity theory has a unique diffeomorphism invariance. Second, it is a bi-gravity theory. There is a dynamical graviton that captures the interactions of the energy momentum tensor of the hidden theory, the composites, and there is a classical fiducian and non-fluctuating metric which is the fixed metric on which your original quantum field theories were defined. Now, in standard holography, the dynamical graviton lives in the bulk, and the fiducial metric of the dual quantum field theory couples via the boundary conditions of the ADS boundary, but also ADS-CFT correspondence is a bi-gravity theory. There is a bulk dynamical metric, and there is a fixed metric, which in fact participates in the dynamics, but it's not dynamical, that appears as boundary conditions. Now, it can be shown, in fact, that in the dual quantum field theory, if you define the dual quantum field theory in a flat metric, and then you look at the emergent gravitational theory, this emergent gravitational theory always admits a flat metric solution for the dynamical graviton, independent of all quantum corrections. And this is, in a sense, the first ingredient that you would need if you want to consider a kind of quote-unquote solution of the cosmological constant problem. And this particular statement can also be shown in the gravitational brane plus bulk language via the so-called self-Turing mechanism for the cosmological constant that under the conditions that I mentioned, now it works, although it didn't work when it was tried in the past in the Randall-Sundrum context. So in this last context, we can calculate the effective four-dimensional graviton mass as a function of the theory parameters, and the presence of large n in the holographic theory is important as both implies a weak effective coupling between composites, in particular the graviton, and it's also responsible for the suppression of the graviton effective four-dimensional mass. However, as already Kostas has mentioned in his talk, there are many open questions that need to be addressed until such a setup can be confronted with data. Let me now come and discuss a few other avatars of such a hidden sector. So there is another special field, in fact, in the hidden sector, which is the universal axion. This is essentially the composite of the instanton density of the hidden theory. This is, in fact, how many you have, of course, depends on whether you have a simple or semi-simple gauge group, and it will give rise to a composite that's a pseudoscalar, and it has very, very special properties because the instanton density operator is a very special operator in a gauge theory. In fact, one can compute its low energy characteristics, which are given by the appropriate scale f and its mass, and in particular, the scale f is related to the m, I remind you, is the messenger scale, and mh is the dynamical scale of the hidden holographic theory, and then its mass has two contributions. There is a contribution that comes from the hidden theory, and there is also a contribution that comes from effects from the standard model that are well known. In fact, this is a more complicated version of a simpler version described earlier by Bonfoy, Dudas, and company. Now, in the holographic case, the interaction of such an axion is four-dimensional only at short and long enough distances, but maybe five-dimensional, in fact, at intermediate distances. And it has been argued by Pascal and company that such a composite axion can provide a new distinct portal to dark matter. In such a context, you can have emergent, what I call graviphotons, which is essentially emergent composite vectors that originate in the hidden theory, but eventually coupled to the standard model. Such vectors are associated with global symmetries of the hidden theory, and in this case, a U1 composite vector is generated by hidden conserved U1 current. Under the holographic correspondence, such vectors correspond to closed string U1s that are usually called graviphotons, and hence the name I'm using. And generically, at large n, or weak string coupling, such composite vectors are weakly coupled and massive. However, as it happens with the gravitons, which are formulated as higher dimensional vectors, they carry an associated gauge symmetry, and in the higher dimension, higher holographic dimension, they're massless. Now, in the case where the hidden theory is holographic, you can write a simple low energy action which describes the infrared dynamics of such vectors, which is in the form bulk plus brane. In the bulk, you can add, apart from the usual story, a kinetic term for these vectors. You can add an induced kinetic term for the brane, and then the estimates of the various couplings are given either by the five-dimensional Planck scale or the combination between the 5-dimensional and the induced 4-dimensional Planck scale, MP. There are several issues, in fact, that may be of phenomenological relevance in this context. Again, I think here you find that the interaction mediated by these types of vectors is 4-dimensional both at short and long distances, but it can be 5-dimensional at intermediate distances. And at long distances, in fact, the mass is of the order of the scale of the hidden theory. And you can estimate also the effective 4-dimensional coupling constants, GIR, and the effective mass MIR, which are functions, as they're shown here, of the characteristic scale of the hidden theory, the 5-dimensional gauge couplings, and the 4-dimensional gauge couplings. And M0 could be a possible addition to the mass if there is some kind of Higgs effect in the standard model. So the effective coupling, in fact, is in general very small for both reasons, both large if n is large, but also the fact that M5, the 5-dimensional Planck scale, is much bigger than the characteristic scale of the hidden theory. And therefore, these types of emergent vectors fall in the class that we usually call dark vectors, and sometimes we consider them as part of dark matter. An important, in fact, question about such emergent vectors is whether they are minimally coupled to standard model fields, and the answer, no. Therefore, the only coupling of such vectors to the standard model is via the famous hypercharge portal. There is a dimension 4 operator of this type that in principle is allowed. It has a coefficient x, and this dimensionless coefficient x controls the diagonalization of the electric charges of the chargeless fields, as it's known since some time ago. Because of this, it's a coefficient which is severely constrained, and therefore it is also a major problem if in your theory you have a large enough such coupling. If you estimate just from general quantum field theory EFT arguments, what is the size in the context I mentioned of this coefficient, you find out that it's of order 1 over n. However, it turns out that if the hidden theory is holographic, there is a further suppression. To estimate that, you have to use some string theory language. For example, in weakly coupled string theory, the analogous coupling is the coupling between a graviphoton and a brane photon, which the hypercharge, in fact, would be the brane photon. This type of coupling, in fact, has been calculated in the absence of Ramon-Ramon fluxes by the Madrid group, and we had to amend this calculation by adding Ramon-Ramon fluxes. And what we find is that in a holographic hidden theory, x goes as 1 over n to the 3/2, with one possible exception. If the standard model or the extended standard model contains an adjoint Higgs with respect to SU2, then this can go back to 1 over n. So in this type of context, in fact, it's easy to have weakly coupled dark gluons, which naturally small mixings to hypercharge. Let me say one final word about neutrinos. In general, composite neutrinos have been discussed in the past. You have some hidden theory, it has strong coupling, and then fermionic bound states in that theory can serve as right-handed neutrinos. Here, the difference is that neutrinos can appear as, in fact, mesons or mesinos, in fact, from the messenger fields. So it is distinct from what has been discussed in the past, and also associated ideas that have been worked out in holographic brane-wall duals. So here, the messenger mesinos are the natural right-handed neutrinos, which mix with the left-handed neutrinos, and the large messenger mass M essentially becomes the seesaw mass that will give light observable neutrinos. So let me conclude. A strongly coupled holographic hidden sector can provide emergent gravity coupled to the standard model. This emergent gravity seems to be a promising route to quantum gravity. It has the potential of alleviating several of the serious problems quantum gravity faces, like the cosmological constant problem. But there are many issues that remain to be understood until a phenomenologically viable theory exists. Along with gravity, one gets a composite universal action, various dark graviphotons possibly, and right-handed neutrinos that appear naturally in this setup. And the dark photons have unexpectedly small couplings and mixings to hypercharge. And the phenomenological signatures and implications of such composite axions and dark photons may need further analysis. Thank you.
Thank you very much, Elias, for the very interesting talk. Are there any questions, please?
Thanks for a nice talk. I have a question. I'm not sure I follow what you want to do with the dark energy. Do you want to get a positive dark energy in ADS correspondence? Does not include that. That's question number one. And the question number two is that in the context of the ADS holography, there's always an extra space, and the limit where ADS is flat. So if you want lambda near zero, positive or negative, regardless, you get tower of states. Are you expecting no tower of light states? What is your picture there? I'm not following it.
First of all, discussing the fact that you have extra dimensions, indeed, the gravity that you're getting is higher dimensional. The fact that it looks four-dimensional on the brain is basically the Gavadadze-Valiant-Porati mechanism, which balances, in fact, the reduced gravity term on the brain with the bulk gravity. So this is why, in fact, this mechanism alone, without a curved bulk, will give you four-dimensional gravity in the UV. The fact that you have a curved bulk gives you four-dimensional gravity in the IR, and then depending on scales, you may or may not have an intermediate regime where you have higher dimensional gravity. So that's the statement about the higher dimensional gravity. Now, your first question also...
no, my question was, the two questions was kind of related. What value of lambda are you trying to achieve? The cosmological constant.
The effective on the brain is not what value you have in the bulk. And that's basically the whole point about the self-tuning mechanism. That is, of course, this has various, this type of problem has various types of answers. If you consider, for example, a completely static situation, which doesn't have to do anything with cosmology, in that case you can find that there is one or more places of putting the brain in the bulk for which, although the brain can have a high cosmological constant, and of course there is a bulk cosmological constant, bulk potentials in general, that the brain in that position does have a flat metal. This is the self-tuning mechanism, basically. Now, of course, this in itself is not enough in cosmology. In cosmology, what we know is the following. That is, if you allow now the brain to move, and therefore you allow time-dependent dynamics, unfortunately, this type of analysis, you can do it for the moment only in the probe approximation. Then the brain moves in a kind of effective potential that has a minimum, in fact, exactly at where the self-tuning position is. Therefore, if you're asking a question about what could be the observable remaining cosmological constant today, this is a more dynamical question. It would be having to do with a kind of friction for the brain moving around the bottom of the potential. But this requires an analysis that so far, that is to estimate how much it is. An analysis so far we cannot do.
Okay, any more questions? Nick?
Nice talk and nice work, Elias. Your action is not related to the string model independent action that we have in general in string theories.
It could be, but for example, if your dual quantum, the hidden theory is n equal 4 super Yang-Mills, then obviously the action, the universal action, is precisely this one. But as you know also from string theory, you can have more than one actions, and that would depend about how many gauge groups you would have in your theory.
So you also have you could have a multi-action phenomenology,
yes,
for instance.
Indeed.
Thank you.
Okay, any more questions? Okay, let's thank our speaker again.
An announcement. Of course, afterwards, we go for lunch to the same place. Secondly, at 7:30, there is a public talk, and immediately in this place, in this room, and immediately downstairs after the talk, after this public talk, there is a reception. Thank you. The public talk is about twistronix. It's from Professor Kaxiras from Harvard. In English, of course. Yes.
Pasterski, which will tell us about Teams and celestial safety.
Okay. So this is my mic? Great, okay. So I had the great pleasure of being, I guess, a guest here at a SUSY conference to, I guess, pitch this kind of program that came out of Andrew Sturminger's group at Harvard and has kind of been developing in different ways over the past just shy of a decade. But the point of today's talk is to at least make sure that the starting point is clear so that we can then get to some of the recent things that we've been figuring out. Let's just start from the motivation for this program. Great. Okay, so we basically expect quantum gravity to be holographic. So for whatever bulk space-time we have, we want to look at how to encode that in this non-gravitational theory on the boundary. The classic success story, of course, is ADS-CFT, but that has the wrong sign cosmological constant. So there are various attempts over the years to try to apply this framework to various astrophysically relevant contexts. So let's play a little game of Goldilocks here. If you wanted to stick to some ADS geometry, you could, instead of saying that's the full space-time, zoom in on some near-extremal, near-horizon region and have some sector that's ADS, and that would be the Kerr-CFT correspondence work that people have done maybe a decade ago. Of course, we really want to go out to a cosmological version where you have the right sign cosmological constant, and that would require us being able to either rotate from, change the sign of the cosmological constant, or start from the de Sitter correspondence. So I would say that the program that I'm going to be talking about today, Celestial CFT, is trying to do this happy medium where we're spanning physics from collider scales up to, say, measuring gravitational radiation coming from some inspiraling binary system, which is well approximated by vanishing cosmological constant. Now, of course, one can always complain that I am going to literally say my spacetime is asymptotically flat, and then my data lives at the conformal boundary, and push that through. But in the end, we want to really think about this program as telling us something about the S matrix. Okay, so now to get onto every cult has their terminology. So what is celestial holography, trademark? It's a proposed duality between gravitational scattering in asymptotically flat spacetimes and a CFT that lives in the celestial sphere. So you look up in the night sky, you see where all the stars are. That space is our celestial sphere where we're going to basically put operators and say that those operators are corresponding to excitations that create scattering states for a given S matrix process. Okay, so the main takeaway, if you guys fall asleep after 3 minutes, is that the point of this program is it's supposed to reorganize scattering in terms of the symmetry. So we wouldn't be doing this kind of change of basis of my S matrix if we didn't think that it was going to have something coming out of it. And in particular, there's basically an infinite dimensional enhancement coming from the asymptotic symmetry group. And this is something where if I'd started with ADS-CFT and then try to take a flat limit, I need to be very careful about how I take that flat limit and how I change whatever boundary conditions I have so that I really do allow for incoming radiation and outgoing radiation and recover this asymptotic symmetry group that I know that I have if I started directly from the asymptotic structure of Minkowski space. So what's the outline and or checklist? Because for a short talk like this and with an audience that's not in this little niche, I'd be better spend most of my time setting up the case for why I would even do this in the first place. But that's going to be the majority of the talk is bullet point 1. And then I'll make sure to give some obligatory shout out to where SUSY's helped in the story. And we'll close with some ongoing questions where we can talk about recent things that are kind of under development right now and why we're still excited about this. Okay, so our goal is to apply the holographic principle to vanishing cosmological constant to understand quantum gravity in these asymptotically flat spacetimes. And the plan is to show that the picture on the left can be mapped in a way that's useful to these punctured spheres and talking about some radial quantized theory on that. So when I say asymptotically flat spacetimes, because it's a broad audience, I mean I have 0 cosmological constant, but I have non-trivial matter distribution. And once you do that, then your metrics are no longer going to be exactly flat, but there's going to be some perturbations. And the point is that the very large scale structure that you get, if you look really far away, is still going to have the same causal structure as Minkowski space would. So let's go through the Penrose diagram for Minkowski space, because, okay, so this is actually relevant to when I want to compare Minkowski CFT to an ADS CFT context. The key difference is basically the structure of this conformal boundary. So I have spatial infinity, where if I just took a time slice and go out, I would go here. Now, of course, if I evolve for any infinite amount of time near spatial infinity, I'm still near here. So the points just above and just below that I0 are misleadingly like close to each other on this diagram. But still, light rays go at a 45-degree on this line. So I basically just try to plot Minkowski space onto a sheet of paper and still capture the causal structure of the conformal boundary. So the part that I'm most interested in is where massless excitations enter and exit, and that's going to be called scry minus and scry plus. And then if I were massive and just sitting along a world line or accelerating but never constantly accelerating so that I'm approaching a like trajectory, then I would start at past time like infinity and end up at future time like infinity. And I've basically doubled it to show a particle that comes in from scry minus and exit at scry plus, but otherwise there's an S2 over every point mod Z2 for 1,3 signature. So what I want to say is that basically that celestial sphere cross-section here is what I'm saying is my place where this conformal field theory is going to live. And the point is that if I want to capture the initial or final data for massless scattering, then my boundary is null. And so that's the main difference between the setup with this cylinder and putting correlators in the boundary. I have something now in Minkowski space that I'd also have in de Sitter, which is I need to deal with basically connecting in and out, I guess, depending on the patches that you're using in the de Sitter case. So let's try to compare two, I guess, maybe precedents for a flat space hologram. The one is, okay, so instead of, say I have some local quantum field theory in the bulk, and then I'm only computing S matrix elements, so I can merge that picture of saying, okay, well, the S matrix, there's only on-shell states. I have some initial data scattering up to some final data, and I look at the probability of that overlap. Or I have instead, like, so that's basically codimension 1 by nature of being on shell. And then in the ADS-CFT context, I get codimension 1 by going out to the boundary, and I'm looking at correlators on this boundary. So those two pictures are actually consistent with taking the flat space limit of the right-hand side. When I think about taking my Cauchy slice and pushing myself up to future or past null infinity. And so when I do that, basically I'm just saying I'm going to prepare my in state and my out state that I would use as my input for some like collider experiment. And think of that as literally being prepared by putting some operators in my space-time in the very far past and the very far future. And it's convenient for me to do so in a manner for massless scattering that really does pretend that it's a long scry minus or scry plus, so these null hypersurfaces, as opposed to just a Cauchy slice that's a constant time slice. And part of the reason why it's nice to do that is because it starts to give you a slightly more local picture from the point of view of the celestial sphere of the excitations that I want to create. So with just some play with the order of limits, so I'm always going to send my R to infinity first to reach this conformal boundary before I look at limits of this coordinate U, which is along this conformal boundary. And when I do that, basically the rapidly oscillating phase of a plane wave will be such that this term here would be swamped if R goes infinity, unless I'm really close to the angle of the momentum and the point on the celestial sphere being aligned. And so when I do that, what happens essentially is that if I wanted to prepare a plane wave, so just a standard, like, I guess, input for like a Feynman diagram, in this space-time picture, I have to smear with a certain Fourier transform the boundary limit of my bulk field operator along a generator of scry. So the thing I want to emphasize here is we're really just trying to attach a space-time picture to the things that you're setting up in the S matrices that you're familiar with. And I could similarly do the same thing with the massive guy, where I need to be careful about how I smear near I plus or I minus. But this perspective is useful because, like as I'll get to later, we can basically merge kind of our understanding of like this phase space from like canonical formalisms in general relativity and what you're used to from perturbative quantum field theory, if you substitute. So when I say I'm going to then dimensionally reduce to the celestial sphere, what I'm basically just doing is using the fact that we have a Lorentz invariant theory. And so each of my operators, there's some little group transformation for the massless case. They're going to be Lorentz covariant. And Lorentz transformations of Minkowski space act as the global conformal transformations in the celestial sphere. So if I wanted to say, let me hand you a celestial CFT, like in a kind of trivial sense, you already can do that, because all it is just a change of basis. And so that's not that interesting, but at least it's not like you're screwed from the beginning, because like, yes, you can do this. This is just kinematics. And so a lot of the downside to, I guess, setting up some of the stuff is there's a sense in which we're really just doing some intertwiners between different representations of the Poincare group. So in this case, we're preferring a Lorentz basis. So why would we want to do this? Okay, so the point is that basically there are going to be two, so if I say I'm a celestial holographer, this is my little pitch. There's kind of two, like a more extreme version of, like, I mean, it's a celestial CFT, and there's a more relaxed version where, yes, the space-time picture helps. So the first thing that hopefully I can convince everybody of is that examining both the asymptotic space-time perspective as well as the amplitude manifestations of a given structure can be beneficial. So you can see kind of what, when you look at what like Claudia was presenting about how the 2-to-2 S matrix behaves as a function of a complexified Mandel-Set invariance, we're thinking of that as being complexifications of null infinity, because we basically have an isomorphism between the on-shell states and this conformal boundary. So that's useful if we think about maybe how we think like structures at scry minus and scry plus are causally connected and things like that, to be worried about collinear limits for in and out versus in and in. And then the second thing, which is maybe the more, like you have to be in a little niche to really, really believe in it, is that the celestial CFT is further useful, this dimensional reduction that we're going to do from this conformal boundary, which has all of these different types of components that we're kind of gluing together, depending if it's a massless case or a massive particle, is useful because it elucidates a larger symmetry algebra. So it'll definitely show that there's this larger symmetry algebra, but again, I'm happy to fight through why we believe in that so much. Okay, so let's go through one example of where, this is a little bit older, of where this is actually paid off. So it's not just like we're going to change the spaces for the S matrix, what have we learned from it? So basically this infrared triangle connecting some features of the low energy behavior of a take one gauge boson soft in quantum field theory to some observables that one can go out and measure, which are signatures of the fact that this asymptotically flat approximation is useful to some extent. When I say I know my cosmological constant is non-zero, but I'm measuring some in spiraling binary systems gravitational radiation, to what extent can I really assume that the boundary conditions for like where radiation's hitting me are effectively as if I had like an asymptotically flat space-time. So there's some measurement here that you can do, which is predicted by Einstein's equations, but at least like the fact that it would be non-zero or have this universal value is tied into also the boundary conditions. So there's something that you're learning there about the approximation. And then finally, this notion of asymptotic symmetries, which comes from the fact that when I go to this flat limit, instead of my standard, like just taking lambda to 0, and I'm careful about making sure to allow for radiation, I get a richer space of vacua. So you have this pattern. In the first instance, there's like Weinberg's soft theorem from the 60s, connecting to the BMS group that was also studied in the 60s. And each of these examples were known back in the day. But the nice thing is about seeing how universal that pattern is, you can find new soft theorems and whatnot. So basically, let me just set up that last corner, because I think this is important to emphasize where these extra symmetries are coming from, is, okay, I'm looking at my metric near scry, and basically have a good gauge so that I can describe with some coordinate system the radiative data near this conformal boundary. And so basically, this 1 over r falloff is set up by Bondi, Vanderburg, Metzner, and Sachs. And if I then have chosen a good set of gauge, a good gauge, so that I understand what each of these coordinates basically mean. Like, so r is going to be a coordinate for like outgoing null geodesic. Then what I'm trying to do is look at what diffeomorphisms I can do that still preserve that class of falloff. So this is the class of spacetimes that I'm in, rather than a particular spacetime whose basically I need to have, say, an isometry. No, I just need basically an asymptotic symmetry. So that's the difference, and that's why it can be larger. So basically, any set of diffeomorphisms that preserve those classes of falloff, so that classes of metric, rather than exactly keeping one metric fixed, becomes this asymptotic symmetry group, and that can be much larger than Poincare. And so this is where these extra symmetries are coming from. And so Bondi, Vanderburg, Metzner, and Sachs knew about super translations, but these super rotations were kind of a proposal that was a bit like unaccepted at the time, because you're essentially allowing punctures in the celestial sphere, and that's kind of singular and something that you wouldn't want to do if you wanted to say like the metric is supposed to be regular there. So just as a concrete example of where kind of this has paid off, this space-time perspective of this S matrix soft theorems have paid off, is you have this proposal to allow super rotations. You then see what would be in that little triangle the soft theorem analog of that symmetry. So Cochazo and Strominger found that. And then you also find a new memory effect. So you basically fill in a whole new iteration just because there's this proposal from the space-time perspective and that can, like covariant phase space methods that you'd want to maybe look at this larger symmetry group. Now, once you have that symmetry as, okay, the S matrix obeys it because of the soft theorem, you would want to try to interpret its word identity. And so instead of the Lorentz group, you actually have a Virasoro symmetry. So already this 2D description is becoming more interesting because we have this same thing that you'd see in a 2D CFT where you have this promotion of the global conformal group to the Virasoro group. And moreover, you have a candidate stress tensor coming from this graviton mode in the bulk when you go to a boost basis. And furthermore, if you want to kind of go back to this like interplay between going to the boost basis and this candidate stress tensor, so all of this was basically some years ago, but recently enough, we also see that we can get the full loop corrections to these guys by basically taking very strictly the fact that we want these objects to transform correctly under the asymptotic symmetry group, yada, yada. So the corrections that would be kind of ambiguous if you just looked at the momentum space form of the amplitude kind of get pinned down by looking at the covariant phase space. So that's nice. But the better thing about, and something that's been more exciting in recent years, so maybe last year or so, is that in this boost basis, there's no reason to stop at like the subleading Zoff theorem for some reason. So essentially, if I look at my, this transform of my amplitudes to go to this boost basis, which involve basically integrating over all energy scales, and I look at the singular structure in this variable that corresponds to the conformal dimension, it picks out a whole tower of soft modes. And then I can look at their collinear limits and construct basically an algebra like I would if I really treated those operators as living in a 2D CFT, and I get this W infinity symmetry. So that's kind of neat. It's like, why is that here? So the understanding of it from the point of view of like, just like classical GR, so would be from symmetries of anti-self-dual gravity. But you start to build up this picture where you have more and more ingredients in this dictionary, and then you can start trying to look for particular concrete realizations of a celestial CFT, like by what you mean for this like hologram. So some subsector of gravity is still maybe a consistent theory of quantum gravity that you can map directly to an actual 2D CFT. So that's nice. So basically, the goal of the celestial holographer would be to convert what Claudia is talking about to a like space-time perspective, so at least we can kind of see what's going on. And then more ambitiously would be also to be able to kind of bootstrap amplitudes from the soft and collinear limits. So looking at, you have this continuous set of conformal dimensions because you really do have a U coordinate that you've dimensionally reduced, so it's not compact. But somehow the data at these integer points is really all you might seem to need. And then if you really do have that, plus you have like understanding of the celestial LP when you take two operators near each other, then one could hope to try to set up some sort of bootstrap program, but we're in early days with that. And so let's do a very brief SUSY shout out because the audience is a SUSY audience. So where have insights from Supersymmetry helped us? One concrete example is where basically the soft theorems equivalence to the word identity. The easiest cases are where you have a gauge symmetry because basically you're just doing Gauss's law in some weird cut of your space-time. But it's less obvious when you have particles without a gauge symmetry. So like the soft photino is related by supersymmetry to one that is, and it has a soft theorem. And so you can really push through this triangular equivalence in an instance where maybe the intuition is less clear for why you would have expected the full set of things, but it kind of guides you to know, like take it seriously, use that soft theorem and reinterpret it as some current in this 2D CFT. So you can do that. Also, wherever supersymmetry is helpful for an amplitudes computation is helpful for us because we're just transforming that. So that's an easy check mark. And then similarly to the stress tensor, you can define a supercurrent from the soft gravitino. And if you look at those algebras, so like the super BMS algebra, it's actually a little bit different than what you'd expect from a superconformal algebra. So those type of tensions raise some interesting questions for what kind of are some ongoing questions now. So the main question that I've, I guess, played with recently is the role of the IR regulators. So essentially, if you want to have a non-zero level for your, so central extensions for things, you need to somehow include either loop effects that introduce an IR regulator or deform the symmetry algebra so that you can look at sectors where basically you have now the IR regulator coming in and giving you a non-zero level. Similarly, along the lines of understanding interesting things from the S matrix, we want to understand crossing both in the 2D conformal block sense as well as in and out sense, and that is closely tied to analytic continuations. So looking at the analytic structure as I move punctures around in this complexified celestial sphere and change signatures. And then finally, building up toy models where we basically have a set of necessary ingredients for celestial CFT. And then basically one particular fruitful example is looking at this conformally soft sector where basically spontaneous symmetry breaking of these asymptotic symmetries is governing everything. So that's what I wanted to say, and thank you guys so much for letting me do my little pitch for my the thing that we can work on. Great. Run out of votes.
Thanks a lot.
Yeah.
We saved a few minutes.
Good.
Questions?
Thank you. Very nice review, Sabrina. So a few questions. First of all, in higher dimensions, you're doing it 3 plus 1 dimension, I assume, right?
Most of the time.
So if you do higher dimension, presumably you have a celestial sphere there too, and you also expect a CFT there?
Yeah, yes. So we expect a CFT in the same sense like the Lorentz invariant. So, yeah. Okay. So the extent to which the mileage is helpful, somehow there's parts of it that are a little murky between going to higher D, but definitely you have the same CFT. I would say that basically most of the kinematic stuff just directly carries over. There's some properties of these like towers of null states that you see in 2D that would be a little bit more complicated if I tried to write down like how do I find primary descendants from a mode with spin 2 down to some other mode that it's going to couple to. So there's some structure that maybe will be less rich in higher D, but you can set up the first step, which is just like mapping to this boost basis in any dimension.
So the other thing is that, if I understood correctly from other talks, that your CFTs are non-unitary generally, right?
Yeah.
And that's related, for example, to the level you were mentioning, maybe, I don't know, or complex, you get complex dimensions, if I remember, right?
Yeah, so we have complex dimensions. So the reason why I want to be a little bit careful of just saying, you're right, like it's non-unitary, is because I think there's some, like, okay, so if I wanted to capture just radiative states, I know my conformal dimension needs to be on the principal series. But there is a sense in which this, like, tower, like, W infinity generators, are essentially as if you analytically continued delta to the complex plane and then restrict it to integer values. So I wouldn't put it past a future version of like some model for some, like, sorry, I just wanted to model like the IR divergences in 4D, which again now is restricting to 4D. Then I could have a free boson that basically captures this like factorized part, which is the soft sector of this, of QED. So what I want to say is that there's a chance that there's still some like more standard CFTs that are sectors within this guy. And so maybe some mileage can be made there, at least in 4D, if I really wanted like to look at the IR divergence part. But I agree that in general, we don't expect it to be the standard unitary CFT.
You don't expect. And you have a structure, you don't have a specific CFT in mind, other than the fact that Virasoro seems to have.
We have more than Virasoro now. So I would say
I mean W version of Virasoro.
Yeah, so you have W, yeah, exactly. So you have, I would say that you expect, like we're adding to this list. I think with Herman, we were trying to argue that there's also some notion of like chaos and things like that. But we're trying to like see what do you need to have in this guy. So the W infinity symmetry seems to be there. There's issues about if it's more natural, just look at a single like helicity sector when you want to exploit that. We also have, I mean, whatever like charges, like, so basically whatever external scattering states you have, if there's like the charges you would associate labeling those, you'd have a different asymptotic symmetry for those and then more restraints on like what you'd want in your theory. But because gravity has to be there, you would have this W infinity. And then I think most of the other things kind of follow from that, that we're saying have to be there.
Thank you.
In the usual ABS-CFT,
yeah.
We know we have conformal bias at the boundary because it's encoded in the bulk letter.
Yeah.
And also we know that there is a UV-IR connection because the infrared divergences of the S matrix become the UV divergences of the dual correlators.
Okay.
In your case, of course, we have infrared divergences in principle in the S matrix elements.
Yeah.
The question is, what do they correspond in the cumulative dual QFT, and do you have scaling variance after all?
Okay, so I'm going to punt to some extent, but I'm going to try to basically say whatever you know in ADS-CFT, I'm confident there's a way to translate it more directly or not, at least when you're not doing a strong weak duality version, to this case. Because, so what we're basically saying is, okay, I'm taking all of my bulk operators to the boundary. So one first, I guess, instance of like a cutoff in this 2D theory, because I'm further dimensionally reducing, is this scale that's corresponding to taking collinear limits. So if I look at, I have certain like modes with logarithmic correlators that correspond to dressings. And so I would say that this natural kind of like cutoff scale in the lower dimensional theory is this collinear limit scale in the bulk. So to me, while I can't directly necessarily answer like the exact question you were asking, I can hint at a couple, I guess, related questions, and then you can like call me out on it so we can reiterate in this. So basically, the IR divergences in my 4D theory kind of come from two sources. One is this like large R limit, if I need to cut that off, and one is the late U limit. So I think that the ratio of those two is connected to this, I guess, UV divergence in the 2D theory. But that's not quite answering your question, so maybe ask again something else building off of that I can answer better.
Yeah, the question is,
Yeah. 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 Oh. Yeah, so the IR divergences in the S matrix correspond to basically the fact that I want to strip off those IR divergences with dressings that basically make all of my operators invariant under large gauge transformations. So the fact that I have an IR divergence is essentially the fact that I have my operators near null infinity are not actually gauge invariant under these diffeomorphisms or gauge transformations that make it out to the boundary. And so I basically dress those away with, instead of with Wilson lines, with basically this vertex operator that also shifts under these gauge transformations. And that little soft sector that kind of factors out would encode all of the IR divergences in 4D. I think it should come down to the fact that, like, if I try to set myself up a little bit better with like the fact that I'm supposed to have this conformal boundary and the data on like a la Ashtekar or somebody, like not necessarily in bonding gauge the way that I've set it up, but I think if you try to be a little bit cleaner about setting up the scattering data in terms of the fact that you're supposed to be able to do conformal rescalings and like of this 4D metric, that you might be able to see that more clearly, but I wouldn't have anything better to say about it now. Thank you.
Okay, so the next speaker is Bepartouche, and will tell us about the wave function of the universe.
On y va. Thank you very much for the invitation to present some work here. Work done in collaboration with Nick Tumbas, Balthazar de Volchier, and also another paper with Alex Quejallas and Nikolaos Tumbas. So what is it about? All right, we are using quantum mechanics to use wave functions in order to derive probabilities. And of course, these wave functions can be seen from two different points of view. First of all, the Schrödinger equation, and also, which is a differential equation, there are solutions. And also, they can be given, the wave functions, an independent definitions in terms of path integral, and of course, it's consistent. Now, if we want to do something similar in quantum gravity, people have tried to define a wave function for the universe itself. And the idea is to derive from such a wave function probabilities favoring, hopefully, realistic aspects of the universe. Now, such a wave function should be a solution of an equation which is called the Wheeler-de Witt equation, which is similar to Schrödinger in quantum mechanics. However, this Wheeler-de Witt equation, as we will see, we will review, presents some ambiguity in its form. And the second point of view is also possible, and Hartle and Hawking, long time ago, made some proposal, at least in the case where the universe is closed, spatially closed, with a positive cosmological constant. And in fact, their proposal is an Euclidean path integral. So the integrand here is just the exponential of minus the Euclidean action. And here the wave function depends on a three-dimensional metric, Hij. So this is the metric of our space, the space we live in, 3 dimension. And the path integral is a sum over all 4-dimensional compact manifold, Euclidean. Those metrics are J, so J is a 4-dimensional metric. And these manifolds we sum over must have a single boundary, which is precisely the universe, the 3-dimensional universe we are living in, and with metric Hij. So we have our universe, 3 dimensions, and we sum over all 4-dimensional manifolds which end on it. Okay, and this is called the non-boundary proposal because the 4 manifolds we are summing over have no other boundary than the 3-dimensional boundary we are living in. All right, in practice, in this talk, we will restrict to a simpler case where we assume that space is homogeneous and isotropic. So we have just a lapse function and a scale factor as usually. And the path integral here, in this case, simplifies and just get a function of the scale factor at the boundary free sphere we are living in. So we are in a 3-dimensional space, which is a free sphere, of scale factor A0, say. The path integral is over the lapse function, dn, dA. The action is the Einstein action in the homogeneous and isotropic case. And we have to sum over all possible trajectories of the scale factor A, satisfying at initial time 0, the scale factor is 0, so that we don't have a boundary here. There's no boundary free sphere. And on the other side, at the end of time, we have the scale factor, which is equal to A0 at the boundary where we are living. All right, and then we have to divide by the volume of the gauge symmetry of the action, which in this case is just the Euclidean time reparametrizations, of course. All right, so in practice, this quantity can be seen as a probability amplitude, it's a path integral, for creating a universe of scale factor A0 we are living in from something which is called nothing by Vilenkin. Nothing because it's a sphere of 0 size, so it's the empty set. So you start from the empty set and you compute the probability amplitude to create instantaneously our space. So the plan of a talk is to, first of all, fix consistency, the gauge of Euclidean time reparametrization, because there are issues in the literature before. Second, we will consider field redefinitions of the scale factor. Of course, at the classical level, it's a trivial symmetry. You just do a trivial field redefinition. However, when you do that, the scale factor is an arbitrary function of a new field Q. The path integral measure, dA, is not equal to the path integral measure for the new field Q. So at the end of the day, we will see the obvious fact that we get different results for the wave function, depending on the prescription you choose for the path integral measure. Now, for each choice that you make for the path integral measure, we will see that we get a different Wheeler-DeWitt equation. And also, we will be able to lift the old ambiguities which are known about such kind of equations, at least at the semi-classical level. So the question arises then, do we get different quantum gravities since we have different wave functions, different Wheeler-DeWitt equation? And the answer will be the following. In fact, they are all equivalent, and we will see why. They give the same quantum gravity predictions. And at the end of a talk, we will do a cross-check by reproducing from the wave function of the universe and the Hilbert space. We will reproduce the classical cosmology in the H bar goes to 0 limit. So it's quite convincing that there is no trivial mistake. All right, so let's start by the beginning. We want to fix the gauge of Euclidean time reparametrizations. So the action is just this thing. So there is a kinetic term for the scale factor. The A factor here comes from the scalar curvature of a free sphere. And lambda here is the cosmological constant, and A cube is the dressing factor. All right, so this action, actually, in the language of string theory, if we are used to it, is just a sigma model. Why? In string theory, we have a world sheet and a target space. And here also, instead of a world sheet, we have a line segment, which is just the time here, a line segment of time, which starts from x0 Euclidean initial and ends at x0 Euclidean final. And the metric is just G00, which is n squared. And we also have a target space, like in string theory, where the target space here is very simple. It's just R plus, because the scale factor is positive. And it parametrizes a one-dimensional target space. Those metric is just given by this object, which is interpreted as the metric on the target space. So now that we have seen that it's similar to what we are used to do in string theory, we can apply techniques which are well known and fix the gauge carefully, like in textbooks somehow. So let's do that in one slide. Let's concentrate first on the line segment of Euclidean time. So this line segment here. And we make the following observation. All metrics of this line segment G00 are not equivalent up to a change of coordinate. And this is obvious since the proper length of a segment, a line segment, is invariant under a change of coordinates. So if you want to fix the gauge, you have to pick, or you have to choose, an arbitrary metric in each equivalence class corresponding to the length L of a segment. So you choose a length, and you pick some particular metric when you fix your gauge. In the language of string theory, L is just the modulus. It's the analog of the Tesch-Müller parameter at one loop. So at the end of the day, you want to replace the path integral over n divided by the volume of the diffeomorphism, the reparametrization of time. It's interpreted as a normal integral over the moduli space, the different length of your segment. And then you sum over the orbit in each equivalent class, so which is precisely all the diffeomorphism group. And of course, this is going to cancel the volume of the diffeomorphism group. So this goes away, it's just one. And of course, when you do that, we are used to introduce a Fadaev-Popov determinant that you need to compute. So I skip the technical details. But you define the Fadaev-Popov as usual. You reinterpret it as in terms of ghosts, anti-commuting ghosts, B and C, like in string theory or in textbooks. This is the result. This thing is a scalar product, whatever it is. And then, at the end of the day, you do a Fourier expansion, and you find, using gauge invariant measure, it's important here for dB, dC, the ghosts, you find that in this particular case, the Fadaev-Popov is just trivial constant. It's independent of L. A priori, it was dependent on L, but it's not. So what we have to do now is to fix the gauge, whatever gauge we like. And of course, we are going to take the simplest one, which corresponds to a gauge in each class L, for each line segment of length L, a constant lapse function. So we take a constant metric, L square, and we choose the boundaries of a line segment to be 0, 1 by convention, because we have the right to fix anything we like. And the path integral is just this very simple expression. Sum over dl, different length, and the path integral of general relativity, where the scale factor starts at 0 and ends at A0 at the end of time, to time equal 1. The action simplifies and gets just this, takes this form. Okay. And since it's cubic in A, we are going to compute it at the semi-classical level. Now, before doing it, let's make some remark about what people have done in many, many papers, several tens of papers before. In fact, in several tens of papers, people are not taking this very simple gauge, G equal constant. They take L squared divided by A squared. But when you do that, then the upper bound of the action depends on A, because J00 depends on A. And of course, you cannot take the equation of motion, you cannot find instanton easily, because the upper bound is not a constant. So people don't write this, they don't explain, and they just start with that by replacing this thing by 1, which is wrong, of course. Because when you do that, the length L is not anymore the invariant length, and it's not anymore the modulus which parameterizes the equivalent classes of a metric. People are doing that because, in fact, when you do this trivial change of variable in the fields, then you get something Gaussian and you can compute exactly the path integral. But the problem is that you have changed the problem. It's not GR anymore. Okay, so we don't do that, and we do, at the semi-classical level, the computation of this path integral. So I go quickly because the method is usual. We find instanton solution, there are two, so I will denote them A bar, comma, L bar, because there is L and A. We have to extremize with respect to the two, to both. And I put an epsilon here, an index, because there are two instanton solutions. And then I expand the Euclidean action around, at quadratic order, around the instanton action. I get a quadratic term in fluctuations of the scale factor, a quadratic term in the fluctuation on the length, and the cross product here. The operator here, Q, is a self-adjoint operator, you can check, acting on an Hilbert space of functions delta A. So you can diagonalize it with real eigenvalues. And you get something which is relatively simple in principle. You get a sum over instantons, and then a Gaussian integral in delta A, the path integral, and then a Gaussian integral, but a normal integral, Riemann integral, with a delta L square here, with a constant here that you have to compute. You can compute this constant, and you can compute the determinant here of the Gaussian path integral, and you get something of this form, as usually. And, okay, I skip the details, but in order to compute the determinant here, you have to improve the well-known method of Affleck and Coleman they proposed some time ago, a very long time ago. And at the end of the day, you find the result that you find in many papers, but with a correct answer here. And in many, many papers, some people take A0 to the power 0, or A0 to the power 1, or A0 to the power P, saying that we don't know what is P, but P is whatever it is, and we continue, and things like that. So the correct value is 1/8. That's it. All right. So now more interesting is something really new, is what's happening if we do a field redefinition. So my scale factor A, I can define it to be any function I like in terms of a new field Q. Of course, the path integral measure dA is not dq, there is a Jacobian, you have to compute. However, if I don't know the scale factor, if I like Q, I can define a new wave function which depends on Q0 at my boundary, exactly as we did with the scale factor A, exactly the same expression, but A is replaced by Q. You redo the analysis that I presented before for the scale factor, and you find a different expression because now you have a dressing factor in the denominator which depends on the function A you have chosen here. So each time you choose a new field Q, you redefine A, you find different wave functions. So, okay, it's very obvious from the beginning, but it's also worrying. So do we get different quantum gravity theories? What does that mean? Okay, we will see later what's happening. Now, since we have different wave function, we should have different Wheeler-de Witt equation because the wave function is a solution of Wheeler-de Witt. So let's see what is the difference in each case in the Wheeler-de Witt equation. So to do that, let's derive it. So the trick is to say that the integral, path integral, of a total derivative, variational derivative, is 0. So 0 equals dn delta over delta n of whatever you like. But when you act here with delta over delta n, you find the Hamiltonian, the classical Hamiltonian, inserted in your path integral. So the classical Hamiltonian, here h, is just this thing, where pi index q is the canonically conjugate variable of q. Now, because the path integral here vanishes, it means that the quantum version of this Hamiltonian is also vanishing when it acts on the whole Hilbert space. And when we translate this in terms of differential equation, you get precisely what is meant by the Wheeler-de Witt equation. All right. Now, where the ambiguity is coming from? In fact, it's obvious because pi squared here is a classical object. So classically, I can introduce ρ1, ρ2, arbitrary function of q, and write pi squared, 1 over ρ1, ρ2, pi ρ1, pi ρ2. It simplifies. Everything commutes classically. However, in the quantum version, when you replace q by an operator and pi by d over dq, ρ1 and ρ2 remain. You cannot simplify. And ρ1 and ρ2 appear in the Wheeler-de Witt equation through, by a redefinition of, in terms of ρ1 and ρ2, in terms of two functions that you don't know, which are ρ and omega. Okay, so we would like to find ρ, and eventually, what is omega? So to find ρ is easy, in fact, because you can solve this differential equation at the semi-classical level using WKB method. It's trivial. You get this answer, but this is precise. But we know one solution. We know the solution of Hartle-Hawking that we computed very carefully, and it looks the same except the denominator here, which was this factor here. So they must be equal. And this allows you to identify the row ambiguity here precisely. It is this. So for a given change of variable A equal capital A of Q, the row in Wheeler-DeWitt is that. For omega, we will see later. Okay. So now that we have different prescription for defining the wave function, because we have different possible choice of the path integral measure, we have also different Wheeler-DeWitt equations. Now we would like to know if we get different quantum gravities with same classical limit or not. And that's a relevant question. So to discuss probabilities, first of all, we have to go slowly and define precisely the inner product on each Hilbert space. Each Hilbert space, I mean for each given choice of path integral measure that you use to compute your wave functions. So to do that, I use a trick. I do a change of variable, my wave function as a function of Q0. I define it to be a new function as in terms of A0. I prefer to do that. They are related by this for an arbitrarily chosen function A. And I define my inner product on the Hilbert space, where I introduce a measure mu that I don't know, but I want to determine it. And in fact, you can determine it explicitly by simply imposing, because you know the Hamiltonian for each variable Q, you know the Hamiltonian. It's the one we wrote before. So you impose that it has to be Hermitian with respect to the scalar product. And this gives you a differential equation that can be solved very simply. And you find explicitly what is the measure. It's unique. This is it. So you know precisely what is the measure on each Hilbert space corresponding to each choice of path integral measure. And now the miracle is the following. This mu here, I can say it's square root of mu times phi, and square root of mu times the other phi. And square root of mu times phi turns out to cancel everything which was depending on rho and A, the arbitrariness in your prescription. So the result is totally independent of the field redefinition, at least at the semi-classical level, because I didn't compute it, the correction of order H bar. So the inner product is universal, independent of the field redefinition and the path integral measure, provided the path integral measure is gauge invariant, and it's what we did. Very good. So it suggests that there is a unique quantum gravity. At least at the semi-classical, it's true. Okay. So now we can try to go further. Let's assume, if we disagree, we don't do it. But let's assume, if we are optimistic, that the quantum gravity is unique at the exact level in H bar. Then if I assume that it's not only true at the semi-classical, but it's exact also in H bar, then I can derive what is the remaining ambiguity of omega for things to be consistent. And when you do that, you find exactly what is omega, and it's given in terms of the rho we derived just before. So to summarize, by computing exactly the path integral of Hartle and Hawking, we have been able to derive that it's a unique, there is a unique quantum gravity, and we derive the quantum measure in the Hilbert space, and also we determine the ambiguity in the Wheeler-DeWitt equation. Now, in the last 2 minutes, I would like to present a cross-check of the whole picture by using what we have found on the quantum Hilbert space and the measure, and taking the H bar goes to 0 limit in order to derive the classical Friedman, Robertson-Walker cosmology, the classical cosmology. So let's do that. In fact, with a little bit more effort, we are going to do it not only with a cosmological constant, but when the universe, the closed universe, is filled with an arbitrary perfect fluid of state equation P matter equal W rho matter with arbitrary W. Okay, so the classical cosmology, when W, the state equation, is greater than -1/3, starts with a big bang. There is a maximum here, A max, and a big crunch. That's the classical cosmology in this case. Now, if we want to compare this classical picture with quantum gravity prediction with a wave function, one possibility is to define what is called classical probability. What does that mean? What we mean by classical probability is the duration, the scale factor A, lies in the range A plus dA. Normalized. Normalized means you divide by the total duration of the cosmological evolution. So the total duration is between the Big Bang and the Big Crunch, and you derive the classical probability, just the time you spend at this scale factor between A and A plus dA, and you normalize by the total duration. It's an obvious definition. You use Friedman equation, you find an answer, and you want to recover this thing from quantum gravity. So, since we know that we can use any field we like, we do it with a scale factor. We derive the measure on the Hilbert space. We did it before. It's the same result when you put an arbitrary perfect fluid. And just a remark, in many papers in the literature, they miss the A, they take rho alone, and so you don't recover the classical cosmology, of course. But if you take the correct measure mu, then you derive what is the wave function in this case, because you derive the new Wheeler-DeWitt equation in presence of a perfect fluid. You can generalize it, what we did before. You derive the ambiguities. You do everything similarly in this case. And then you compute when the scale factor is smaller than this maximum value in the classical cosmological evolution. You can compute the quantum probability, just the measure on the Hilbert space times modulus square of the wave function, which is the solution at the WKB approximation level of the Wheeler-DeWitt equation. And when you take h bar goes to 0, it fits perfectly with the classical limit. And when you take the scale factor in the quantum case greater than AM, so it means that it's the classically forbidden region, you find that the quantum probability goes to 0 perfectly, as it must, when h bar goes to 0. Now, the second case is when W is smaller than minus one-third, and then in that case you have a bouncing cosmology. So in that case, since the classical probability was defined by dividing by the duration of the cosmological evolution, and in this case it's infinite, you cannot normalize them. So you take these pseudo probabilities, but you can take ratios of these pseudo not normalized probabilities to define some ratios, which can be understood as relative probabilities. So this is well defined from a classical picture. And in the quantum case, the wave function consistently is non-normalizable, but you can take also ratios of wave function at A and A prime, say, at two different values of a scale factor. And again, it reproduces exactly the classical picture when h bar goes to 0. So everything seems consistent. Now, the conclusion and the summary is the following. We have considered the Hartle-Hawking wave function for the universe in the case where the latter is closed, and in the homogeneous and isotropic case. The system can be seen as a nonlinear sigma model with a line segment of Euclidean time and a target space parametrized by the scale factor. We fix the gauge for the reparametrization of time by integrating over the moduli space, which is just the length of the line segment. We compute the phi df Popov, we use gauge invariant measures, so we fix the gauge correctly. And then we compute for any field redefinition the path integral over the scale factor or any field redefinition of it. We find different wave function, but at least at the semi-classical, the quantum predictions are universal, and the whole story in the h bar goes to 0 limit reproduces the classical limit. Thank you very much.
There is a special reason why you chose a closed universe instead of doing it for
If you close the universe, you can you have something finite when you integrate over the volume, of course, and everything is well defined, and somehow the action is finite. It's just a number. If you get an infinite volume, I guess you have something to do, some regularization or something. I think some people have done it in the past, but at least in this case, things are very well defined. And also, well, we were more interested in the inflationary case, of course, because for ADS, you have something much more powerful than that. We know ADS-CFT. In the DS-CFT is something else, and so we are trying things simpler.
I'm not an expert of this stuff, so let me ask you a heretical question. What have you learned that goes beyond the classical result from all of this hard calculations.
Well, you don't need to take h bar goes to 0. So, in fact, there are many things that you can, in fact, there are debates. I didn't go into the details. I didn't say many things, in fact. Here, this wave function, this expression is the one when this variable A0, the size of the free sphere we live in, lambda A0 square is smaller than 1. I didn't say anything about the case where lambda A0 is greater than 1. In fact, you can do the computations, and there are two groups in history, and there are debates about that. In fact, depending on the number of instantons you are going through, here I chose a prescription in this case where I'm going through the two instantons. So this is a group, Vilenkin, Linde is doing that. But Hartel and Hawking are going through a single instanton. So depending on the choice of prescription when you go from Lorentzian to Euclidean, you find a totally different result. Because here, what we are interested in is not the case where lambda A0 is smaller than 1. It's when lambda A0 is greater than 1. We live in a big universe. And when you do the case greater than 1, depending on the instanton you go through, you get totally different picture, totally different prediction. So, if you take the case treated by the prescription of Vilenkin and Linde, you predict that inflation is natural. While if you take Hartel and Hawking prescription, which you predict that the cosmological constant should be 0. So, it's very, very important. So, how to differentiate which one is correct, if one is correct? In fact, the correct way to do it, because I didn't say it, but okay, I say more, the Euclidean path integral actually is not well defined. It's ill-defined, it's totally divergent. And it's obvious because the Lagrangian here, where is the Lagrangian? Okay, you have a wrong kinetic term for the kinetic term, for the scale factor, and the scalar potential is unbounded. So the path integral is totally divergent. So how can we compute something? In fact, the correct way to do it is not to use the Euclidean action, but the Lorentzian path integral. And people tried that a few years ago. And we are doing it now. So we have not finished, so I don't discuss it. But we did it. And when you do correctly the things in Lorentzian, okay, I say it, we find that Linde and Vilenkin are right. So the prediction is that the natural thing is inflation and not 0 cosmological constant. So that's the thing that you are really interested in. You want the scale factor to be bigger and in the regime where you are not, where you can predict if there is inflation or not. That's the point.
So thanks for a nice talk. So I think that my question is that in what we have learned in string theory is that you cannot have a situation where lambda is a parameter in your theory. So lambda should be promoted to field or something, function of fields or so on. Whereas that was not the original picture of Hartel-Hawking, I think. So if you promote that to field or something which depends on fields and some kinetic term for those fields and all that, what do you learn from this, if any? And do you get any of the things that we have learned in the context of quantum gravity lessons from string theory? For example, the fact that as lambda goes to 0, you have a tower of states and this and that. How does this fit with this picture?
Okay, I don't know if I'm going to answer your question. I just make comments. So the natural thing, actually, they did in Hartel-Hawking in the original paper. They take lambda constant, and in the second part of the paper, they take a scalar field, which is conformally coupled. Of course, it's because you can do computation easily, but you can generalize this thing with an arbitrary potential. And of course, the good thing to do is to try with Starobinsky, of course. So, if the question of sign that I was discussing qualitatively here is the sign of Linde and Vilenkin, then I suspect that the natural prediction of this thing when you use a scalar field with a Starobinsky potential that you put by hand, the natural thing will be to predict that the wave function modulus square will be much bigger when you start with a scalar field along the plateau. So it can be interesting to say that the initial condition are
Sorry,
more...
what do you mean by that? You have to give a potential, right?
Yes, you put it by hand. Here you put everything by hand.
Oh, no, this is my whole point. I mean, I'm trying to avoid that. So, suppose let me ask you a specific question. Suppose I just take a massless scalar field of the type we see in string theory, like Calabi moduli.
A massless scalar field?
Yeah, yeah.
Yes.
Like the moduli fields we see in string
Yes.
theory.
Yes.
What does this give you in that context? Or in the ADS context that we know in holography, if you try to do that in this context, what would you learn?
In this case, actually, we did it 2 years ago. We gave up. What you get is a deformation of this theory because you have only kinetic terms, of course. So you will have a different action, and which depends on A0, the scale factor, and phi 0, which is the constant value of your, or the asymptotic value of your scalar field. You get a deformation of a story, and I think, and you find something, it's not normalizable, because phi 0 is a modulus. I don't remember what was the story. You don't get something very, very interesting, I think.
Okay, thanks.
Okay. Do you meet the issue of the grip of ambiguity when you do the gauge phasing?
Sorry, can you repeat the question?
Do you meet the issue of the grip of ambiguity when you do the gauge phasing?
Sorry. Sorry? You said that there is an ambiguity with Fadayev-Popov?
Yeah, grip of ambiguity when you do the gauge phasing. Yeah. In the QCD, we have the issue when doing the gauge phasing.
So, I don't know. I don't know. I don't know the answer. I don't understand.
Okay.
Well, what kind of ambiguity? Because here you compute the thing and you find, well, the computation we do, where is it?
In the QCD case, if we're naive to the body purple, naive use the naive purple method, then it determines should be 0 if you do not consider the weak covering perturbation theory.
Sorry, I don't understand.
Okay.
Today I will talk about atlas measurements of the CP evaluations and the ready case processes. And we focus on these processes with using the beauty methods. So first of all, I would like to introduce B-physics in Atlas. We have very rich B-physics and very rich program. We use large amount of data that were collected both in run 1 and mainly in run 2 when we benefit from the 139 inverse femtobarns. Unfortunately, not all of the B-physics analyses are connected, at least hiddenly connected with SUSY particles. So today I will discuss only about 2 analyses. One of them is the CP evaluation in BSJ Psi-Phi, and the second one is the observation of the B or BS decaying into 2 muons. Both analyses uses events that were collected with a mixture of triggers that are based on dimuon identification with the PT thresholds of either 4 or 6 GeV. As I have only 2 analyses, I can use my time to go into some details to describe the procedure of both analyses. So let's start with the first one, the measurement of the CP evaluation phase phi S in the BSJ Psi-Phi decay. So we know that in this decay the CP evaluation appears, and this channel is very sensitive to some deviations or very sensitive to new physics. How we know that the standard model can very precisely predict the value of the phi S, and this value is connected with the CKM elements, and we can see here. So if in case we see any potential deviations from this value, we can expect that our expectations that the mixing of the BS and BS bar, we can expect that this is not all that we know about this mixing, and we miss some additional box diagram describing this decay. In this analysis, we are not interested only in phi S. We are also interested in other quantities like lifetime quantities, delta gamma S and gamma S. They are not very sensitive to new physics. However, it's very interesting to measure them because we can test other theories. Atlas is not only one experiment measuring the CP evaluating phi S, phase phi S. Other experiments also measure it. So this is the situation before the LHC run 2. The Atlas is the brown circle. We see also in a white ellipse the combination of all experiments results. And the very thin black box is the standard model prediction. So you see that the prediction of the phi S is very precise with respect to the measurements of experiments. Okay, I will just shortly introduce how we select our data. This will be really quick. In this analysis, we use the proton-proton collision data collected between 2015 and 17. And the obtained result is statistically combined with run 1 Atlas result. I already discussed how we select our data and how we use our triggers. And we keep only events in this mass window of BS. Very important thing that we do is the angular analysis. We know that our final states is an admixture of CP-hot and CP-even states. We also expect that our decays of BS to GIPSI-Phi is polluted by the BS to GIPSI-KK, so we also expect that our data contains this channel. We can distinguish these final states through the time-dependent angular analysis, where we use the 4 types of amplitudes. These 3 are connected with the CP-hot and CP-even states, and the AS is connected with the non-resonant S-wave contribution. The definition of the three angles can be visible in this figure. Yeah. Another important input to our analysis is the opposite side tagging, because we know that the BS can freely oscillate between BS and BS bar, as already mentioned in the first the motivation slide. However, what we know, we only detect the final states. I mean, the phi is decaying into kaon and GIPSI decaying into meon. So we don't know what was the initial state of this object. To do it, we use information that at LHC the B quarks are created in pair. So we try to reconstruct, or at least use tracks from the opposite sides. From the charges, we can estimate the probability of this object being B or B bar quark, and from that we know, or we have some probability of knowing of the initial state of this BS or anti-BS. To tag our events, we use muons and electrons, as well as also the jet charge. This looks very nice. However, this tagging needs to be somehow calibrated, because we need a self-tag channel to estimate the probability of the tagging and then use it for BS. To calibrate, we use B plus to GIPSI-K plus channel. And here are some results of the calibrating channel. We do not use only leading lepton. We construct some object like a jet. In that object, we calculate the weighted charge of all tracks, and then this gives us the probability. From this probability, we can easily get the probability to tag BS meson. In this plot, the red and blue are the weighted charges of the opposite sides, leptons with their tracks. And the black curve is an tag probability to tag a BS meson. From this table, we can see that mostly 20% of our events are tagged. Other events have probability 50 to 50 to be BS or BS bar. Okay, so using all this together with other inputs, we can define our likelihood, and we perform unbound maximum likelihood fit. We do not use any lifetime cut or any additional cut, so we need to very well describe the peaking background. Because we do not have very good particle identification. As I said, we do not have any strict cuts, so we need to also very well describe the combinatorial background. We perform the fit in 5 dimensions: mass, lifetime, and 3 angles. And we weight our likelihood with the trigger efficiencies. This is this term. The peaking background contributions comes from BD to GIPSI-K star, BD to GIPSI-K pi. This is the non-resonant one, and also the lambda B decaying into GIPSI-K on and proton. So Having all this together, we have results. We see very well separated local maxima in the likelihood. However, these are for the delta parallel and the delta perpendicular. These are connected phases with the amplitudes. This split of the maxima has doesn't change or has no impact on the value of this the most important parameters, that are the phi-s and the lifetime parameters. These are the same for both strong phases maxima. Okay, so these results are just for run 2. When combining it with run 1 results, we obtain these values. The important, very interesting is to look at it in the phi-s delta gamma s plane, where the blue circle is run 1 result, the green one is for run 2, and the red one is the run 1 and run 2 combination. You see that we are in the delta gamma s, we are one or 2 sigma far away from the prediction. However, for the phi-s, we are still in agreement with the predictions. Okay, this is additional analysis. It will be very short. This discuss the possible prospects for high luminosity LHC. We expect some very good improvements for tracking, and also improved trigger scenarios. With this, we can expect this cyan-colored results that will be very precise, and then we will be able to see and say if we really perform that standard model is right or not. Okay, the second promise analysis is the search for BS2 mu mu. We know that this decay is the flavor changing neutral current that is very highly suppressed in standard model. So again, any deviations can predict some theories beyond the standard model. We see, and it's the possible way how the B or BS can decay into 2 muons, and if the standard model is not right, we would need to include some other particles like supersymmetry particles or dark matter and so on. So this is the reason why this measurement is also very important. To exclude most of the detector effects, we calculate the branching ratios relative to the reference decay mode, that is BS2 GPSI K plus. B plus 2 GPSI K plus, and so this is what we measure. All these are used from the heavy flavor average group or the PDG, and we just measure the number of candidates for BS2 mu mu and GPSI K plus. Okay, I will skip the data selection. This is very similar to the previous analysis. We use, again, the triggers with dimuon identification. And a very important thing is that we need to raise our signal from the background. So here we use very tight cast on LXY to be larger than 0. We also need to very precisely describe the background. So we have 3 types of backgrounds. First of all is the partially reconstructed B hadrons. This is mainly expected at the left area from the expected peak. Then we have the peaking background. This means that both hadrons from the BS are misreconstructed as muons. This is very well simulated and fixed in the mass fit. The last background contribution is the continuum background, and this background is very well reduced by the BDT that we use 15 variables to reduce this continuum background. Okay, so here's the results of the mass fit, and this is the output. The data are the output of the BDT. Here I show only one BDT bin of 4 bins. So in red, this is our signal, both BS to mu mu and B to mu mu. We see that we have a very large amount of partially reconstructed BS candidates, and then we have some peaking background that is small, relatively small with respect to the signal. Using this fit and also fit to the B plus 2 chip K plus, we can calculate the BS to mu mu and B to mu mu branching ratios, and here is the final results. Here's in a plot that we see the run 2 result. It's in a blue ellipses, and the combinations is in a black. And when using, then we can also extract the values from the fit. The combined measurements is still compatible with standard model, but at the level of 2.4 sigma. So we expect additional data to see if we will move closer to standard model or far or away. LHC also provides the combinations of the measurements from Atlas, CMS, and LHCb. So when the total combinations is a bit closer to standard model, but it's the changes is I would say small, still 2.1 sigma away from the standard model. Okay, so this is my last slide. To summarize, I presented the CP evaluation with GPSI and search for BS to mu mu analysis in the latest LHC and 2 data. We saw that we are still more or less consistent with Atlas Run 1 results, and in FIS and we are in FIS we are still consistent with the standard model prediction. The BS mu mu shows some tensions, but we need more data to see if we are right with these tensions. Okay, that's all from my side. Thank you very much.
So thank you for the interesting talk. Any questions, comments? Sakis?
Could you please go back to slide number 20? Slide below. Is this minus?
Yeah, this is minus.
Minus branching ratio?
Because you know, after the BDT and so on, the fit is not able to fit the BD to mu mu. So BS mu mu, it shows very nice peak. However, it's not visible very well here. But we have also four bins, and then there's some in this region the fit undergoes the zero. So this is the reason why we present for BS. It's clear that we can present the value, but here we can present only the limit of the branching ratio. I mean, it's in this y-axis.
Okay.
And do you expect any update on these numbers because they look?
There are some one analysis using the full run 2, because this analysis uses only 2015 and 16 data. We are expecting that the full run 2 analysis will be published soon, but that's all I can say now.
I see in gamma S and a bit in delta gamma S, there's a a disagreement with the measurement from LHCb and CMS.
Yeah.
What are the? Do you suspect any? What are the systematics affecting these two?
Okay.
Should we be worried?
Yeah, we are very well aware of this, let's say, problem that we are far away from in the lifetime. We are away from LHCb and CMS results. We performed lots of systematic checks and so on. I can also provide systematic uncertainty table. So looking into this column, we see that the largest, there are lots of contributions, but some of them are the largest one are the time efficiency, I would say, the inner detector alignment, and also we use the per candidate error in our fits. So the lifetime per candidate error is split into PT bins. So this time resolution in PT bins gives us some additional systematics. So in the results, I think that the gamma S values exceeds the systematics exceeds the statistical uncertainty right now.
Okay. Okay. And I saw there's a large systematic called fit bias. Do you correct for the bias and then assign a systematic? How do you remember how this is done?
You mean, yeah.
Yeah, the last one, yeah.
Yeah, this is the corrections if we use wrong fit model. So we generate on Monte Carlo, then fit it again and compare it with the input for the toy Monte Carlo, and so on.
So your standard fit gives an unbiased result. It is not about your standard. It's about alternative fits.
Yeah, we also performed some alternative fits, but the deviations were not so large to be included even to the systematics.
Any other questions? So, let's thank. Model with the gauge flavor we want. Because there's something went wrong, so could you please correct?
No, it's okay. Just close this one.
Okay.
The middle is the pointer.
Yeah.
And
next and
yeah.
Okay.
Next and back.
Okay. Okay. Can you hear me? Okay. Thank you for introduction and thank you for giving a chance to organizer. I'm Ioannina from State University in Japan, and today I will give you a seesaw mechanism in R-parity valuing scenario in SUSY standard model with discrete symmetry. And this discrete symmetry is motivated from the baryon number conservation instead of R-parity. Okay. First of all, I will give you a motivation, my presentation. First of all, the supersymmetry is one of the promising ideas to explain the naturalness problem. In general, SUSY standard model have baryon and lepton number violating operators, which induce the fast proton decay, such as following this diagram. R-parity can prohibit such dangerous operator at the renormalizable level. On the other hand, we have the dangerous operators such described by Planck suppressed operators and at the non-renormalizable level, and which contributes to the proton decay again. In this context, in order to prohibit such dangerous operator, the alternative class of the discrete symmetry to R-parity have been considered, and there is some class such as baryon triarity and proton hexarity, and so on. And there is a phenomenological application based on this discrete symmetry, and we can realize the Yukawa hierarchy and neutrino mass and mixing angle based on this discrete symmetry. Another aspect of the standard model is flavor problem. As we know, quark and charged lepton has a huge mass gap between the generation, and we don't know the origin of the small mixing angle. In addition to the quark and charged lepton, we don't know the origin of the tiny neutrino mass. So we have a serious question in particle physics, what is the origin of the flavor observable? Today, I will give you a SUSY standard model with a discrete symmetry, so-called matter triarity. I repeat that this matter triarity is motivated from the baryon number conservation. And under this symmetry, we construct the seesaw mechanism. And due to the R parity violation in our model, the MSSM neutralino such as Gaugino and Higgsino contribute to the effective active neutrino mass matrix. Secondly, I will construct the flavor model based on the Frogat-Nielsen mechanism. We embed the matter triarity into the gauge flavor UX symmetry. Then the flavor charge is restricted from the phenomenological and theoretical argument. Finally, I will give you a phenomenological aspect of our model, such as the neutrino-less double beta decay. As a brief summary, I will give you a unified model of flavor symmetry and the baryon number conservation in the SUSY standard model with matter triarity. First of all, I will give you a seesaw mechanism in our model. I repeat that the matter triarity is introduced as an alternative to R parity. This discrete symmetry requires 3 generations of the right-hand neutrino, and we show the baryon and lepton number violating operators under the R parity or matter triarity up to dimension 5. We can see that the table, the baryon and lepton number violating operator can be prohibited and under the matter triarity. So we can ensure the proton stability. Another aspect of the matter triarity model is no Majorana mass. This is because the right-hand neutrino is charged under the matter triarity, so we don't have the Majorana mass, such as bilinear operator in superpotential. However, we obtain the Majorana mass from the lepton number violating operators, denoted kappa, and this Majorana mass comes from this operator after the right-hand neutrino acquires the vacuum expectation value. In fact, the right-hand neutrino acquires the vacuum expectation value from the discussion of the neutral scalar potential. If we evaluate the extremum condition, we obtain the left-handed neutrino. We can find the left-handed neutrino vacuum expectation value will vanish if neutrino-Yukawa coupling is so small. On the other hand, right-handed neutrino acquires the vacuum expectation value of the order of soft SUSY breaking scale from the extremum condition. So we obtain the Majorana mass where right-handed neutrino waves, which is associated with the soft SUSY breaking scale. Then we study the neutral fermion mass matrix. This is given by 10 by 10 neutral fermion mass matrix because of the R parity violation. So in our model, the neutrino mix with the MSSM neutralino such as Higgsino and Gaugino. Then we can decompose into the block mass matrix, and we can read the effect of the R parity violation from this MX. It depends on the right-handed neutrino waves. So we can realize seesaw mechanism in our model. In fact, the neutral fermion mass matrix can be diagonalized by proper unitary mass matrix, and which is defined by the ratio between the block mass matrix. And then we can obtain the seesaw formula in our model. This is given by two parts. First one is the same with the type 1 seesaw mechanism, and the second one comes from the mixing with the neutralino, MSSM neutralino. So we emphasize that in our seesaw scenario, in our seesaw mechanism, two contributions can be divided independently. So by using this seesaw formula, we will construct the gauge flavor U1X model. First, we have to note that the alternative to R parity, such as matter triety, is introduced as a remnant of the gauge symmetry. So we can identify this gauge symmetry with the flavor symmetry. Following this discussion, we embed the matter triety into the gauge flavor symmetry, and in this construction, X-charge flavor charge consists of matter triety charge and generation depending parameter. Such flavor charge is constrained from the theoretical and phenomenological argument, and in the theoretical point of view, the X charge should satisfy the anomaly cancellation conditions. In the Green-Schwarz mechanism, the anomaly coefficient, which is given by the X charge, should satisfy the following conditions, and we fix the Katz-Moody level, which is determined by the algebraic procedure, fix equal to 1 for non-abelian standard model gauge group. On the other hand, we regard Ky, hypercharge Katz-Moody level, as a parameter to solve the anomaly cancellation condition. Then we introduce the Frogat-Nielsen mechanism to realize a fermion mass hierarchy. If we introduce a standard model gauge singlet, so-called Flavon, we obtain the flavor symmetric superpotential, and we can realize hierarchical equal coupling after the flavor symmetry breaking. If we assign the mass hierarchy and mixing, the X charge or K phi I, this is the generation depending parameter, can be restricted from the phenomenological requirement. For example, in an up-type quark sector, X charge should satisfy these conditions. We leave the degree of freedom of parameter Y, and this is responsible for the secant mixing matrix. So we can conclude K phi I, generation depending parameter, is determined except the degree of freedom of such parameters. And let us move on to the neutron sector. I repeat that M effective active neutrino mass matrix can be divided into two parts, lighter neutrino contribution and neutralino contribution. Each contribute can be evaluated in terms of the flavor charge, and we can find the matrix texture can be determined by the flavor charge of lepton doublet, KLI. If we define the ratio between them, we can fix the dominant contribution to the M effective. So if R is smaller than 1, then the lighter neutrino contribution dominates to M effective. Combining with the mass hierarchy of the active neutrino, we can find that flavor charge assignment can be classified by dominant contribution to M effective and the mass hierarchy of active neutrino. We have to ask the Higgs sector, what is the origin of the supersymmetry Higgs mass? Why it is electroweak scale? Why mu term is electroweak scale? In the superpotential, the mu term is dimensionful parameter, so it is naturally scale is of the order of Planck scale, cutoff scale. In order to obtain the correct electroweak symmetry breaking, we introduced the Giudice-Magellan mechanism. In this mechanism, the non-minimal coupling in the Keller potential induces the effective mu term. This is associated with the soft SUSY breaking scale. If we choose the flavor charge of mu term as negative, we obtain the electroweak scale mu term associated with soft SUSY breaking scale. This is because the mu term in the superpotential is prohibited due to the holomorphy of superpotential. So we can control the Higgs mass hierarchy due to the holomorphy. We set the soft SUSY breaking scale from 1 TeV to 1 PeV, and it is characterized by parameter W. The 1 PeV soft SUSY breaking scale is slightly large to explain the naturalness problem, but we would like to check the compatibility with anomaly cancellation conditions and phenomenological requirements, so we choose this range. Okay, in this slide, I will give you a procedure of numerical analysis. First of all, we have flavor charge, and in the following discussion, we introduce the extra Higgs field to solve the anomaly cancellation condition, but such extra Higgs field does not contribute to the low energy effective field theory, and because such field will decouple from the theory. If we assign the Fermi mass hierarchy and so on, phenomenological requirement, we can reduce the flavor charge to a few free parameters. And we leave the flavor charge, some flavor charge. And this remaining flavor charge can be determined by the anomaly cancellation conditions. And then if we solve the anomaly cancellation condition, we obtain the some flavor charge assignment. And this assignment can be divided into the 4 classes, depending on the dominant contribution to the M effective and hierarchical spectrum of the active neutrino. We note that the flavor charge of we note that flavor charge of right-hand neutrino is undetermined. So if we choose the flavor charge of right-hand neutrino, we obtain the right states of the stellar neutrino. Okay, finally, I will give you the phenomenological aspect. First of all, we check the neutrino observable. If we fix the flavor charge, in other words, few parameters, we can obtain this flavor charge is characterized by this parameter set. And we use the model number 4, and this is characterized by right-hand neutrino dominated case and normal hierarchical mass spectrum of active neutrino. And the soft SUSY breaking mass scale is 20 TeV. If we fit the vacuum expectation value and on the one factor to minimize the difference from the observable of neutrino sector, and we can check the consistency with the neutron mixing data. If we choose the other flavor model, we can realize the similar result of neutron sector. Okay, finally, I will give you the behavior of neutrino less double beta decay under our model. If we choose the flavor charge assignment, we obtain the right state of the stellar neutrino. And such stellar neutrino contributes to the neutrino double beta. And in this discussion, the effective Majorana mass, which the decay lifetime of the neutrino double beta can be evaluated by the effective Majorana mass, and this comes from the active and stellar neutrino mass contribution. As we know the contribution from the active neutrino, we have to check the stellar neutrino contribution. Then such contribution can be determined by the stellar neutrino mass and active stellar mixing. And we can evaluate them in terms of the flavor charge. And we can find this is characterized by some parameters, and this law characterizes our flavor model from the observation of neutrino double beta decay. We show the comparison with the neutrino double beta decay. This plot shows the flavor charge depending flavor charge assignment and minimum of rho and maximum of rho. We can see that the different range of the mixing angle can be predicted in our flavor model. This is in normal hierarchical case, and left panel shows the right-handed neutrino dominated case, and right panel shows the neutralino dominated case to M effective. In inverted hierarchical scheme, the situation is more clear more slightly clearly. This is because the Lagrange neutrino dominated case, the mixing angle is not suppressed. On the other hand, in neutrino dominated case, the mixing angle, we have the flavor charge assignment suppressing the mixing angle. So we can conclude our flavor model can be characterized by neutronous double beta. Okay, I summarize my presentation. First of all, I repeat that the matter triarity can prohibit the baryon violating operators, baryon number violating operators instead of alparity. So proton longevity is ensured. Then we construct the seesaw mechanism following this seesaw formula, and we can realize the Yukawa and Hicks hierarchy. And then we obtain the anomaly-free flavor charge assignment. Our flavor charge assignment can be distinguished from the observation of the neutronous double beta decay. My presentation is all. That's all. Thank you for listening.
Thank you for the talk. If I can make a comment. It was one of the not so many talks during the conference really dealing with details of the supersymmetric models.
Yeah.
So any questions?
Maybe I can shout. So can't you already forbid proton decay with flavor symmetry? Do you need this M3 in addition?
Sorry.
Yeah. So I think you can already forbid proton decay with a flavor symmetry, right? You don't necessarily need the M3. So your flavor symmetry alone is not sufficient to forbid proton decay? No, forbid. Is your flavor symmetry not sufficient to forbid proton decay? Because you introduced this M3 as well. I think you have to go. I think you have to go to microphone.
Okay. Where?
No, to the microphone because I couldn't hear you.
Switch on the microphone.
Okay, okay. In our model, the matter triarity, discrete symmetry can prohibit the proton decay. So.
Yes, this I got. My question was, is the U1 prime symmetry, the U1X symmetry you introduce, not sufficient already to forbid proton decay?
Not sufficient.
Yes, that's the question. Is it sufficient or is it not sufficient?
Yeah. It is sufficient because this is because the.
So you don't need this M3 in addition. It's somehow optional.
You mean alparity is sufficient? You mean sorry, I cannot answer your question.
You said you introduced this M3 symmetry instead of R parity to forbid proton decay.
Yeah.
Yes. Now, in addition, you introduce a U1X flavor symmetry.
Yes.
So, if the U1X flavor symmetry is already enough to forbid proton decay.
Enough.
You said it is enough, right?
Yeah.
Yes. Then you do not really need the M3 symmetry in addition, right? Or is there any reason why you want to have in addition this M3 symmetry?
Sorry, I can not find your question.
Yeah.
Any other questions? I think I understand the question, but maybe it's better to discuss it. Okay.
Thank you.
Thanks, speaker again. Okay, so our speaker is now Anil Tapa, neutrino mass models and its links to flavor anomalies.
Thank you. Good afternoon, everyone. My name is Anil.
I'm a postdoc at University of Virginia. Today I'll talk about neutrino mass model and how you can link the neutrino mass model to different flavor anomalies. Whenever I say flavor anomalies, I'm talking about RK star, G-2, RDRD star. So, and this work is based on these two papers. So as you know that I guess one of the major drawback of standard model is in the standard model neutrino mass is precisely 0, but experiment shows that neutrino flavor mix. This flavor mixing is given by this UPMNS unitary matrix, which implies that neutrino mass is not 0. So we require new physics to beyond the standard model to explain the neutrino mass. So this UPNMS has all these mixing parameters, which is given by this table, as you can see, and we also do not know whether the neutrinos are normal ordering or inverted ordering. We do not know what quadrant this theta 2, 3 lives, and we do not have any information of delta CP as well. And this table is I obtained from this new fit, global fit 5.1. So how do you generate neutrino mass? So there are properly two schemes to generate neutrino mass. One is tree-level system mechanism. The alternative way is radiative scheme. Okay. So to talk about tree-level system mechanism, the light neutrino mass is induced by Weinberg dimension 5 operator LL55. Once you have this kind of operator, you can integrate out this new physics, which I call it lambda, to suppress the neutrino mass. And given by this phi, vacuum exponential of phi divided by lambda new physics scale. Okay? And popularly there are three types of system mechanism, type 1, type 2, and type 3, depending on what kind of new particles you add to the standard model. So for example, if you add a singlet fermion here, this is called as type 1. If you add a triplet fermion, it's called type 3. If you add a triplet scalar field, it's called type 2. But at the end of the day, the effective operator is LL55. So in this kind of framework, if you take the couplings to be of order 1, the new scale of this new physics can be rather large, of 10 to the power 14 GeV, to explain the neutrino mass. But alternative way to tree-level system mechanism is radiative scheme, which is the main focus of my research. So for the radiative neutrino mass generation, neutrino mass are 0 at tree level. So in this kind of framework, right-handed neutrino may be present and maybe not as well, depending on what kind of model you are working on. So in this kind of framework, the small finite mass are generated at quantum correction at 1 loop, 2 loop, even higher order. But if you go more than 4 loop, every loop you have, there is 1 by 16 pi square suppression. If you go more than 4 loop, the neutrino mass becomes too small. Okay. Typically, in this kind of framework, you involve at least 2 scalars, and that will lead to lepton number violation. For example, one of the simplest example is Z model, which is shown in this diagram, where in Z model you have a second Higgs doublet, which is this H2, and a charged singlet, which is eta plus. Okay. Now, once you have these two scalar fields, you can draw a diagram like this, and this precisely this scalar coupling, cubic coupling, breaks the lepton number by 2 units. Thus, since it is breaking the lepton number by 2 units, you can generate Majorana mass. Now, smallness of this neutrino mass is explained by loop suppression factor. Since it is a 1 loop, there is a 1 by 16 square suppression. And furthermore, as you can see in this diagram is proportional to this chirality flip. This chirality is basically, this diagram is proportional to charged lepton mass. And in this kind of framework, the new physics, that the new scale that you introduce may lie at TeV scale that can be probed at collider. So there are various plethora of radiative mechanism. So we can categorize into 2 types, type 1 and type 2. Okay, this type 1 is basically can be obtained by the effective dimension 7, 9 operators with delta L, which is lepton number equal to 2 selection rule. Basically, if you have at least 1 standard model particle inside the loop, you can cut this diagram, which means that you can effectively integrate out the new fields that you introduce, and it will induce this such kind of D equal to 7, 9, 11 operators. And this is called type 1. One example is G-Babu model, where you introduce a singly charged scalar and a doubly charged scalar, and you generate neutrino mass at 2 loop level by dimension 9 operator. This kind of classification is done by Babu and Leung, furthermore, and then by Smith, Volkas, and all. So the second type is type 2. So in the type 2 radiative mechanism, basically, if you do not have any standard model particle inside the loop, it is called as type 2. So if you do not have any standard model particles inside the loop, you cannot, no matter how you cut the diagram, you cannot generate dimension 7, 9 standard model operators. So that is what we call type 2 mechanism. One of the popular examples is, of course, Skotonic model, where you have this eta naught is a doublet scalar, and n is a fermion, a Majorana fermion. So both of these are G2 odd in this model. Since they are both of these are G2 odd, the lightest among these two particles can be a dark matter candidate. If it is a dark matter candidate, then it requires TV scale new physics. But as you can see, this diagram, there is a flip, but the flip is because of this Majorana mass term. So since there is no chiral separation in this kind of diagram, so the new scale can be rather large if you want. Okay, I think G-2 of muon does need no introduction. So basically the intrinsic magnetic property of lepton can be characterized by this G factor, and the deviation of this G factor is basically anomalous magnetic moment. Okay, it is purely quantum nature of elementary particle. In the standard model, the contribution comes from this QED, weak and hadron, which is shown in this diagram. But at the end of the day, the Fermi level Brook level combined shows that there is a 4.2 sigma deviation from the standard model prediction. Okay, and which I am trying to address in the model I am going to talk about. So B anomalies. This is just one slide for the B anomalies. So B anomalies I categorize into B2S anomalies and B2C anomalies. Basically B2S is observables I am interested in is RK star. It is a neutral current process. It happens at one loop in the standard model, as shown in this diagram. RK star is basically defined as the ratio of B2K mu mu over B2K EE. And in this kind of framework, the new physics can be rather heavy. When I say heavy, it is of order 30 TeV. Okay? And then the experiment shows that there is 3.1 sigma deviation from the standard model prediction. Similarly, B2C anomalies, there is RDRD star. That is what I am interested in. And this is charge current process. It happens at tree level. There is a 3.4 sigma deviation from the standard model prediction. RDRD star is basically B2D tau nu over B2D L nu. And the new physics must be light. When I say light, of order TeV scale. Okay? So what is the idea? What is the goal of our work? So the goal of our work is to construct a neutrino mass model where the new physics scale is at TeV scale, and you can simultaneously, at the same time, explain RK star, RDRD star, and G-2 of muon and electron. Okay, and of course, gives a fit to the 6 neutrino oscillation observables. So this is a cartoonic picture of here where neutron mass is interconnected with G-2 of electron, muon, RK star, and RDRD star. Of course, in this kind of framework, since you have new scalar particles or new particles at TeV scale, you have a plethora of scalar implication, and then the same parameter that gives delta G-2 will also lead to Higgs to mu mu, which was shown by Krivlin et al. So what is the idea? So the framework for the anomalies, and anomalies is basically you introduce leptoquarks, which has been popularly studied in the literature, where you have this S3 leptoquark with a triplet under SU2 with hypercharge 1/3. S1 is a singlet with hypercharge 1/3. R2 is a doublet with hypercharge 7/6. And it is been shown, it is widely known that S3 can explain, for example, RK star. S1 can explain RDRD star. R2 also can explain RD star. But none of this leptoquark by itself cannot explain both of them simultaneously. So the idea is basically combine these two and try to generate neutrino mass. And notice also that S1 and R2 can also induce G-2 of muon. Okay, so you pair these two leptoquarks, at least two leptoquarks, to generate neutrino mass. Once you are trying to generate neutrino mass, the neutrino mass will basically force it to have some kind of flavor structure. That flavor structure is highly constrained. Okay, and this kind of framework can be tested at LSC and as well as in the process such as tau to mu gamma. So there might be some lepton flavor violating prediction. So here I divide into the three classes: class 1, class 2, and class 3, depending on what kind of particle you add. For example, in class 1, you have S1 leptoquark and S3 leptoquark. S1 can explain RDRD star, but not RK star. This model 2 can explain RK star, but not RDRD star, or G-2. But this class 3 model, where you have three particles, R2 and S3, for example, R2 can explain RDRD star, S3 can explain RK star, and basically you require one more particle to connect into the loop and break the lepton number, and then you generate neutron mass. So I'm not going to go through each and every detail, but let me just focus on the model 7, which has S1 leptoquark, R2 leptoquark, and some new field C. Okay, where S1 is a singlet field, R2 is a doublet with hyperscalar 7.6, and the neutrino mass you can generate at 2-loop level. This is the 2-loop diagram. Where this is R2, this is a doublet field with a component R 5/3 and 2/3. These are the charged. S1 is a singlet. This is a triplet field. Once you have these 3 fields, you can break the lepton number by 2 units. S1 is in this diagram, and you can generate neutrino mass. So at the end of the day, neutrino mass, since it is 2-loop, it is suppressed by 16 pi square whole square. Okay, this G is just the SU2 gauge coupling, and this I is just a loop factor, and then there's a various flavor structure. Okay, where YL, FL are the flavor structure of the leptoquark coupling with the fermions. So we look at the flavor structure and try to explain everything, all the BFV physics as well as neutrino mass. So here is one typical flavor structure that I am showing here. For example, this FR21 and FL21 can explain G-2 of electron. FR21 and FR31 can explain RK star through electron. FR33 and FL23, when I say the first index is quark flavor, the second index is the lepton flavor. Okay, FR33 and FL23 can explain RDRD star. For in this YR Yukawa coupling, YR32 and YL32 can explain G-2, and the rest of these 3 Yukawa couplings are required to satisfy this neutrino fit. And various, you can see there are various zeros. You require these various zeros just to satisfy lepton flavor violation. Okay, this is one of the minimal texture you can have to explain all of these in the same framework. Now you can ask like why you have too many particles, but notice that no matter if you just take out any of these particles, then you don't have neutrino mass. Okay, all of these particles are required to generate neutrino mass. Of course, since there is a Gauge boson in the diagram, the figure itself is just a one typical diagram. There are many other diagrams which one has to consider and calculate, which I show here. So there are particularly 8 diagrams which you have to calculate all of them, sum of together, and so that it is gauge independent. So since we are doing a flavor physics, there are various experimental constraints. For example, this Li to Lj gamma, which is mu to E gamma, tau to E gamma, tau to E gamma, so on, mu to E conversion. G to tau tau decay is basically happens at 1 loop level. Ray demission decay, DD bar mixing, bounce from kaons, and collider constraint like pair production bounce and dilepton bounce. I'm not going to go through each and every detail. I'll just talk about this highlighted constraints. And this is one. This is for the lepton flavor violating Li to Lj gamma. So notice that the same diagram that gives muon G-2 will also give rise to Li to Lj gamma by just removing its photon. And as you can see, this diagram is enhanced by chirality flip. So here there are 2 columns. One is without chirality flip, the other one is with chirality flip. So they are this is quite a strong constraint. For example, mu to E conversion is a very strong constraint of 10 to the -6 for a TeV scale leptoquark for the product of Yukawa coupling. Similarly, there are various constraints from kaons, K along to EE, K along to E mu, and so on and so forth. And to talk about collider physics, I'm mainly going to talk about pair production bound. Basically, leptoquark can be pair produced by gluon-gluon fusion process, as shown as in this diagram. This is just one typical diagram, and then leptoquark will decay into leptons and quarks. So if it happens, then I show this plot shows basically as a function of branching ratio and mass of leptoquark. For example, if the leptoquark decays into jet electron, and then the bounce is quite severe of 1700 GeV for a branching ratio 1. Similarly, there is a dielectron bounce, which is the non-resonant production of pair of leptons, which is shown in this diagram as a function of Yukawa coupling and then mass of leptoquark. For example, if it goes to first generation, the bounce is quite strong, as you can see here. And as I was telling you before, to explain RDRD star, you require somewhat lighter mass of order 1000 to 1200 GeV. That means the Yukawa coupling are quite strong. So this is the result for RDRD star. Here first I choose the R2 leptoquart to be 1 TeV, and I show the plot as a function of 2 Yukawa couplings. As you can see, this is the allowed region. As you can see, you require somewhat larger Yukawa coupling to explain RD star. And these various other set of regions are the exclusion region from different experiments. For example, this PP2 tau tau is non-resonant production. This tau 2 E gamma is just lepton flavor violation, BCC of tau nu, and so on and so forth. And this is G2 tau tau. And as you can see, this particular model can be the parameter space can be fully probed by tau 2 E gamma future sensitivity. Okay, which is quite interesting. Similarly, for the RK star, the allowed region is this green, and yellow regions are the allowed region for 1 sigma and 2 sigma. And this orange region is for the G-2 of electron, and these various other set of regions are the exclusion region from different experiments. And tau 2 E gamma again can probe most of the parameter space in this kind of in this model. So here's the numerical fit. I am just showing one benchmark point with 4 different Yukawa couplings, Yukawa coupling matrices. For example, this blue explains G-2 of electron. This 2 explains RK star. This red color region explains RD star, and these cyan color regions explain G-2 of muon, and the rest of them are required to explain neutrino mass. And this gives a very good model prediction as shown in this table. Okay. Now I conclude my talk. So the conclusion is basically we studied a simple 2-loop neutrino mass model that utilized TeV scalar leptoquark and explained V physics. When I say V physics, RK star and RD star, the same model can explain muon and electron G-2. There are, I did not go into detail, but there are the same Yukawa coupling also is responsible for chiral enhanced delta G-2 of muon, which can be tested at fusion hadron collider. The model is, of course, consistent with neutrino oscillation data. Thank you.
So, thank you for the talk. Any questions? Go ahead.
Do I understand correctly that your model changes? Can you hear me? Yes. Changes the effective coupling to the electrons in RK star?
Yes.
And not to muons?
Yes.
So
the reason is, of course, I'm sorry to interrupt. So since we want to explain both of them together, so if you want to go through muon sector, then I don't think there is any model that can explain both of them together, just because you cannot satisfy the flavor constraints. And since in this particular model, we have, here, in this particular model we have S1 and R2. So in principle, S1 and R2 both can explain RD star. So if you want to explain this particular model, if you want to explain RK star, the only way is to go to electron sector. However, in this, for example, this model 6, you have R2 and S3. Here you can explain RK star from the muon sector.
I ask because, you know, most extensions of the standard model trying to explain RK star change the muons because we also have anomalies in K star mu and BS. Yeah.
Yes, I know that.
Yeah, but those are affected by hadronic uncertainties. So yeah, okay.
So I understand now because it's a comment or question.
So, but if you take into account the loop effect for R2, because with the loop effect for R2, you could get effective muon.
So I think probably you're talking about, for example, in the loop effect. If I understand it correctly, loop effect, for example, from the penguin diagram, right? You can induce effectively C9 and minus equal to minus C10 operator.
There are 2 loop diagrams which are important for R2.
Yes.
The first one is a box with a W, and the second one is an off-shell photon penguin with a tau inside. And each of them alone is not large enough, but if you add the penguin and the box, you can get a very good fit.
Oh, I mean, yeah, I was aware that there were loop diagrams, but we did not calculate that one. That is good to know, yes.
You didn't need to calculate it, but
sure.
Just checking would be interesting, yeah.
Yeah, that will be interesting, yes. Thank you for that, yeah.
Other questions? Okay, so let's thank the speaker again.
Thank you.
now Daniele Rizzo, also the predictions of flavorful Z-prime models from asymptotic set.
Thanks for the introduction. Good evening. I'm Daniele Rizzo. I'm a PhD student at the National Center for Nuclear Research in Warsaw, and today I will talk about prediction for flavorful Z-prime models from asymptotic safety. I work in collaboration with these three people. Our results are not published yet, but they will be on the archive. You will find them in the archive in a couple of weeks. We tried to tackle the problem of flavor anomalies, as measured in this paper, and we all know that in the framework of asymptotic safety, these anomalies are parameterized by two Wilson coefficients C9 and C10. In particular, we work on the transition bottom into strange, and there are a lot of ways to solve this problem of flavor anomalies, including scalar leptoquark, vector leptoquark, and the idea of adding a U1X in the standard model. That's actually what we do. So we introduce a Z prime whose job is to mediate the interaction between quarks with different flavor. And in particular here we ask, so we assume that Z prime mediate only the interaction between bottom and strange and the muons. Of course, depending on the new physics part of the new physics fermionic part of the theory, we will have different delta L and delta R for quark and leptons. It is this way possible to compute C9 and C10, and here delta 9 and delta 10 for mu mu are defined this way. Okay, I will start by introducing a quark. This quark has the same quantum number as the standard model quark and -1 as charge under U1X. I also introduce a scalar because I want to break the U1X symmetry. And if I assume the quark to be vector-like, then these are the terms that I add to the Lagrangian of the standard model. This way I can compute delta L and delta R for the quark part. And if for now we neglect the contribution coming from the leptons, because they are normally negligible, we can already explain the flavor anomalies in this way. Actually, the truth is that we only have information about the ratio, mz prime over gx and mq over y, q over the Yukawa coupling, which tell us that we only have information about 2 out of 4 parameters. So we need some tool, some technique that is able to constrain the parameter space and make us able to give prediction for all the 4 parameters. Our idea here is to use asymptotic safety. Because before going in the details of asymptotic safety, I will introduce the leptonic part. And here we decided to split our model in 3 different models, depending how the leptonic part is chosen. So first of all, we can introduce a new vector like lepton charged under U1X. And in particular, if this charge is -1, so the same as the quark, we will call the model 1A, while if we put a +1 here, so opposite sign as the quark, we will call it model 1B. If the lepton is vector-like, then the Lagrangian is this one. We can compute again delta L and delta R for the leptonic part and obtain C9 and C10, which is the same with different sign. The third model we worked on is the famous L mu minus L tau symmetry model, in which we charge muon and tau under the U1X. We compute again delta 9 and delta 10. C10 will be 0, and C9 has this form. So now I will stop with the model for a moment. I will talk about asymptotic safety, and I will explain how asymptotic safety constrained our models, and then I will go back to the models and talk about phenomenology. So we all know that in quantum field theory, coupling constants are not actually constant, but they run with the energy scale. In particular, for a generic one-loop calculation, we have the coupling at some scale lambda depend on the coupling at some observed scale, let's say m. And this denominator can be 0, which defines the scale that I call here lambda Landau. And depending if beta is positive or negative, we have 2 different behavior. We have a Landau pole if beta is positive, and asymptotic freedom if beta is negative. Examples here are quantum electrodynamics and quantum chromodynamics. In the standard model, because of hypercharge, we have a Landau pole. And we want a way to preserve the hypercharge to run into the Landau pole. One solution, well known and well studied, is gravity. So we know from dimensional analysis that at leading order, gravity corrects the beta function linearly. So if I have a theory below the Planck scale that is defined by this set of beta function, let's say for one gauge coupling and one Yukawa coupling for now, then in the Transplanckian regime, I can write the beta function this way, where Fg and Fy parameterize my quantum gravity correction. It is important here to notice that I'm not specifying a model for quantum gravity, but I'm just saying whatever quantum gravity is, I have correction to the gauge and to the Yukawa beta function through these two numbers. Okay, because of gravity, now I don't have anymore the Landau pole in the hypercharge, but I also have, the important thing is that I have fixed points now. So I can find a value in the deep ultraviolet in which I have a fixed point, which is a value of the couplings, let's say again G star and Y star, such that the beta function are 0. I can then linearize the system of beta function equations and obtain the so-called stability matrix. The eigenvalues of the stability matrix give me information about the fixed point. In particular, if an eigenvalue is positive, the corresponding eigenvector, so the eigendirection, is UV attractive, is named relevant, and in this case, a small deviation from the fixed point introduce a free parameter. So if I change a bit the value of the fixed point, I will get completely different values in the IR. So this is IR repulsive as well. On the other hand, if theta is negative, then I have a UV repulsive direction, which is actually able to give prediction, because whatever the value of the fixed point will be, I will always end with the same IR value. So this is able to give predictions. Okay, let me now go in the details of the fixed point for our models. First of all, here are all the coupling constants relevant for flavor anomalies. We work in the two-family approximation so that the only element of the CKM matrix that we care about is the element 3,3. GD is the gauge coupling for the U1X, and G epsilon parameterizes the kinetic mixing. We know that at the fixed point, the coupling of SU2 and SU3 are 0 because of asymptotic freedom. We know that V33 is 0 as well, and we must impose, this is actually something we find later, that the Yukawa coupling for the bottom is 0, because if we don't do that, then we are not able to fit the standard model at the IR scale. In this table, I give you the values for Fg and Fy, such that, again, we can fit the standard model, and the values of the coupling at the fixed point. In particular, if YQ3 is 0, we call the model, the scenario A. If YQ2 is 0, we call it B. So we had 3 models before, and now we have, let's say, 6 scenarios. Is it important to notice here that the kinetic mixing for model 1A is 0, and from analytical computation, it turns out that this is because the value of the charge for the new quark and the new lepton is the same, the U1X charge, of course. Okay, when we run the renormalization group flow down, so from the ultraviolet to the infrared, we obtain something like this. Here in the x-axis, I have logarithm of the energy divided by the Planck scale, so 10 to the 16 TeV, and on the y-axis, all the couplings. In the table, I wrote all the values of the coupling constant at 2 TeV. As Q0, I chose 2 TeV. And in the plot, it's quite interesting to notice this plateau in the green line. The green line is YQ2, and what this plateau tells is that YQ2 in its running, while, this coupling was going through the running, found another fixed point, started to be attracted by it, fall into the fixed point, and at this point, the only, the future for YQ2 is dictated by the properties of this fixed point. So this fixed point is not important anymore, and let's say the infrared value for YQ2, which is this 0.74874, is dictated by the properties of this fixed point. Again, G epsilon here is 0 for model 1A, and we will see later that this is quite important. Why is it important? Because the only actually experimental constraint that I will show in this talk is the kinetic mixing. We have kinetic mixing, as said before, because we have two U1 factors in our Lagrangian, and in terms of the G epsilon and Gy that I previously defined, G epsilon is given by this expression. Now, we have limits on G epsilon depending on the mass of the Z prime, and we had it at 7 TeV in this paper, and we had to actually obtain this line for the 13 TeV search at the LAC in our work. The dashed lines are the value of the kinetic mixing for model 1b and model 2, which means that we need at least Z prime of 3.9 and 4.8 TeV. If we plug this number in the parameter space for model 1b, for example, we see that all the parameter space allowed is already excluded. Here it's important to notice actually that all the parameters are fixed by asymptotic safety. The only three parameters that I have are the mass of the lepton, the mass of the quark, and the mass of Z prime. So I can fix some value for the lepton and plot MQ and MZ prime. As you can see, and as I said before, since we want an MZ prime at least 3.9 TeV, I don't have parameter space here. So model 1b is already excluded. Something similar happens for model 2. So even model 2 is actually excluded this way by searches for kinetic mixing, from constraint from the kinetic mixing. And as I said before, model 1a does not have kinetic mixing. So here we need something different. Actually, for scenario B, we can see that this is already excluded because YQ2 is quite big, 0.8. And if we compute the cross-section strange into mu plus mu minus through the Z prime, we obtain a very big value. So a value that is not able to explain flavor anomalies. So this can be, again, excluded this way. On the other hand, for model 1a scenario A, we don't have this problem because YQ2 is quite small. So here we need to look at other bounds at LAC and try to understand if this model is already excluded or not. But this is work in progress, so this is something that you will probably see in the paper. Okay, so let me summarize and conclude. Despite standard model gives often good prediction on physical quantity, this is not a UV completed theory. We aim for a UV completion of the standard model, and Z prime is able to give UV completion. The parameter space of models with Z prime are always very wide, and asymptotic safety was used as a tool to reduce the parameter space of such models. To do so, and this is our crucial point, the only assumption we made is the presence of an interacting fixed point in the deep UV zone. Then we run the coupling constant, so the flow of the coupling constant gives us prediction for new physics, and we test this prediction with searches for kinetic mixing at LAC with the run at 13 TeV. This way, all the scenarios but one were excluded because of a value for the kinetic mixing too high, and new tests for scenario 1AA must be performed using other LAC bounds. So the only thing I can say is stay tuned, and thanks for your attention.
Any questions, comments? Andy?
I would disagree with your very first point on the conclusion slide. I would not say that set prime model is more...
Andy, wait for the microphone because it's not so... We are not so well.
Concerning the first point, I would not say that the set prime model is more or less UV complete than the standard model.
Exactly. That was also, by itself, standard model is probably only UV complete.
Yeah.
Right.
At least you can consider it so.
But with the Z prime and the vector, okay. You mean that I should add also the vector-like fermions?
I mean, the standard model is UV complete. Even if you add a UV complete set prime scenario, you don't gain anything in this direction because the standard model is anomaly free, it's renormalizable, so there's no problem of this kind which you solve.
Okay, I get what you mean. Okay,
and my question was concerning the kinetic mixing.
Yes.
Why, can you explain why you have kinetic mixing in some models and not in all of them?
Yes. I was saying that I don't have actually the analytical expression, but about the fixed point, it turns out that the fixed point for this G epsilon depends on the difference between the U1x charge of the quark and the U1x charge of the lepton. So in model 1A, that if you remember is the one in which I said -1 for both, this cancel out, and G epsilon is 0. While you could also say, why in the ER then it's 0? You are running. So in principle, you can generate some kinetic mixing.
But what is the, you need some initial condition here, no, for this epsilon? For this G epsilon?
The fixed point is my initial condition.
Sorry?
The fixed point, the value of the fixed point is my initial condition.
The fixed point at the UV scale or the IR scale?
I run from here, from the UV. I start from the UV and I run down to the IR.
Yes, but at the UV, how do you know the value at the UV?
From the fixed point. Fixed point means you take the beta equations, you set to 0, and you solve for the couplings. This equation. So, okay, let me show you. For example, let me take, here I have only the gauge couplings. So if you take this and you set to 0, you have 5 couplings and 5 equations, and you can solve, right?
Ah, okay, now I see, yeah.
Okay. So this way you obtain for model 1A, you obtain 0, and for model 1B and model 2, you have value different than 0. The question there actually could be why you don't generate kinetic mixing in your renormalization group flow. And this is because G epsilon in here is multiplicative. So, yeah, exactly. In this equation, you have G epsilon everywhere. So if you start with 0 and you start to run, there is no way that you will have, in all the flow, a value different than 0.
Like this would mean you could avoid it in all models, no?
Sorry?
But this would mean you could avoid it in all models if it's multiplicative. If it's 0 at one scale, it will always remain 0.
Because it's multiplicative.
Yes.
Yeah, that's correct. That's correct. That's the point. That's why it's 0. That's why it's 0.
Yes, but only in some models. I didn't... Okay, we can talk later.
Exactly. I'm saying in model 1A is 0 always, at all scale. It's 0 here, it's 0 here. In model 1B, here is not 0, then you run down, at the 2TV, it's not 0, of course.
Okay, anybody else? Okay, so let's thank I guess so. It's the technical side. Yeah. So, neuronal facility, grand unified origin of gauge interactions and families replication.
Thank you. Much appreciated for giving me the opportunity to give this talk. This talk summarizes quite a few years of our activities, of our collaboration among the main members are here. I don't have to spend much time motivating my talk here. Of course, I will just highlight a few basic points that the standard model is, of course, extremely successful, probably more successful than those who invented it initially could have imagined. However, it fails to explain a few things. For instance, neutrino masses, dark matter, CP violation, matter-antimatter, and symmetry, as well as the observed flavor structure, very peculiar properties of flavor sectors in the standard model. So, more concretely, when it comes to the measurements, we all know that these emerging anomalies are difficult to explain in the standard model altogether. So, yeah, they are not quite discoveries yet, but they are at least pointers towards something new. Well, there is still a little question mark remains about G-2. Well, question mark because of some contradicting theoretical issues there, but still, that's an open question. And also the recent W mass anomaly which still needs to be confirmed in an independent measurement, but also one of the pointers to look at. Anyway, so my point here is to tell you what ground unification concept can tell us about all these issues, hopefully in a consistent way. So I'll start with reminding what we know about a model called trinification, and that's the focus in this talk. So trinification was one of the few candidates for ground unification since Glashow's work in '84, due to a few quite remarkable features. So this is the symmetry breaking steps down to the standard model, starting from this product of 3 SU3s, and then the standard model comes out here. The matter sectors just motivated by group theory. Basically, we have embedding into E6, treating this trinification as maximal subgroup of E6, and there we do have 27 plets, and for generation index we have this I here, which traditionally was just 3 copies of 27 plets of E6, but then of course you decompose it into trinification, then you end up with leptonic superfields here, quark left and quark right. So supposedly all the chiral sectors of the standard model should belong to this very, very few bitriplets in the original trinification group. Why this is interesting? Well, there are a number of positives about this concept. First, has been known since the past that the model accommodates in principle any quark and lepton masses and mixings, without assuming anything about flavor structure of this trinification representations. Then neutrinos appear to be naturally light via radiative seesaw with a split SUSY. Gauge symmetry preserves baryon number, so there's no gauge-mediated proton decay. And it's also motivated as low-energy version of a string theory, but I will not make any connections to string theory in my talk. There are also negatives. Among those are this type of operators, one lepton times lepton times lepton superfields that actually are very dangerous. So one has to find a mechanism to suppress those. There is a considerable amount of states that if you push some of them down, a lot more go down than you would like to have at the electroweak scale. That's a general problem for many GUTs. There is also unmotivated hierarchy between trinification and electroweak symmetry breaking scales. One has to do some assumptions about that. So that, despite of those multiple positives, those other negatives I just mentioned, a few of them made this scenario least developed in the literature so far, although an enormous amount of work has been done already. So here comes something new. On top of trinification, we have flavor structure. The usual approach to understand the flavor hierarchies is to impose a horizontal symmetry called family of flavor symmetry, whatever you like to call it. And that's what we do here. So let's marry the gauge trinification with flavor symmetry. So let's add and treat that index I, that is generation index, as being an index of a fundamental representation of a flavor symmetry. So with this framework called flavor T-GUT framework, T just stands for trinification GUT, we try to address all these other issues that the previous formulations, trinification-based formulations, have never managed to even talk about consistently. But all those issues that I mentioned as negatives in the past slide could be resolved. I don't think I will show you all the details in this 20 minutes presentation. It's a big work, but those can be consistently resolved once you have that flavor symmetry on top of trinification. Things like mu problem gets consistently resolved, generates larger masses in Kabiba mixing, and tree-level, like large quark masses, for instance, get tree-level contributions, but then others, leptons, for instance, receive one-loop masses and neutrinos as well. So for light-active neutrinos, one can identify a mixture of different seesaw-type mechanisms as well. So one can have radiative contributions, one can have seesaw type 1 contributions, and so on. No strong PMNS hierarchies are natural here. There is nothing that provides an hierarchy which is different from CKM, where you have strong hierarchy because Kabiba mixing readily generated, being readily generated tree level. So besides gauge unification, could then be married with additional gauge coupling in the flavor sector, then those could unify as well altogether under asymmetry where the C6 cross flavor symmetry comes from, which I'm not making any assumption about that one. One of the emergent phenomenon in this concept is the Yukawa unification. So one has a lot fewer Yukavas than we have in the standard model. That makes it into a predictable Grant unification, which is probably a rare precedent. So there's an enormous amount of work done by our group over a number of years. So actually, this is not the full list, but most relevant ones. Right. So in this presentation, I'll present the latest, and we'll found it. Framework based upon what I just said earlier. So we start with some unknown big symmetry where everything unifies. An actual starting point here is from E6 cross SU2 cross U1. Then go down to unification times flavor, and then go down to intermediate symmetry, which is left-right symmetry. SU2 left cross SU2 right are here, with color being intact, and some flavor remains, and then the standard model gets out at the soft SUSY breaking scale. So the hierarchies are such that there is nearly compressed scale hierarchy here, where MGOT is being the uppermost scale where E6 cross flavor symmetry gets emergent, and then we have E6 symmetry breaking scale M6, and M3 is the trinification breaking scale. Due to steep running, those scales are actually rather compressed, and then we have soft breaking scale, which is much, much below the trinification breaking scale, and that's where all the observable phenomenology comes from, and the standard model, essentially. So anomaly-free formulation, minimal anomaly-free formulation of this model is given by this table. To decoupled unwanted states, we actually impose Z2 symmetry, making this sector, this part of the spectrum, Z2 odd, which can host dark matter candidates. But I won't talk much about that Z2 odd sector. I will only talk about what happens in Z2 even sector. So the massless sector come out from dimension 3 superpotential with universal Yukawa coupling. However, that one at renormalizable level, dimension 3 renormalizable level, is identically equal to 0 due to E6 matching. However, one can bring high dimensional contribution, which becomes dominant in this case, and basically this where the full flavor structure comes about. So here MGOT is the uppermost scale, and this is just the product of three 27 plates. So E6 and trinification get broken then just by generating VEVs in this higher, larger representations of E6, 2430 rep and 2650 rep. So that provides necessary matching conditions and threshold corrections to the gauge couplings evolution here with this condition. Can be found in this paper, actually. We just exploit that concept. important thing that these threshold corrections get emergent at E6 breaking scale through high-dimensional operators, 5D operators like this. So then below E6 breaking scale, we recover this 78, what the parts of 78 representations called W78. So here we have delta fields. They are just octets under each of the SU3s. And then we have those ones here. So all of those guys get VEVs and get consistently integrated out. So they're actually very, very heavy. They do the job of breaking trinification and disappear from the spectrum. So what is interesting now is what emergent as trinification EFT after E6 breaking. So we have this LQ, L, and QR representations here. We have accidental symmetry appearing among those. 2 U1s accidental. One of them corresponds to the barrier number conservation. So you cover sector at the superpotential level perfectly protects proton. It doesn't decay at all to all orders. So the effective superpotential then looks like this in terms of 2 distinct couplings, Y1 and Y2, which accept this hierarchy from the matching to the standard model. Matching to the standard model gives this hierarchies quite naturally between the quark masses that actually consistent with observations right away, just in terms of two couplings, which are different by a factor of 100. So supersymmetry in this case unifies Higgs and leptons all together. We get 2 universal Yukawa couplings at unification scale and 2 quark generations acquire 3-level masses. Also CKM gets contributions at 3-level in the form of Kabibo, and then higher orders make it into a real CKM. So I will not have time to discuss mass spectra of quarks. It's all written here. We have up, down type quarks, and the down type also feature vector-like quarks. Some of them go down to the LHC energy scales, which can be probed naturally. So quark mixing, as I said, takes Kabibo form, and then we also recovered more general forms if we take into account mixing between light down type and heavy down type vector-like quarks. So this provides opportunities for LHC searches of vector-like quarks. So all leptons get their masses at one loop level. These are typical diagrams. The vector-like leptons here that are partners essentially of the Higgs states. So they also generate loop masses, and they all sit around the TV scale naturally by choice of parameter. So summary of the symmetry breaking chain is here. Actually, we have 3 regions here. The breakings in a supersymmetric theory, and then we have range where supersymmetry is already broken, then we have the range where flavor is already broken. So these are the colored ones. So I should say that there's no proton decay below E6 scale. So E6 scale, of course, is very high to not allow gauge-mediated proton decay through E6 gauge bosons, but then everything below essentially protects proton. It can be destabilized by certain cubic interactions in the soft SUSY breaking sector if one wants, but that usually brings an extremely small contribution. So at low energies, we discover something like minimal 3 Higgs doublet model, and we also have 2 generations of VLQs below the soft scale, and 3 generations of vector-like leptons below the soft scale. So this is the running here. So the largest running, the largest span between the scales is protected by supersymmetry. There's no issue with radiative instability of the hierarchies in this model. So I just want to highlight flavor physics part of this concept. So if we focus on the minimal low energy EFT of this flavored trinification gut, then we can absorb just these 2 states. the singlet leptoquark and doublet leptoquark, which is naturally predicted by supersymmetry, they unify into, one of them unifies into a single superfield, quark superfield down type, and another one is just coming from as a superpartner of standard model quarks. So the effective Yukawa Lagrangian appears to be here, and then we generate all these diagrams in the effective field theory limit that contributes to RK star, to be the case. Those ones contribute to RD star. This gives rise to G-2, and this provides neutrino masses radiatively at one loop level. All of that can be just parameterized in terms of these three Yukawa matrices only, so a very minimal scenario. So take into account hordes of different flavor physics observables, including also lepton flavor violation and lepton flavor conservation, so on. One could actually make a fit to the entries of those Yukawa matrices. With these three scenarios, 3 points that we have found out here. The first one, where G-2 and W mass anomaly are not explained here, B and C provides G-2 but not W mass. And red, this was sign, and red actually explains all the anomalies with kappa squared over a number of degrees of freedom is around 1.7, 1.75. So, okay, so I think with this I can conclude. So we developed a novel flavor trinification Grant unified framework giving rise to a standard model, effective field theory, standard model-like. There are corrections to the standard model, of course, with a realistic flavor structure in charge fermion and neutrino sectors. So the framework, in fact, offers interesting implications for flavor and collider physics. I hope I highlighted that for flavor. Didn't have time to talk about collider implications, but those implications primarily coming from the discovery potential of vector-like quarks and vector-like leptons, which are, some of them at least naturally, lighter at the TV scale, or few TV scale. So it's minimal energy FT, just keeping, for simplicity and for the sake of minimality, only leptoquarks, those two different types, doublet and singlet leptoquarks, can explain B physics, say mu, neutrino masses, and consistency with lepton flavor violation observables and lepton flavor conserving Z decays at this level. Pretty remarkable, I must say. Can also potentially address W mass anomaly if confirmed. Doesn't have to, but it can, with slightly disfavored ratio chi-squared to degrees of freedom. But right, so there is such a potential, and I hope if you have any questions, I would like to talk more about the details here. Thank you.
So, questions, comments? I have maybe one general comment. Sure. It seems to be a huge model with
it's
numbers
huge.
of parameters.
It requires many papers to be published.
Yes, okay, but it means that you can probably fit almost everything, but there should be many new phenomena. I guess you did not have time to show what you can see behind fitting already existing. But
yeah,
there are so many new fields that probably there should
yeah,
be.
the first and the biggest enterprise or challenge, if you like, is to actually take the fitted values of those Yukawa couplings, assuming that you only have lightest, what is it, 1.5 TeV up to 8 TeV, which is what fit prefers.
Sorry,
for the yeah, sure. For the leptoquark masses, and just keep those. We have those three Yukawa matrices. What we could do, and we should do actually, is just to fit, not to fit, but to actually match them to a unified paradigm that we have at a higher scale. Through multiple threshold effects, through RG evolution, we should be able to reproduce what is suggested by the data on those hierarchies between the entries within those Yukawa matrices. We should get them essentially from the matching as well. So then we find that consistency. We could say that, well, that's part of the same theory. However, at this point, what we just did, we have those states coming up from the high scale. We know that they can be lighter and everything else can be integrated out. And we just built an EFT which is inspired by high scale, but still not matched fully into it. So that's of course the biggest challenge. But given the number of couplings at the low energy scales, which of course when the original single or a few couplings branch out into many, of course to go through all the Yukawa RG flow and multiple scales in between, of course it's a big challenge. So that challenge remains over years, and we just make baby steps towards doing that. But of course, given the urgency of the flavor, we just thought, well, can we actually explain it with a minimal particle content from the flavor gut? And yes, we can. So of course, this low energy minimal scenario can be thought of a standalone scenario without matching to the high scale. But it's inspired, and this is already a first step. Of course, there are other challenges. For instance, for the QCD, for collider phenomenology, those hierarchies in the Yukawa's matrices, for the largest entries, we can really suggest to the experiment look into that particular channel, because that Yukawa is the largest, is preferred by all the flavor physics observables. That's a natural next step. We're working on that actually. What we have done so far, we looked, before looking at the leptoquarks, we looked into the sector of vector-like quarks and vector-like leptons, and found statistical significances for potential discovery of those into specific channels that are driven by this model. And yes, they can be discovered, at least in a certain parameter region, or excluded, if you like, at the next high Lumiere LHC upgrade. Not so much at the current LHC setup, but in the future. So that has been published already. So there are a few challenges that still remain, and I think we're going pretty well on that. So, but however, if we hear some interesting suggestions from the FINO community, we would of course like to address that too. But we do what we can at the moment.
Okay. Other questions, comments?
Hi. At what scale can you really break the trinification? I think I missed it.
Yeah, so I think I have highlighted that value, although a bit quick, that we considered this this setup with the scale. So M3 essentially compressed with MGOT, M3, M6, and MGOT, they are close to each other, within an order of magnitude from each other. So those are pretty high, so they're 10 to the 6, above 10 to the 16, sorry, above that scale. However, what is important here is this MS, which represents a collective soft SUSY breaking scale that actually gives masses to all the otherwise massless states, right? There's a lot of scalars that are just massless in the supersymmetric theory. You have to break up supersymmetry. In that case, you give the masses at that scale, which is, in our analysis, was taken to be at or below 1,000 TeV. Okay, so possibly with future colliders, you could start probing this type of physics, provided that the soft scale is there, up there, but not too far from what we can measure potentially, right? So 100 TeV would be already something we could hope for to discover masses of most of the particles that coming from this tri-triplet sectors.
Thank you.
Other questions?
So in the end, you get the neutrino masses from these super partners, so the leptoquarks. So why then do you choose this particular breaking scheme for the gut? In particular, why do you choose to have a left-right model in between the trinification and the standard model?
Yes, we looked at several possible scenarios. That's the most general what you can expect. But if you compress the scale of left-right symmetric model. I guess it's those ones here, those three ones here, which is what we did here essentially. All those scales are generated at ms, roughly. But of course, you can have some spread out between the scales. You can still have those in sequence. But you can make them broken at the same time. You can just start with unification, put a collective energy scale where this PF and omega are roughly the same values, and just break it down directly to the standard model. That's what we actually do in practice, but we wanted to show that there is a potential to have intermediate symmetries. You can impose strong hierarchies there between those scales, and you can generate left-right symmetric model if you want. So this is the most general setup that you can have. But if it's too complicated, and it is quite complicated, you can start compressing those scales and break more symmetries at once. So we do that, yes. For the sake of minimality, we should be doing that.
Okay, I guess that's it. Let's thank the speaker again. We have now talks by Mario Gomez, muon G-2 and lepton fiber violation with supersymmetric gut theories.
Okay, thanks to the organizers and thanks to the city for having me here once as a postdoc and giving me the opportunity to come back 20 years later or more than 20 years later. Anyway, so I will be speaking of the SUSY theories and combining them with the last results of the muon G-2. In the framework of the Patty-Salam model. How you pass this? There is. Okay. This thing. Okay. Sorry. So I will make a brief introduction of the Patty-Salam model and the motivation for the theory, and later I will just presenting results basically. So. Okay. So. Where I am? Here, okay. So the SUSY theory is something that assumes a partner for every particle known. So everybody knows that, but no, I don't know how many people know that this idea already ran around for many years. There was some theory based on the antipodia saying that the known world has a connection of something unknown, where everybody has his partner, and we don't see each other because there is a very big gap of energy between us. So this was written certainly in the motivations of many people to explore the world, certainly in the Columbus papers where I took the idea from. Okay, so still we are not doing anything new, the same ideas. Okay, so what are the motivations that we will write in our proposal? First, that when you measure very precisely the things of the standard model, we may find something missing, that it will be known process. The other thing, to explain something that we had no other explanation for, that it will be the dark matter, so the supersymmetric particle has a good prediction for the dark matter to explain all the properties, like the rotation curves of the galaxy, and also something exotic, something that is not predicted by a standard model. Then I'm going to combine results of these three things to see a framework that can explain the three of them at the same time. So the simplest scheme for the breaking of supersymmetry, it will be the universal scheme, but taking from gravity, but this is too simple, and with this you have difficulties to explain these three things. So we advance to other schemes. In this one, you have very few parameters and you predict everything. So you go to other scenarios based in unification models where you have different representations to put all the matter. You may have a reason to provide different initial conditions for the different representations of the group. So you end out with a more gain for the spectrum that you may found. Okay. In our case, we are taking the Patty-Salam model, that where we take non-universal Higgses, we take non-universal gaugino masses, and we assume that all the left and right, they are in the same representation, and we are assuming a symmetry between the left and right initial conditions. So basically, with these parameters, we think that we can explain the G-2 and the other problems. So, for example, the first thing that you have is that to explain dark matter, in these scenarios, there is many combinations of masses that you don't have before. Basically, in the SO10 model, that it will be the one with non-universal Higgses, you only have Stauch annihilations, you have what is called the resonances on the S channels, and this is what is called the funnel, sorry, the focus point area. Then, if you go to the Patti-Salan, you had by far more possibilities. You had charginos, because you don't have universal masses for the charginos. You have even gaugino dark matter. You have Stauch neutrinos as co-annihilations, and so it provides a fairly large amount of models to explore. Okay, so the G-2 is very difficult to fit because you have a very tiny signal, and the masses or supersymmetric particles, they are pointing towards several hundreds of GeVs. So this is a problem to explain something like this. So it will be nice if the G-2 was not there. So because it will be a lower limit, it's very easy to find in any supersymmetric model. So what happened? What is so problematic to fit it? That you have a problem with the Higgs mass. To explain the Higgs mass, you need a large spectrum. So basically, the trick is to split. For G-2, you need light leptons, and for the Higgs problem, you need heavy stops. How you can do that? You can do that with the gaugino non-universalities. If you put a very large N3, you end up with the mass for the S quarks, very large, and if you put light N2 and N1, you have lightest S leptons. That is basically the combination of things that you need to explain the G-2 in supersymmetry. So what happens when you do that? Then you have one area where you can explain G-2 very nicely at 3, 4 sigma. You find this set of points satisfying dark matter and all the constraints of the supersymmetric models. So we are going to concentrate in explaining what is the particles and what are the predictions for this area. So if we expand this area, we see that most of the people, the first thing that we appreciated is that most of the co-annihilations had disappeared. So we only have the annihilations using the TNU channels that appear in the first papers of supersymmetry, that in this case, due to the light masses of the LSP, they still provide a good relief density. So this is the line of W map. Most of the models, they provide very low relief density. The good relief density is between the bounds, the 5 sigma range, it will be this one. And then you have models with Stauch co-annihilations, models with co-annihilations of charginos. Our masses, since we are eliminating the left-right symmetry, we can select the leftest leptons lighter than the rightest leptons, and we have this kind of co-annihilations. Over there you have the S neutrino is also degenerated, and this will be these red points. So you can see that there is a very good distribution for every kind of LSP. We have almost a different kind of co-annihilations, that it means a different spectrum. So this makes it interesting to go further. So the next thing to see is the other invited person is the things to be discovered. It will be the mu gamma. The mu gamma, by taking the simplest scheme, that it will be the CSO1, we need some heavy masses for the right-handed neutrinos, and then we generate something effectively that is the MSSM plus the masses to the neutrinos. Here we are adopting a very simple scheme that is assuming that all the right-handed neutrinos are degenerated, and basically the mixing matrix is the PNMS matrix of neutrinos. So it's something that is very well known, and this is a very high reference. I mean, this implies a lot of mixing. So the question now to be asked here is, this is where they enter, is if the schemes generating the G-2 solving the G-2, they are not destroyed by predicting very large rate for mu gamma. And what we can see here is that taking some masses, some intermediate masses, the right-handed neutrinos that we took is the 2.5 10 to the 13. So they are very large, and here we find only a few models are violating mu gamma. So most of the people, just to explain colors, this is the gray one, are the light LSP annihilation. The red ones are the S-tau annihilations, neutrino annihilations, sorry. The red ones are Chargino annihilations, and the S-tau annihilations are the dominant, that are the orange ones. So when we put this in one scheme of parameters, so you can explain why we had this kind of annihilations. Here, this is the line of M1 and M2 at the SUSY level. So basically, points above this line, you have the LSP is Bino-like. Below this line, this is Wino-like. So the Wino-like is very difficult to match with then the limit of W map. The neutralinos decay very fast, and they cannot account for the relic density. So all this put a very strong constraint on the red points, that it will be the left-handed staus and the Chargino annihilations. So all these points will be excluded, and also they provide a very large prediction for mu gamma. So still the areas excluded for the mu gamma, this will be this one. Putting that in, so what is the question now to be answered is what is the combination for the Gaugino masses that are good to satisfy all these constraints. Then here is easy to plot in the discrete values, and we see that M1 is very similar to M2, and this will be below the TeV. And to satisfy the Higgs bound, you have to put Gaugino masses at the order of 2-3 TeVs, that it will be this one. So the different kind of annihilations, we set the limit that this one particle is the 20% heavier than the LSP. So this will be the splitting. So this will be points satisfying that matter, but not all of them are inside the W map. The W map constraint, it will be satisfied by the green area. So that this is still, you see that all these points, most of them, they don't satisfy the W map constraint. They satisfy, but they provide very small amount for dark matter. Okay, and what will be excluded in our scheme by the mu gamma? It will be these ones. All these areas, they were affected by the mu gamma. Okay, so all these points we can say that they are light supersymmetry particles, and they will be affected by the LHC searches. How? We can see that this is the LSP and this is the S-tau. The line for the S-tau, this is based on the search of S-leptons, and when they are very close to the LSP, you have a large room, so these almost don't exclude any models. It's more dangerous, the one of the neutralinos, and you see the ones affected by the one that provides a good relic density, some of them, they are in the area of at the reach of the LHC. We have not done the analysis, but many of them could be excluded. But still, you have this room for models not excluded by the LHC that provides a nice relic density, and also good prospect for the mu gamma. They are 1 or 2 orders of magnitude below the current bound. So still there is something that you can see. There is a nice motivation. And also the direct detection, just to complete the picture, this is the neutrino floor. This is what is excluded by the xenon 1 ton. You have many models here. And the problem here is some of them are below the neutrino floor. But still, in the analysis that we had done, most of the models are in the reach of the new experiments for direct detection, at least all the ones that predict good dark matter candidates. So I think that I can come to the conclusions that the SUSY models can explain the G-2 discrepancy via the SUSY contribution. Models with the Patti-Salan has the nice conditions to explain why, having, by searching N3 larger than N2 and N1. And the dark matter, you can have dark matter in the LHC range, implies the Chargino and lepton masses at the LHC ranger, and this is not true. The identification signal is okay at this transparency, and anyway, and right-handed neutrinos put in with the 601 mechanism, the branching ratio for the mu gamma falls in the experimental range. And this is true. Many of the points with the density interesting in the spin. No, this is not true. Spin independent. Sorry. I was very sleepy tonight. Last night that was modified the talk. So for me, that's all. Thank you. Thank you for that.
So thank you for the talk. Any questions? Okay, if not, let's try again. So we have now the last talk of today's session. The last talk is Tobias Falk, Flavor Anomalies meet Flavor Symmetry.
Okay, thanks. Yeah, hi everyone. Welcome to my talk. So I'm going to talk about this work today, which will appear on the archive this week, maybe tomorrow. So I was involved in that together with my supervisor. Sorry, how does this work? Yeah. Together with my PhD supervisor, Michael Schmidt, and Ines and Claudia. Yeah, and I'm going to talk about a model in which we address several flavor anomalies with the help of a flavor symmetry. Okay, so this probably doesn't require a lot of motivation at this point. We all have probably seen this plot here, provided by the HFLAV collaboration, where RD is plotted versus RD star. Several more or less recent measurements included, and the world average here exhibits a tension, or like a tension with the standard model prediction at a level of roughly 3 or 3.5 sigma or so. We also all know that the muon AMM is off with respect to the prediction in the standard model, although of course there's debate. But we take this as it is and want to explain it in terms of new physics. In general, we know that the flavor structure of nature must be more complicated than what the standard model suggests due to neutrino oscillations. So we want to explain RD and RD star together with the muon AMM with the help of a scalar leptoquark, which we call phi, which is essentially S1. This is not new. This has been done several times already. But I think a nice feature of our work will be that the interaction structure of the model will be determined completely in terms of a discrete flavor symmetry. Okay, so I'll briefly describe the model setup. Afterwards, explain what leptoquark coupling texture we want to achieve. Then how this is done in terms of this flavor symmetry and how we break it. Before I turn to the phenomenological study, and we'll address a few key observables that we identified as the most prominent ones. Okay, so we extend the standard model by a scalar leptoquark, as I had said, phi, which is S1 complex conjugated in principle, It's a weak singlet, and since it's a leptoquark, of course, it carries color charge. We impose baryon number conservation by hand, in order not to having to deal with proton decay. And then, since we do not include sterile neutrinos in our model, the only renormalizable interactions with standard model matter fields are those two here, involving the left-handed lepton doublet, left-handed quark doublet, and right-handed charged lepton and up-type quark fields. So the hats here mean that we are in the interaction basis of the charged fermions. But the pheno we discussed in terms of the mass basis of those. So in order to do that, we consider the model after electroweak symmetry breaking. Then we remove the hats in order to indicate the mass basis, and we use the superscript M in order to indicate the fields. So now this matrix X hat has kind of split up into matrix Z and matrix X, which are related via quark mixing. Formally, we operate in the context of a type 2 Higgs doublet model, where there are two Higgs doublets, which both take a VF of which the squared sum adds up to what we know from muon decay, for example. But we assume the decoupling limit, meaning that there's essentially only one standard model-like scalar, which we identify with the standard model Higgs boson. The rest of the spectrum is decoupled. The point of this is actually that it is more convenient in terms of model building. So we assume that the masses of the charged leptons and of the down-type quarks originate from HD, whereas the other Higgs doublet HU generates the up-type quark masses, which is easier to achieve than if you only had one Higgs doublet. Right, and now, so for the flavor structure of the model, we employ a group product. We use the dihedral group D17 and an external Z17 symmetry. So the reasons for following dihedral groups are relatively simple in structure. They only feature 1- and 2-dimensional irreducible representations. And so what we can do is we can use singlets for the third generation of fermions, which makes sense because those are the heavy ones. And we try to use the the doublet representation for the first two representations, the first two flavors, sorry, as much as possible, which is essentially, which is very convenient for quark mixing. But since we are in a non-SUSY context, we will, so that means that the complex conjugate spurions will also couple. This is something which will be important later, but another aspect is that the representations of dihedral groups are real. And so we'll probably get interactions that we don't want if we don't also impose this Z17 symmetry. Z17 is abelian, and in that sense it's a bit similar to the well-known Froggatt-Nielsen approach, which has been proven successful in order to give rise to the mass spectrum of the charged fermions. Okay. So in this work, in which my supervisor was involved in, this texture was identified as viable if we want to explain the anomalies in RD, RD star, and delta A mu. So the leptoquark masses seem to be not larger than 5 TeV, and it turned out that one can express this texture in terms of symmetry breaking parameter lambda, which is numerically coincident with the Cabebo angle. And then, so we need a large effect in RD and RD star, so the involved couplings should be unsuppressed. To get delta A mu of the right order of magnitude, we need this product of couplings to be given by roughly lambda to the 4th power. And the rest of the texture basically arises from requirements related to avoiding certain bounds from B2K nu BS bar mixing and transitions involving a charm quark and a muon. So in order to do that, we chose the following assignment of some of the fields to the dihedral group D17 as follows. So first of all, we said, okay, we want the leptoquark to be the trivial singlet of the entire flavor symmetry. That's just a choice. one can make. We also want the Higgs doublets to be singlets under D17. And then, so in order for these couplings to be unsuppressed, the fields which constitute them should be in complex conjugate representations. So since in D17 all these representations are real anyway, this only refers to the external Z17 symmetry, but we learned that L3, Q3, as well as ER3 and UR2, which constitute these two couplings here, they need to be in the same representation essentially, and so we also put them into trivial singlets under D17. Same argument for the third generation charged fermion masses. They should arise at the renormalizable level, and so all the involved fields should be in the same representations. We chose this one to be the trivial singlet as well. And now, in order to get the suppressed entries here, suppressed by at least one power of lambda, we invoke one single spurion S, of which the VEF is given by lambda itself. Then we need as many insertions of S, well, as given by the power of lambda here in order to achieve the correct strength of the coupling. So for example, for this coupling here, which we want to be suppressed by lambda only, we need this to be generated by an operator where we only have one insertion of the spurion S. And since we have already fixed Q3 to be a singlet, this means that L and S should live in the same doublet under D17 in order to contract into an invariant of the flavor symmetry. So we can choose S and L both to be in the doublet 2, 1. So D17 offers several inequivalent doublets, up to, I think, 8 overall. And so we can play this game as well for the other non-zero entries that we can see here. So for the other ones, for this one here, we use 2 spurion insertions, meaning that Q and S squared will have to be in the same doublet. So Q transforms under 2, 2. Yeah, and similarly for the other 2 remaining couplings here. So this then fixes these transformation properties. Right, okay. So let me address the symmetry breaking in a little bit more detail. On the renormalizable level, again, we only want these 2 couplings to appear. And in the standard model Yukawa sector, we want to generate the masses of the heavy third generation, meaning that all these operators here are supposed to appear at the renormalizable level. So at this stage, the symmetry is fully intact. But then when the spurion S gets its VEF, we break it down to a residual symmetry, which is given by the diagonal subgroup of a Z17 symmetry, which is contained in D17, and the external Z17 symmetry. So this means that these non-zero couplings that we see here in these matrices, coupling matrices, they preserve this diagonal symmetry Z17 to leading order. Because the VEF of S is engineered such that it's uncharged under that. In fact, this way we also generate, or we also source contributions to 2 of the quark mixing angles. And then we need to introduce 3 more spurions in order to generate the masses for the lighter charged fermions, because the hierarchies are too pronounced in order for that to be achievable just with 1 spurion. So we have 3 more, of which the VEFs are smaller, and so these VEFs generally break the symmetry down to basically nothing at the electroweak scale, say. So as soon as we do that, as soon as these fields take their VEFs, we also populate the entries here in the first row and the first column, these couplings, but we see that the diagonal Z17 symmetry manages to suppress them fairly efficiently. And so the spurion T generates the mass of the strange quark and the muon. The spurion U generates the mass of the down quark and of the electron. And lastly, W is responsible for the Cabibbo angle, the charm quark mass, as well as one of the quark mixing angles. And then we have this combination here, which gives rise to the up quark mass. So these are only the most important operators, so to say, that we identified for our model. There are many more we in fact considered all operators with insertions of spurions such that we get contributions up to order lambda to the 12. So we have many, many more operators, but these are the most important ones. Okay, so now for the phenomenological study, we classified the observables that we were considering into primary and secondary ones. Primary are those, trivially, that we want to explain, are d and rd star and delta mu, but also those of which current bounds, in principle, constrain the parameter space of our model. So I will only address a few of them in the following, just for the lack of time. Secondary observables are currently not competitive, but promise to be so in the near or midterm future. So for the mass of the leptoquark phi, we chose these three benchmark values, which are compatible with searches for this leptoquark decaying into a tau top pair or a bottom neutrino pair. If these two branching ratios are similar, which is the case in our model because they are the relevant couplings are related via quark mixing. We performed two numerical scans. First one only over the primary observables, where the coefficients that we had seen beforehand, A11, A21, and so on, same for this matrix, and the matrix Z, which carries the coefficients Cij. We vary them mostly independently in this range, which preserves the expansion in lambda in the mass basis of the charged fermions. Whereas in the second scan, we consider all observables, and we also fit the standard model Yukawa parameters to the spectrum of charged fermions and to quark mixing. For leptoquark couplings in this case, we want to target a region in parameter space which is interesting for our purpose of explaining the anomalies here and being consistent with current bounds. And so we derived suitable biases for some of these coefficients here from the result of the primary scan and imposed them for this more comprehensive one. Otherwise, we also varied them independently, more or less. But we also made sure that we respect the underlying kind of fundamental structure for our model in the interaction basis of the charged fermions, meaning that these coefficients are now not free parameters anymore, but instead they're given by the standard model Yukawa parameters and these coefficients in the interaction basis. So these coefficients constituting the matrices X hat and Y hat before electroweak symmetry breaking. Okay, so the dominant contribution to delta mu is given by this diagram here with an up quark running in the loop. We generate the correct order of magnitude with that. Let me get to the plot in 1 second. Rd and Rd star are sourced at tree level, as is well known. The leading order correction to the standard model expectation is given by this term here. So now for the plot. First of all, we distinguish the three benchmark masses, 2, 4, and 6 TeV, with the colors red, yellow, and blue. In this plot, the sample points that you can see are very heavily selected. So the light-colored round dot points are those for which all experimental bounds that we have considered are respected, and we explain the G-2 of the muon at 3 sigma. Similarly, for these specific shapes here, for the star, the plus, and the cross, where the same thing holds, but we can even explain the G-2 at 2 sigma. And we see that doing we actually managed to populate a region inside the 3 sigma contours, which arise from the current world average provided by the H-fluff collaboration. So we managed to explain all 3 anomalies together at 3 sigma, respecting all experimental bounds. And we even identify one sample point here where this works at 2 sigma. So of course, one sample point is not super much, but I think it's remarkable that at least it seems to work in principle. Okay, let me go through the other observables rather quickly. We have tau mu gamma, which is in principle generated by the same diagram. This is the most stringent bound for our model, we think. We easily saturate the current bound. The the future search for that at Bell 2 will test our model very efficiently. Note that for these plots here, the color points respect all experimental bounds, but they do not necessarily explain the anomalies we want to explain. This is only the case for these white crosses here. So we are essentially after those white crosses. In principle, the same for mu2e gamma, also a very efficient probe for our model. mu2 I don't have a dedicated plot for, because in our model it's very, very stringently correlated with mu2e gamma, so you just plug in this factor and you do the maths. mu2e conversion in aluminium, in a way, is the most interesting future probe for our model, because all of the white sample points here, which we are after, seem to fall above the future limits at mu2e and at Comet. And finally, the decay tau to 3 mu also seems to be an interesting probe for our model in the case of 2 TeV, where we find that we might see a signal at Bell 2 and simultaneously explain the G-2 at 3 sigma or better, which is due to contributions from Z penguins. Contributions from photon penguins are in general too stringently constrained by the non-observation of tau to mu gamma to achieve that. For larger masses, it's not possible to have both a signal at Bell 2 and to explain the G-2, but at least for lighter leptoquark masses, this can be achieved. Okay, so in the interest of time, let me conclude. We have constructed this extension of the standard model, which is constrained by a flavor symmetry group, which is intact at very high energies, but then gets broken by 4 spurion fields which take baths. A residual symmetry is preserved by the leading order contributions to these leptoquark couplings here, which very efficiently suppress couplings to electrons and up quarks, and therefore allow us to evade many stringent constraints. Essentially the model manages to explain these anomalies at 3 sigma at least, and we can perform a successful fit to charge fermion masses in quark mixing. Thank you so much.
So, that was the last talk today. Any questions, comments? Sakis?
Is this a dihedral symmetry that you have assumed? Is it able, I mean, are you able to kill also the baryon number violating operators?
No, unfortunately not. So we checked that, but so the assignment that we have chosen in order to get the leptoquark couplings the way we want them to be, it's not sufficient to also suppress baryon number efficiently enough, so we just impose it by hand. But you're right, that will be an interesting future direction to look at. Yeah.
Okay. And just one, if I may.
Go
What about RK?
No, we can't also explain RK because we only have like this leptoquark, which is S1. RK is only sourced at one loop level with neutrinos in the loop, and then.
And you need the S3, and then.
Yeah, exactly. You need S3.
And then you need, I mean, the same symmetry will not work again, or.
We haven't yet
or
checked
maybe.
that. Maybe, yeah. So there would have to be modifications, most likely.
Other questions? Okay, so if not, that's all. Let's thank all the speakers, and let's meet at the public lecture. Sakis.
cosa tipo di vedete si lascia ottimo το μικρόφωνο είναι εδώ, είναι εντάξει, το with us here Professor Thimios Kaxiras. He's professor of physics at Harvard University, physics department. He's also the head of the department. And another thing is that his origin also is from Ioannina. So he immediately responded to our invitation, and he came from Harvard here to give us a lecture about twistronics. So Thimio, thank you very much for coming, and please.
Thank you, Yorgos. Thank you also for the invitation. As you said, I was very happy to accept your invitation, and I'm very honored and particularly happy and excited to be here. The title of my colloquium is Twistronics, a new platform for physics and applications in using 2D materials. I'll give you an outline in a moment. I just wanted to thank you all for staying so late in the day after a long day of talks. Usually these kind of evening talks are after dinner, so the problem of the speaker is to keep the audience awake. I have a different problem because I assume you haven't had dinner yet. My problem is to keep you here, but I think I have an advantage because, as you know, Greek restaurants don't open for dinner until much later, so I have a captive audience in this sense. I'll try to address the following questions in my talk. First, why you're doing this work, a little bit of motivation, what's the interest and importance of this, how we are doing things. I'll give you a little bit, remind you a little bit about condensed matter physics and what enters in these considerations, to how to describe these materials, and then what exactly are we doing, a little bit about new methods we have developed, and some what I think is quite neat new physics, interesting physics. And in the end, if I have time, I may address a more philosophical question of why am I here? George alluded to it a little bit. Okay, so let me start with a big question, why 2D materials? Now, I have to say, when I put that question up there, I realized that this audience doesn't have any problem playing with dimensions, 2, 3, 5, sometimes even many, many more. However, we are talking about real materials which exist in 3 dimensions, so I feel the obligation to justify why you are focusing on 2 dimensions. And the reason is that there's quite a bit of very rich physics in the 2-dimensional electron gas. And just to highlight a few of the big contributions, there's the quantum Hall effect, and the fractional and integer quantum Hall effect, and these are the people who first observed this, von Klitzing and Tsui, Stormer, and Art Gossard, and Bob Laughlin, who contributed to the theory of this. So this is captured by this quantization of the resistivity in the direction perpendicular to the current. And this is a picture of what is really happening in a 2-dimensional electron gas. Now, the electrons form these orbits, which are quantized in Landau levels, and there's interesting behavior at the edges. This is something that my colleague Bert Halperin pointed out many years ago. And more recently, there were predictions about the quantum anomalous Hall effect. So this happens under the influence of an external magnetic field. The anomalous Hall effect does not involve an external magnetic field. Dang and Haldane predicted this and created the theory for this. So many of these gentlemen were actually awarded a Nobel Prize in Physics for their accomplishments. So it is, this figure contains a lot of the highlights of condensed matter physics, all of this in the two-dimensional electron gas. However, creating a two-dimensional electron gas with three-dimensional crystals is really very, very difficult. And the way that it was done many years ago, several years ago, was by creating this kind of potential. The vertical axis here is the potential that the electrons experience. This is position in space by this very elaborate arrangement of the different three-dimensional crystals. And right at the interface here between two different crystals in this very small region, you have this kind of potential well, which captures the electrons in the direction, in this direction, and creates the two-dimensional electron gas. So it took a lot of effort to make the materials behave well enough to create this and study this exciting physics that I was just describing. However, in the last few years, we've solved this problem. We've actually solved this problem in a bigger sense. For quite some time, it was believed that two-dimensional solids themselves cannot really exist. And this belief was based on this theorem that continuous symmetries cannot be spontaneously broken at finite temperature in systems with sufficiently short-range interactions in dimensions less than or equal to 2. So this is the famous Mermin-Wagner theorem. Also, Pierre Hohenberg discussed this. And intuitively, this means that long-range fluctuations can be created with little energy cost, and since they increase the entropy, they are favored. Therefore, lots of these long-range fluctuations would destroy any kind of two-dimensional arrangement of atoms. And Sidney Coleman also discussed this in the context of quantum field theory. However, there is a cornucopia of two-dimensional materials that is available to us now in the last couple of decades or so, including different types of semiconductor crystals, all of them really two-dimensional layered materials, insulators, there's several of those, and even metals, and in particular graphene. And in fact, the persons who discovered graphene, Geim and Novoselov, were awarded the Nobel Prize in Physics for their discovery. And in fact, the existence of these materials does not violate the Mermin-Wagner theorem because in graphene, in freestanding graphene, there are these long-range fluctuations. However, the bonds between the atoms are so strong that the crystal is not destroyed. In fact, this is the second strongest bond between atoms of the same type in nature. So this is really, really strong material in the layer, and there are these long-range fluctuations. So one of the exciting questions in the last few years is how to combine several of these materials to create even more exciting possibilities for physics and applications. And this is a nice picture that Geim and Grigoriev published a few years ago, and then it has become the standard thing to show. However, it is deceiving because these layers do not quite fit like Legos on top of each other. And they each have their own structure, characteristics, and so on. So putting them on top of each other is a challenge, and creating variations on this theme of simply stacking them brings out a lot more interesting possibilities. And this is essentially what I will be describing. Now, for real devices, you do need a variety of components. You can't just have one material. So you need a metal, a zero band gap material. We have graphene. You need a semiconductor. We have a family of very versatile semiconductors called transition metal dichalcogenides with different band gaps, which depend on the composition and the number of layers. So there's a lot of flexibility here. And we also need an insulator. There's a very good insulator, again, a layered material, hexagonal boron nitride. And indeed, people have been combining these types of materials to create interesting devices. So here's an example. Green is the insulator. Black is graphene, which is the metal. This material here in the middle is the semiconductor in which carriers, electrons, and holes are created and transported away. And these contribute to devices for faster data communications and so on. So it's a reality. We can use these materials in these arrangements to make real devices. Here's another example. This is from the group of Thomas Palacios at MIT. So here's graphene again, which acts as the source and the drain to bring electrons in and out of the system. Molybdenum disulfide, this purple is the semiconductor which does all the switching, and you can create different gates here, NAND gate, and so on. So real devices for future devices that consume much less power. Okay, so a twist, so to speak, on this theme came up a few years ago, where by creating this kind of situation, putting one layer on top of each other, or on top of another, and then twisting them by a small angle, produces this moire pattern. So this is graphene, for an example. And this moire length scale, which is much, much bigger than the atomic length scale, gives essentially another adjustable superlattice to control the electron behavior. So that's the essence of the physics that I will be describing from now on. Notice that this is not a truly periodic pattern when you have a twist of an arbitrary angle between the two layers. And here's a real example, not a schematic. So this is what my colleagues call twist engineering. This is from the work of Philip Kim, a colleague at Harvard, and his group has been a pioneering group in this field. So this is twisted bilayer graphene with a relative twist of about 1/10 of a degree, which is quite spectacular. And you see these beautiful patterns when you have this. This is a dark field image by scanning transmission electron microscopy. I'll explain a little bit about where these patterns come from. And just so that you don't get the impression that it's only graphene that does that, all the systems, the two-dimensional systems that I told you about can be used to create this. So this is another case. This is molybdenum disulfide on molybdenum disulfide, 2 layers stacked and twisted in different arrangements. This is what each layer looks like at the atomic level. Again, lots of interesting patterns that can be observed and explained by theoretical considerations, and they have interesting implications. Okay, how do they do it? Just out of curiosity, so you know what exactly is being done in experiment. So they take one layer, they stick to it, to 1/2 of it, another flat material. So this is graphene, this is hexagonal boron nitride, and then they lift this part, so the original layer is torn in half, but now you know exactly the relative orientation of the two halves. So you raise 1/2 over the other and just mechanically twist it by a small amount and put it back, and there you get the twisted bilayer. So they claim a control of less than 1/10 of a degree. Nowadays they're actually claiming control of less than about 1/100th of a degree twist, which is really quite mind-boggling. Okay, trying to explain the physics now, let me just refresh your memory about how things work at the atomic level for crystals. So this is a picture of the graphene crystal. It's what we call a honeycomb lattice. It's a hexagonal lattice with a 2-atom basis, A and B. These are the lattice vectors in real space, and of course periodicity in real space implies periodicity in reciprocal space, in momentum space. So the corresponding unit in momentum space is this so-called Brillouin zone. It's a hexagon, and this is the irreducible part by symmetry of this hexagon. So I'll be showing you lots of hexagons, and so I wanted to orient you of what I'm referring to. I'll also be showing a lot of results, theoretical results, and we do have a lot of confidence that our results represent nature quite realistically. So I wanted to explain why we have this confidence. It's based on a realistic theory which uses the atomistic structure of the material. This is called density functional theory. It's also called the Hohenberg-Kohn-Sham theorem. Walter Kohn was one of the major contributors and developers of this theory. He was actually awarded the Nobel Prize in Chemistry. And here's the essence of this theory. We have the Hamiltonian of a solid, kinetic energy, and this potential in the red box is the effect of the atoms on the electrons, and there's an effective potential which contains the Coulomb repulsion of the electrons and all the details of their exchange and correlation effects. Now, of all these terms, the exchange correlation contribution is not known, so we have to make an approximation for this, but there are developed approximations based on exact calculations on the uniform electron gas. And this then offers an excellent description of the total energy of the solid and its gradients, which are the forces on the atoms. So this can be used to have a very good description of the structure of the solid. But there's also a good description, reasonable description of the single particle states. These are these eigenvalues of these equations. There's a lot of experimental checks for this. There are no adjustable parameters, so we refer to this as an ab initio theory, and it allows us to make a lot of predictions and to explain and guide experimental searches. The limitations are that it can only handle relatively small number of atoms with periodic boundary conditions of order 100 to 1,000 at most, and that's a severe limitation for the problem that I will be discussing. I'll show you why this is so. And it is based on the crystal structure using block states, Brillouin zones. These are the momentum-labeled states referred to as block states, and K vectors, the momentum vectors in the reciprocal space, and so on. So with this kind of theory, this is the picture that emerges for the electronic structure of graphene. So we solve this equation now, and we get these energy eigenvalues for all the momentum values in the Brillouin zone. Here's the hexagonal Brillouin zone in the reciprocal space that I showed you already. And this is the energy in a cross-section of this Brillouin zone. And in this small region around the Fermi level, these are occupied states, the white are unoccupied states. So around here, you see this linear dispersion. So the energy is linear in the momentum, which is highly unusual for real materials. When this was realized, it created a lot of excitement in the condensed matter community. So the energy is linear in all directions in reciprocal space. So you get these so-called Dirac cones with linear dispersion of the energy with momentum in every direction in momentum space. So this, as I said, created a lot of excitement about graphene, and a lot of work was done theoretically. However, this also has a severe limitation. If you look at the density of states, so on this axis is the energy again, here I'm plotting the density of states, and right at the Fermi level where we have the linear dispersion, the density of states is 0. So there are no states, no electrons at the Fermi level to use. So in this sense, graphene is a very bad metal, and it's referred to as a semi-metal. However, near the Fermi level, you see that the dispersion flattens out. These are called flat bands. And that's where you get a lot of density of states, those so-called Van Hove singularities. But it is impossible to access these flat regions because they are far from the Fermi level, 2 or 3 electron volts, which is a very large energy difference on this scale. So the holy grail for using graphene in a practical way was from the beginning to try to find ways to enhance the density of states, but accessing these large regions was impossible. Now, this is the thing that the situation that the twisted bilayers made possible. So a little bit more about what the twist actually does. So here's the picture again of a twisted bilayer. So what you find here is that there are regions where the stacking of the layers is of this type, which this is referred to as AA. So the two layers are stacked so that only the top layer is seen and the bottom layer is completely hidden by the top. There are other regions called BA and AB. In this case, the top layer, of course, is seen again, and half of the bottom layer can also be seen. This is a different stacking. This is the high-energy stacking. The atoms do not like to be in this arrangement. This is the low-energy stacking. The atoms prefer to be in this arrangement. This has also important implications. Now, related to this twist in real space, you also have the two Brillouin zones of each layer, the red and the blue one, twisted relative to each other, which creates a supercell Brillouin zone, the smaller one, the smaller black hexagon. And of course, attached to each one of the big hexagons is a set of Dirac cones at the corners of the hexagon, so at the of the large hexagons. So at the corners of the small hexagon, the supercell Brillouin zone, you get a Dirac cone at each one of these points from different layers. The adjacent ones are from different layers. So that's the essence of what happens when you introduce the twist. And the consequences of this were pointed out first by Bistreitzer and MacDonald in a really beautiful theoretical treatment. So basically you have this black hexagon that I just mentioned, the supercell Brillouin zone. At each one of them you have, at each corner you have a Dirac cone from the two different layers, the blue and the red. Those two Dirac cones intersect at the intersections. The degeneracies are lifted by this splitting. The amount of splitting here is determined by the interaction between the layers, and the distance between these nodes is determined by the moire length, the size of the supercell hexagon. Okay, but related to this arrangement now, you have a density of states as a function of the energy, which is significantly different, and these new bands, the so-called flat bands, have a much higher density of states. And to compare this density of states with that of the single graphene layer, you have to multiply the density of states of the single layer by a factor of 1,000, so it's on a comparable scale. So this is really a very large density of states created simply by this twist and the splitting of the bands. So this was a qualitative picture. In order to have a quantitative picture, you do need to do a more detailed calculation. The trouble is, I mentioned this briefly already, the layers are incommensurate if you assume an arbitrary twist angle. So how can you describe the system? Well, the way that we are doing this is by looking at what is referred to as configuration space. This is actually based on work that this group of mathematicians did. We worked very closely with them to develop this theory. And essentially, you have these two layers, the red and the blue layers on top of each other. And if you look at different regions, you have different local configurations, different local arrangements of the blue atoms relative to the red atoms. So referring everything back to a common origin, the second layer atoms are displaced by various vectors, and then you have a configurational space. So instead of doing integrals in momentum space, as you typically have to do to calculate any physical observable, now you have to do integrals over configurational space. That's described by the variable little omega and the whole space by capital omega. So that's the essence of the mathematical formulation of how to do calculations for incommensurate layers. However, for this, you cannot use the extended block states, the momentum label states. You have to have states of finite range, localized states of finite range. We know how to do this. There's a well-developed theory. I'm not going to go through the details, but essentially you can create the equivalent localized orbitals for graphene, not the extended orbitals, and these can be represented by an atomic orbital. This looks very much like an atomic orbital, but higher angular momentum contributions. So this is work that my student Shang Fang did. And then you create an interaction term in the Hamiltonian that depends on these more complicated orbitals. And since we know how to do this, we can then use the machinery that I was describing earlier to do calculations for a very large number of atoms, up to millions of atoms, which is what it takes to describe accurately, with all the atomic positions, twists of approximately 1 degree or less. So the unit cells are so big that they involve hundreds of thousands up to 1 million atoms and so on. So this is work by my two students, Stephen Carr and Shang Fang. And this is a plot now of the density of states as a function of the angle and as a function of the energy. And it's also color-coded. Yellow is high density of states. And just to compare with the picture that I showed you earlier, it's flipped. So the axes match. This is energy, this is density of states, this is the zero that I was mentioning earlier, and these are the Van Hove singularities. You can see them roughly here. But through the twist at about one angle twist or so, you get this huge density of states very close to the Fermi level. So that was the revelation. Now we can have density of states, very high density of states, where we want them, close to the Fermi level, just by simply playing with the twist angle. So when we realized this, we published this paper and called it twistronics. And it was a catchy word. Some magazines picked up on it, and there were articles published. Twistronics tunes 2D material properties, and as magazines tend to do, they exaggerate the coming age of twistronics. Okay. There's a lot of interesting behavior here once you look at the details. Here's some experimental evidence. So what you see here is a superlattice-induced insulating states in twisted bilayer graphene. So this is the conductivity, and this is the doping level. So you can think of this as basically probing the density of states. The values of the conductivity is equivalent to what I was talking about, the density of states. And you can think of this axis as moving the Fermi energy around. So you're scanning the position of the energy for different states. So these are the two humps that I was describing earlier, but those are now separated by gaps from the rest of the states. So this picture shows you what happens when you turn on the magnetic field. And you find different Landau levels. So these are called Landau fans. You can identify these slopes of the Landau fans by different fillings. And our theoretical calculations fully capture this picture. I'm not going to show you details. I just wanted to flash this to give you a sense of what experiment tells us. But as I've emphasized already, you do need to know exactly where the atoms are to do a realistic calculation. So here's what experiment shows for graphene. Here's for molybdenum disulfide. This doesn't look at all like the two layers on top of each other in a very simplified way of just stacking them on top of each other. Instead, it looks much more like this, with triangles forming, or roughly hexagons or distorted hexagons forming. These are the results of taking into consideration how the atoms relax, how they find their optimal configuration. And how do we do this? This is a short description of our methodology for doing this atomic relaxation, which tells us where the atoms are so we can do realistic calculations. So we calculate what is referred to as the generalized stacking fault energy. That means take two layers and slide them on top of each other in all the possible ways and calculate the energy for this sliding. That's the generalized stacking fault energy. These are cross-sections of this energy landscape for different materials, graphene, molybdenum disulfide, stacked in different ways. And these are cross-sections of these energy landscapes along the diagonal. But once you have the energy, you can take gradients of the energy, which tells you the deformation of the solid. And you follow the deformation gradient until you get an optimized structure. And that's how we get these patterns of fully relaxed atomic layers. There's a lot of calculations behind these simple representations of where the atoms are, but we are indeed able to have a fully relaxed, realistic atomic structure. And here's another way of viewing it. This is again twisted bilayer graphene viewed from the side. So I was showing you in the previous picture the relaxation within the plane of the layers. This is the relaxation in a vertical direction, and you see that different parts of the stacked layers are relaxed by different amounts. The distances are different in different regions, AA region, AB region. I'm highly exaggerating the vertical axis to magnify the effect to make it visible. Okay, so does it matter? Indeed it does. If you do a calculation of the fully relaxed structure, you get this picture. So these are the flat bands near the Fermi level, and they are separated by band gaps from the rest of the states. If you neglect the relaxation, simply stack the two layers without paying close attention of where the atoms actually are, you get this mess, which is far away from experimental measurements. Okay, another very interesting and exciting surprise came about 4 years ago when the group of Pablo Jarillo Herrero at MIT, with whom we were collaborating very closely, reported superconductivity in twisted bilayer graphene at a magic angle twist. At a very special twist, you get this kind of behavior. So this is basically conductivity, or the potential for current in a direction in the sample, and this properly goes to 0 if you have a low enough temperature. So below about 1 degree K, you have superconducting behavior with 0 resistance. And this is schematic representation of the device. So a closer look of what is actually happening reveals even more exciting behavior. So here's a plot again of the conductance as a function of the carrier density, and as I mentioned before, the conductance axis is essentially equivalent to the density of states. The carrier density is equivalent to scanning the energy. 0 is the Fermi level of the original crystal, and you see these were the two humps that I referred to earlier of the high density of states due to the flat bands. But these are not the simple two humps that would have been expected from the simple considerations that I mentioned earlier. There are smaller gaps. So this is a band gap that I referred to earlier, but there are also smaller gaps in between. And if you blow up this region, you see that this axis now is temperature. And in this range of temperatures, the system is superconducting. In this range of, you go at higher temperatures, it has metallic behavior. In this range of carrier density, it's actually a Mott insulator, and so on. So these diagrams, so this diagram is for a twist of 1.16 degrees. This is for a twist of 1.05 degrees. And again, you see similar behavior. So these diagrams of superconducting behavior created a lot of excitement because they have a lot of similarities to the diagrams, the phase diagrams of the high temperature superconductors, the so-called cuprates. Here's the doping again, carrier density, and different phases. The similarity is not superficial, because if you look at what is happening from a slightly different perspective, you realize that these are highly correlated systems. So in this picture, I'm showing you the critical temperature on this axis as a function of carrier density on the horizontal axis, which can also be translated into a Fermi temperature. There's a connection between the density and the energy, the Fermi temperature. This is where the magic angle twisted bilayer graphene is. And as you see, it's relatively low in critical temperature, about 1 degree or so. There's many other materials that have much higher critical temperature for superconductivity. However, if you scale the critical temperature by the Fermi temperature, the different magic angle samples, all of them shown by red dots here, are actually have a higher value for the critical temperature scaled by the Fermi temperature than the high temperature cuprates. So in this sense, they are highly correlated systems, similar in behavior to what the cuprates exhibit. However, this presents a real problem in terms of explaining what is going on in the language of single particle physics that I employed so far. So again, in a very simple picture, single particle states are described by bands. So if you have a half-filled band, then you simply have a metal. But what the experiment was showing was that at a half-filled band, you create these extra mini band gaps. So what used to be one hump becomes two smaller ones. This is density of states again. And this is indicative of a Mott insulator, Mott-Hubbard insulator. And a single particle picture with electrons moving from lattice side to lattice side is not adequate, and you need to include electron repulsion and correlation, which is much more difficult to do. In fact, there's no resolution of this problem up to now. So this is a fancy picture saying that we need to understand better how single particle states combine to form many body types of correlated behavior. The ground state of these electronic states and interaction mechanisms between those quantum phases remains a mystery. But our detailed calculations can shed some light. So what I'm showing you here is, again, the band structure, the flat bands. Well, they're not totally flat. There's a small amount of dispersion, and other bands near them. The color coding corresponds to the projection of different wave functions on different parts of these bands. So the different colors correspond to projections on layer 1 or layer 2, sublattice A or sublattice B, different wave functions in different regions of the system of triangles that I was describing earlier. So these states are localized in these corners. These states are localized in the lines, which are the domain boundaries. These states are localized at the center of the triangles, and so on. And they're all interrelated. So focusing on just a couple of states near the Fermi level is not adequate. So from this picture, it becomes evident that the minimal model involves at least 6 coupled single particle states, and of course that makes the description of the many-body wave function much more demanding. There are simple theories of the Hubbard model and quite a bit of numerical work to understand the Hubbard model, but using essentially 1 particle per lattice site. Here we have to have the equivalent of 6 particles per lattice site of the Hubbard model, and each one of those particles has quite complicated wave functions in real space, all of which matters. So that's where we are. There's no simple theories to capture the many-body behavior, but there's a lot of insight from the calculations that we have been producing, and other groups are very diligently working to try to solve this problem. So what about more layers? So having played quite a bit with 2 layers, we were bold enough to go more to systems with more than 2 layers. So here's a little bit about the tri-layer graphene system. So twisted tri-layer graphene. So again, just as a reference point, this is the picture that I showed you already about the bilayer with the 2 Dirac cones intersecting and the flat bands forming. If you have 3 layers, you have 3 Dirac cones. The orange, the black, and the blue one, all of them intersect, and again the flat bands are formed, but other states are also formed, and it becomes much more complicated. Moreover, in this case you have 1 twist angle, 1 relative twist angle, 1 Moiré pattern, and the cell size of the Moiré pattern scales as 1 over theta, theta being the twist angle. In the tri-layer case, you have 2 different independent twist angles, more degrees of freedom to worry about, and the cell size scales as 1 over theta square, which means you have much bigger unit cells. It's quite exciting in that in the tri-layer graphene, superconductivity was also observed. Here's another phase diagram with superconducting regions and insulating regions and so on. That's the diagram that shows the flat region of the resistivity, zero resistance, true superconducting state, and quite a bit higher critical temperature at 3.4 degrees Kelvin. So, but in order to capture what is going on here, much more work needs to be done, detailed work of understanding the system. Fortunately, I had a brilliant student, this is Zoe Zhu, who did a lot of this work. So here's the outcome of this. So this is, I'm showing you the relaxation patterns for the tri-layer now. So there are 3 layers, layer 1 at the bottom, layer 2 in the middle, layer 3 at the top. And these are the patterns of atomic relaxation. This is the quantity that describes the atomic relaxation. And I have the curl of this quantity plotted in a color pattern here, so you can more easily see the patterns that are formed. The tiny boxes here are these where you can actually see the atomic scale features, where the atoms of the different layers are. And you can see that this is a box much larger than the atomic scale. And these are the patterns that you see. And of course, you see periodicities, different periodicities in the top layer or the bottom layer. If you zoom out, something interesting happens. So I'm zooming out now, and the black boxes here are what I just showed you in the previous slide. So the purple boxes are much larger in size, and again you see lots of interesting patterns here and lots of interesting periodicities. For example, in the curl of this quantity, if you zoom even further out in these big boxes, the purple boxes are the ones from the previous slide, and again you see lots of interesting patterns and lots of interesting periodicities. So there's a moire of a moire of a moire, and it keeps going, and the length scales become very, very large. Of course, we can't do calculations for all of these using the detailed atomistic models. It just becomes impractical. So then we created a model Hamiltonian in momentum space, for example, for the tri-layer, where you have the Hamiltonian of the individual layers along the diagonal and the coupling terms in the off-diagonal. And these coupling terms involve summations over reciprocal lattice vectors of the interaction terms, and you do these summations over a restricted region. That's what I mean by the cutoff. Of values of the reciprocal lattice vectors to satisfy the selection rules. And the essence of all this is that in the bilayer case, in the restricted region, you only have a few vectors that satisfy the selection rules. In the tri-layer case, because you have two different reciprocal space vectors here, you can go outside and come back inside the restricted region to get more matching, more values that satisfy the selection rules. So it's a much more complicated system, and indeed the band structure reflects this. So those are the bands of tri-layer graphene at these two different twist angles for layers 1, 2, and layers 2, 3. Again, very high density of states at the Fermi level, low density of states around it. But the new feature here is that there's no band gaps anymore, anywhere, under any conditions. So you cannot claim that you have a Hubbard insulator anymore. What's the alternative? Well, the alternative is phonon-mediated pairing of the electrons. So this is the classic BCS theory of superconductivity, Bardeen-Cooper-Schiffer. And in a simple picture, you have these electrons. One of them goes through the lattice, it distorts the lattice, the other one follows and feels the distortion. That's the phonon, and that provides the coupling. I know you are high energy in the string theorists. You may find this simple picture hard to understand. So here's something that you can understand, I believe, easily. So a phonon in a Feynman diagram creates the coupling between electrons. But this implies that we know very well what the phonons do. That's another big challenge, because the ways that the atoms vibrate around their equilibrium positions is not a trivial thing to capture. We have been doing a lot of detailed calculations. Here's some pictures of phonon modes in plane. These are the little arrows that I'm showing you, and out of plane. This is the color coding, how much out of plane motion there is for different stackings. And through this, we have created a nice theory of what phonons look like in these systems, both bilayers and trilayers, and we are in the middle of developing the electron-phonon coupling theory to capture what is going on in these systems, hopefully to give some insight of whether conventional superconductivity can account for what is seen in the trilayers or not. Okay. A little bit about work that I don't have time to describe, just to give you a flavor. We can do a lot of calculations and sort out which arrangements can give interesting features like flat bands. So here's 5 layers, here's 6 layers, twisted in different ways, and we can make lots of predictions for our experimental colleagues of where to search in this high-dimensional space for very interesting behavior. We're also doing So what I just showed you was for a single type of system. This is all graphene. This is lots of different materials labeled here, but I don't have time to explain what this corresponds to. We have created another effective Hamiltonian that allows us to examine many different materials, identify, again, interesting states which exhibit topological behavior. And I alluded to this a little bit at the very early part of the talk. So these are states that live on the boundaries of the material, and they cross the band gap, and that's a rigorous imposition on their behavior by the symmetry of the system. And there's a lot of interest in these types of topological behavior. And finally, we're exploring a lot about what can happen when you introduce defects and doping foreign atoms in these systems, which can be trapped by the deformation of induced by the relaxation, potentially acting as interesting structures of ordered arrays. And if you have localized spins here, those could be used possibly as qubits and so on. So that hopefully gives you a little bit of a broader picture of the types of investigations that we are doing currently in relation to the twisted layers. I've had the good luck to work with a fantastic group of students and postdocs. I showed you some of them and their pictures and their contributions as I was going along. Several more have contributed to the work that I've discussed. And here's a recent picture of the group, and here's a list of the main contributors. I showed you the pictures of Stephen Carr, Shang Fang, and Zoe Zhu, 3 students that have done really beautiful work, and many more have contributed. We've also had the good luck to work with wonderful experimental groups. I've mentioned some of them: Philip Kim at Harvard, Pablo Jarillo Herrero at MIT, Jenny Hoffman and Amir Yacobi also at Harvard. The mathematicians contributed very nicely in the formulation that, of configuration space that I described, and our condensed matter theory colleagues are working intensively, and we're collaborating with them to shed light on the many-body behavior of these types of systems. Here's acknowledgements to some of the funding agencies that supported this work. And I think I have a few more minutes to try to answer the existential question that I put at the very beginning. So with your permission, here's a slide that will try to address this. Why am I here in this conference of supersymmetry and unification of fundamental interactions? This conference takes place, as several of the speakers already mentioned, in this beautiful setting. It's their word, not my words. So somewhere in this beautiful setting is my home, where I was born and raised. Very close to this is the place where I spent my kindergarten and primary school years. A little bit farther away, where I spent secondary school and high school. And very close to my home was the original campus of the University of Ioannina. When I was in high school, George was in, where is George sitting? Yeah, there is George. Yeah, George was a graduate student. So he told me, why don't you come by, see what we're doing at the university? So I said, okay, I have nothing better to do. So I tagged along, and George took me to a lecture by Professor Vergados. And I don't know if you remember what it was about. Yes, it was about Green's functions. And I was hooked. I said, these guys are doing amazing things. I don't think I understood much, but I appreciated the beauty of what they were doing. So that's how I became a physicist. And in fact, my very first paper was on phenomenology, quark phenomenology, hyperon radiative decay, published in 1985. So in some ways, I followed the direction that George set me on. But shortly after that, I took a course in condensed matter physics, and I was really thrilled by condensed matter physics. Sorry, George, that I strayed a little bit away from the orthodoxy of physics, but that's the reason I'm here. Okay. Okay, so thank you for your attention. I'd be happy to take any questions. Yeah, that's a very good point. Yes, indeed it is. In fact, if you twist graphene, well, 0 or 180 degrees or 60 degrees are exactly equivalent. 30 degrees produces a quasi-crystal. And people are looking into that, and we've done some work, but not very much. I didn't present anything, but it is a very, very good point, and there's a lot of interest in this, but it has not risen to the level of the other structures that I showed you.
The other thing is that, have you considered creating effects, not just geometric effects like forms, and then superposing?
Yes, that's a very good point also. In fact, you can do that. Chemists are amazing in what they can do. They can take different types of molecules and create structures that contain holes. And then they're flat, like graphene, but they contain holes. They're not continuous in the position of all the atoms. And then they can take those and put them on top of each other and look into what's happening.
I mean, literally the cone. Maybe if you cut a wedge and do that, so you get a cone.
Yes, those are, yeah. Sorry, I heard holes. You meant cones. Yes, sorry. Yes, you can create these kinds of structures as well. And there are different realizations of this. You can even fold them on top of each other, a single layer. You can play a lot of games. But I don't know as much detailed work about this.
The reason is that it could be different kind of geometry, so there could be brilliant zone, and that doesn't quite work that way, but there will be something two-dimensional still.
Yeah.
And then if you put these layers on top of each other, that potentially could be new kind of.
Yeah, I think that's a wonderful suggestion. Let's go and talk to Philip Kim. Yeah. Mm-hmm. Yes. I don't know of any tetrahedral geometry. I know of structures that look like cones, now they're sort of folded with defects, so they form something like that, but I don't know of anything resembling tetrahedral geometry.
You mentioned that in the case at least of two layers, when you have this superconductivity, that this has some properties of strange metals. Now, strange metals, they have a specific sort of phase diagram where as you lower the carrier, you go from Fermi gas to a superconductive dome and then some striped region and then ridge layer. Now, is this true for this type of materials?
The phase diagrams of these materials have not been studied at the same level as the cuprates. So here's the cuprate phase diagram, and there's a lot of information about this. So this is basically what we have for these materials, these types of. So I don't know if there's more elaborate behavior here of the type that you're describing. It has not been examined at that level, but it could be.
For example, one of the hallmarks of these materials is that they have, especially in the optimal doping, they have linear conductivity that goes up quite a bit. Is that something that has been studied in this material?
Not as far as I know. So there's a metallic behavior here and Mott insulator here, but I don't know a lot of details about the behavior at the level that you're describing. But that's a very good point, yeah. Correct. Yes, absolutely. So there are moire patterns that have to do with mismatch of the lattice periodicity. And they have been producing these kinds of structures. And you can also do it by straining one layer relative to the other. And people are indeed creating those and examining what is going on. We have been doing also some work, but again, it's not at the level of what I just showed you already. Yes, but absolutely, these are very interesting possibilities, and people are exploring them. Yes. Yes. Okay. The theorem, at least as far as I understand it, didn't say that two-dimensional materials are prohibited, it said that because of this, the long-range fluctuations can be created with little energy, they would basically take over and destroy the crystal. So it's not a proof in itself, it was an expectation that the long-range fluctuations, so many of them would destroy the crystal periodicity. But there are long-range fluctuations, the layers are not flat. Okay, so this is very realistic. A flat layer of graphene for suspended graphene is not realistic. This is much more realistic. So there are lots of fluctuations. But the bonding at the atomic level is so strong that it doesn't destroy the crystal.
But somehow this is not related to the fact that there is no magnetization to it, that there is spontaneous.
Yes, there's no magnetization. It's just the fluctuations of the structure that are entropically favored. That's how I understood the reason for this argument. Yes, yes, that's a very good point. Yes, there are measurements. I don't have the details now. Graphene itself has extremely high mobility. A good fraction of it is realized experimentally. I don't know the exact number, but it's not, the experimental number is not orders of magnitude smaller than that. Maybe it's a few times smaller than that, but it's not many orders of magnitude smaller. So it is quite extraordinary. And there are measurements of conductivity in the twisted layers, and we have been gearing up to try to predict this. So for example, this is the kind of calculation that you need to do to calculate conductivities and so on. We're working on that. I don't have results to show you, but it is controlled by the twist. The twist makes a big difference, and we're trying to understand and rationalize this.
Yes, very nice talk. I would like to ask you a question on your superconductivity, on your phononic. You haven't seen phonons yet experimentally, as far as I understood, or you have? That's my first question.
No, phonons exist. There's no,
I know that,
yeah.
but in this particular material, do you know that the mechanism for superconductivity?
No, no. I did not say that it is. I said that no. We need to examine it. Yes, yes.
Second question comes about that.
Yeah.
In cap rates, also you have nodes at the Fermi surface, and therefore you have linear dispersion relations. The superconductivity is due to fractional statistics.
Yes.
Why here people, or have they looked here at anyons, for instance?
They are looking, they're trying to figure out what are the right many body states to describe this. But in order to do this, you need to have a Hubbard insulator. You need, and you don't have in this case. You just absolutely don't have. So that's why I think the alternative is worth exploring. Moreover, if you look at the phonons that I showed you here, I didn't have time to discuss this in more detail, but if you look at this, so this is a Moiré supercell. This is at 1 degree twist. This is at 7 degree twist. So even though I show you the same rhombus here, the length scales are very different. So this axis is 30 angstroms. This axis is 240 angstroms. Okay. So, but however, look at the phonon patterns themselves. They're at the corners of this rhombus, and at these corners is where the distortions of the lattice were that I showed you earlier. And this is where the electronic states are localized. So everything happens there. So it's intriguing. And electron-phonon coupling could play an interesting role.
Do you also have plasmons?
Yes, indeed. Yes. That's another whole branch. I didn't mention anything about plasmons. Yeah, we've worked on graphene plasmons quite a bit. And we try to extend it to these twisted systems. But plasmons do exist, especially in graphene, and they have a lot of interesting possibilities. Moreover, creating sandwiches between layers of graphene and insulating layers is very, very promising for manipulating plasmons and creating zero epsilon behavior and so on. So we've done a lot of work on that, but I didn't include it here. Yeah. Yes, that's a really excellent point that you're raising. Graphene itself doesn't have spin behavior. It's not spin polarized, and it doesn't have spin orbit coupling. It's basically negligible, but other systems do. Again, I didn't have time to discuss this in detail, but this bunch of, so these are a lot of different materials. Every band structure corresponds to a different material. So each of these materials is twisted at a different angle, and they create different states. So this is the Hamiltonian. In the Hamiltonian, there's a term that corresponds to spin polarization. Exactly to capture the effects that you were describing. So these are materials other than graphene. And we are trying to explore this, yes.
Possibly including any transition metal that might...
Exactly. So these materials do indeed include transition metals. So this is tungsten, sulfur, selenium. So tungsten is, of course, a transition metal with spin and so on. So we're indeed exploring this. And in fact, this is a very interesting structure. The transition metal is in the middle, and the sulfur and the selenium are on the two sides. This is a structure that we proposed theoretically. We didn't think it would be easy to produce, so experimentalists produced it, and now we're exploring it at great length to capture these types of effects.
So thank you very much. I mean, this amazing work. One thing that really struck me, probably I didn't get it exactly, is you're working in configuration space, so you have small cells. So you're looking at the local properties, but within your theory, you managed to capture all the long-range correlations in the system.
Yes. So basically what we're doing is we're sampling all the possible local structures when we want to take this integral over all the possibilities to calculate physical observables. But when we want to have the detailed structure, we have the actual atomic structure, but it's relaxed. It's created by this mechanism that I was telling you, the generalized stacking fault energy, which again is from small cells, but you determine the deformation potential for the entire set of possible. Yes. Right. Right. That's right. That's right. That's right. So like these structures that I was showing you, oops, sorry, I'm going the wrong direction. Yeah, these structures were relaxed with this method that I showed you, but then we know exactly the atomic positions, and then we can create an equivalent Hamiltonian for the local vibrations, so the cost of local atomic displacements. And that's what gives us the phonon modes.
Yes, but also not only the phonon modes, but the first one is a bilayer. It was also collective long-range correlations between the Moore patterns, right?
Yes, yes. Yes, because the deformation applies to the entire layer. Yes, yeah. Okay. Correct.
Does that mean that we could drive down an effective theory for the associated vectors with reasonably short range interactions, for example, the more possibility that will determine the long range?
Yes, basically yes. Yes. And
this is more or less a local theory.
Exactly. Yes. And we have published a paper explaining all of this in great detail. I don't think I can reproduce it here. Yes. But what you were saying captures the essence of it. Yes. Thank you very much.
I think we can move now downstairs, and there's a reception, wine, I suppose so. And
Okay, great.